Failure of the physical philosophy of the Greek schools. Sect, one result of the Greek school philosophy. The methods and forms of philosophizing which we have described as employed by the Greek schools failed altogether in their application to physics. No discovery of general laws, no explanation of special phenomena rewarded the acuteness and boldness of these early students of nature. Astronomy, which made considerable progress during the existence of the sects of Greek philosophers, gained perhaps something by the authority with which Plato taught the supremacy and universality of mathematical rule and order. And the truths of harmonics, which had probably given rise to the Pythagorean passion for numbers, were cultivated with much care by that school. But after these first impulses, the sciences owed nothing to the philosophical sects, and the vast and complex accumulations and apparatus of the Stagirite do not appear to have led to any theoretical physical truths. This assertion hardly requires proof, since in the existing body of science there are no doctrines for which we are indebted to the Aristotelian school. Real truths, when once established, remain to the end of time a part of the mental treasure of man, and may be discerned through all the additions of later days. But we can point out no physical doctrine now received, of which we trace the anticipation in Aristotle, in the way in which we see the Copernican system anticipated by Aristarchus, the resolution of the heavenly appearances into circular motions suggested by Plato, and the numerical relations of musical intervals ascribed to Pythagoras. But it may be worthwhile to look at this matter more closely. Among the works of Aristotle are 38 chapters of problems, which may serve to exemplify the progress he had really made in the reduction of phenomena to laws and causes. Of these problems, a large proportion are physiological, and these I here pass by, as not illustrative of the state of physical knowledge. But those which are properly physical are, for the most part, questions concerning such 81 facts and difficulties as it is the peculiar business of theory to explain. Now it may be truly said that in scarcely any one instance are the answers, which Aristotle gives to his questions, of any value. For the most part, indeed, he propounds his answer with a degree of hesitation or vacillation, which of itself shows the absence of all scientific distinctness of thought, and the opinions so offered never appear to involve any settled or general principle. We may take, as examples of this, the problems of the simplest kind, where the principles lay nearest at hand the mechanical ones. Why, he asks, do small forces move great weights by means of a lever, when they have thus to move the lever added to the weight? Is it, he suggests, because a greater radius moves faster? Why does a small wedge split great weights? Is it because the wedge is composed of two opposite levers? Why, when a man rises from a chair, does he bend his leg and his body to acute angles with his thigh? Is it because a right angle is connected with equality and rest? Why can a man throw a stone further with a sling than with his hand? Is it that when he throws with his hand, he moves the stone from rest, but when he uses the sling, he throws it already in motion? Why, if a circle be thrown on the ground, does it first describe a straight line and then a spiral as it falls? Is it that the air first presses equally on the two sides and supports it, and afterwards presses on one side more? Why is it difficult to distinguish a musical note from the octave above? Is it that proportion stands in the place of equality? It must be allowed that these are very vague and worthless surmises. For even if we were, as some commentators have done, to interpret some of them so as to agree with sound philosophy, we should still be unable to point out, in this author's works, any clear or permanent apprehension of the general principles which such an interpretation implies. Thus, the Aristotelian physics cannot be considered as otherwise than a complete failure. It collected no general laws from facts, and consequently, when it tried to explain facts, it had no principles which were of any avail. The same may be said of the physical speculations of the other schools of philosophy. They arrived at no doctrines from which they could deduce, by sound reasoning, such facts as they saw, though they 82 often venture so far to trust their principles as to infer from them propositions beyond the domain of sense. Thus, the principle that each element seeks its own place led to the doctrine that, the place of fire being the highest, there is, above the air, a sphere of fire of which doctrine the word empyrean, used by our poets, still conveys a reminiscence. The Pythagorean tenet that 10 is a perfect number led some persons to assume that the heavenly bodies are in number 10. And as 9 only were known to them, they asserted that there was an anteichthon or counter-earth on the other side of the sun, invisible to us. Their opinions respecting numerical ratios led to various other speculations concerning the distances and positions of the heavenly bodies. And as they had, in other cases, found a connection between proportions of distance and musical notes, they assumed, on this suggestion, the music of the spheres. Although we shall look in vain in the physical philosophy of the Greek schools for any results more valuable than those just mentioned, we shall not be surprised to find, recollecting how much an admiration for classical antiquity has possessed the minds of men, that some writers estimate their claims much more highly than they are stated here. Among such writers, we may notice Dutens, who, in 1766, published his Origin of the Discoveries attributed to the moderns, in which it is shown that our most celebrated philosophers have received the greatest part of their knowledge from the works of the ancients. The thesis of this work is attempted to be proved, as we might expect, by very large interpretations of the general phrases used by the ancients. Thus, when Timaeus, in Plato's dialogue, says of the creator of the world, that he infused into it two powers, the origins of motions, both of that of the same thing and of that of different things. Dutens finds in this a clear indication of the projectile and attractive forces of modern science. And in some of the common declamation of the Pythagoreans and Platonists concerning the general prevalence of numerical relations in the universe, he discovers their acquaintance with the law of the inverse square of the distance by which gravitation is regulated, though he allows that it required all the penetration of Newton and his followers to detect this law in the scanty fragments by which it is transmitted. Argument of this kind is palpably insufficient to cover the failure of the Greek attempts at a general physical philosophy, or rather we 83 may say that such arguments, since they are as good as can be brought in favor of such an opinion, show more clearly how entire the failure was. I proceed now to endeavor to point out its causes. Sect 2. Cause of the failure of the Greek physical philosophy. The cause of the failure of so many of the attempts of the Greeks to construct physical science is so important that we must endeavor to bring it into view here, though the full development of such subjects belongs rather to the philosophy of induction. The subject must, at present, be treated very briefly. I will first notice some errors which may naturally occur to the reader's mind as possible causes of failure, but which, we shall be able to show, were not the real reasons in this case. The cause of failure was not the neglect of facts. It is often said that the Greeks disregarded experience and spun their philosophy out of their own thoughts alone, and this is supposed by many to be their essential error. It is, no doubt, true that the disregard of experience is a phrase which may be so interpreted as to express almost any defect of philosophical method, since coincidence with experience is requisite to the truth of all theory. But if we fix a more precise sense on our terms, I conceive it may be shown that the Greek philosophy did, in its opinions, recognize the necessity and paramount value of observations, did, in its origin, proceed upon observed facts, and did employ itself to no small extent in classifying and arranging phenomena. We must endeavor to illustrate these assertions, because it is important to show that these steps alone do not necessarily lead to science. 1. The acknowledgement of experience as the main ground of physical knowledge is so generally understood to be a distinguishing feature of later times that it may excite surprise to find that Aristotle and other ancient philosophers not only asserted in the most pointed manner that all our knowledge must begin from experience, but also stated in language much resembling the habitual phraseology of the most modern schools of philosophizing that particular facts must be collected, that from these general principles must be obtained by induction, and that these principles, when of the most general kind, are axioms. A few passages will show this. The way must be the same, says Aristotle, in speaking of the rules of reasoning, with respect to philosophy, as it is with respect to 84, any art or science whatever. We must collect the facts, and the things to which the facts happen in each subject, and provide as large a supply of these as possible. He then proceeds to say that we are not to look at once at all this collected mass, but to consider small and definite portions. and thus it is the office of observation to supply principles in each subject. For instance, astronomical observation supplies the principles of astronomical science. For the phenomena being properly assumed, the astronomical demonstrations were from these discovered, and the same applies to every art and science. So that if we take the facts, tau letter 1F70, letter 1F51 pi alpha rho chi omicron u tau alpha, belonging to each subject, it is our task to mark out clearly the course of the demonstrations. For if in our natural history, kappa alpha tau letter 1F70, tau letter 1F74 nu letter 1F31 sigma tau omicron rho ode alpha nu, we have omitted nothing of the facts and properties which belong to the subject, we shall learn what we can demonstrate and what we cannot. These facts, tau letter 1F70, letter 1F51 pi alpha rho chi omicron u tau alpha, he at other times includes in the term sensation. Thus, he says, it is obvious that if any sensation is wanting, there must be also some knowledge wanting which we are thus prevented from having, since we arrive at knowledge either by induction or by demonstration. Demonstration proceeds from universal propositions, induction from particulars. But we cannot have universal theoretical propositions except from induction, and we cannot make inductions without having sensation, for sensation has to do with particulars. In another place, after stating that principles must be prior to, and better known than conclusions, he distinguishes such principles into absolutely prior and prior relative to us. The prior principles, relative to us, are those which are nearer to the sensation, but the principles absolutely prior are those which are more remote from the sensation. The most general principles are the more remote, the more particular are nearer. The general principles which are necessary to knowledge are axioms. We may add to these passages that in which he gives an account of the way in which Leucippus was led to the doctrine of atoms. After describing the opinions of some earlier philosophers, he says, thus proceeding in violation of sensation and disregarding it, because, as they held, they must follow reason, some came to the conclusion that the universe was one and infinite and at rest. As it appeared, however, that though this ought to be by reasoning, it 85 would go near to madness to hold such opinions in practice, for no one was ever so mad as to think fire and ice to be one. Leucippus, therefore, pursued a line of reasoning which was in accordance with sensation, and which was not irreconcilable with the production and decay, the motion and multitude of things. It is obvious that the school to which Leucippus belonged, the eclectic, must have been, at least in its origin, strongly impressed with the necessity of bringing its theories into harmony with the observed course of nature. Nor was this recognition of the fundamental value of experience a mere profession. The Greek philosophy did, in its beginning, proceed upon observation. Indeed, it is obvious that the principles which it adopted were, in the first place, assumed in order to account for some classes of facts, however imperfectly they might answer their purpose. The principle of things seeking their own places was invented in order to account for the falling and floating of bodies. Again, Aristotle says, that heat is that which brings together things of the same kind. Cold is that which brings together things whether of the same or of different kinds. It is plain that in this instance he intended by his principle to explain some obvious facts as the freezing of moist substances and the separation of heterogeneous things by fusion. For, as he adds, if fire brings together things which are akin, it will separate those which are not akin. It would be easy to illustrate the remark further, but its truth is evident from the nature of the case. For no principles could be accepted for a moment which were the result of an arbitrary caprice of the mind, and which were not in some measure plausible and apparently confirmed by facts. But the works of Aristotle show, in another way, how unjust it would be to accuse him of disregarding facts. Many large treatises of his consist almost entirely of collections of facts, as for instance, those on colors, on sounds, and the collection of problems to which we have already referred, to say nothing of the numerous collection of facts bearing on natural history and physiology, which form a great portion of his works and are even now treasuries of information. A moment's reflection will convince us that the physical sciences of our own times, for example, mechanics and hydrostatics, are founded almost entirely upon facts with which the ancients were as familiar as we are. The defect of their philosophy, therefore, wherever it may lie, consists neither in the speculative depreciation of the value of facts, nor in the practical neglect of their use. 3. Nor again should we hit upon the truth if we were to say that 86 Aristotle and other ancient philosophers did indeed collect facts, but that they took no steps in classifying and comparing them, and that thus they failed to obtain from them any general knowledge. For in reality, the treatises of Aristotle which we have mentioned are as remarkable for the power of classifying and systematizing which they exhibit as for the industry shown in the accumulation. But it is not classification of facts merely which can lead us to knowledge, except we adopt that special arrangement, which, in each case, brings into view the principles of the subject. We may easily show how unprofitable an arbitrary or random classification is, however orderly and systematic it may be. For instance, for a long period all unusual fiery appearances in the sky were classed together as meteors. Comets, shooting stars and globes of fire, and the aurora borealis in all its forms were thus grouped together, and classifications of considerable extent and minuteness were proposed with reference to these objects. But this classification was of a mixed and arbitrary kind. Figure, color, motion, duration were all combined as characters, and the imagination lent its aid, transforming these striking appearances into fiery swords and spears, bears and dragons, armies and chariots. The facts so classified were, notwithstanding, worthless, and would not have been one jot the less so, had they and their classes been 10 times as numerous as they were. No rule or law that would stand the test of observation was or could be thus discovered. Such classifications have, therefore, long been neglected and forgotten. Even the ancient descriptions of these objects of curiosity are unintelligible or unworthy of trust, because the spectators had no steady conception of the usual order of such phenomena. For, however much we may fear to be misled by preconceived opinions, the caprices of imagination distort our impressions far more than the anticipations of reason. In this case men had, indeed we may say with regard to many of these meteors, they still have, no science, not for want of facts, nor even for want of classification of facts, but because the classification was one in which no real principle was contained. For, since, as we have said before, 2 things are requisite to science, facts and ideas, and since, as we have seen, facts were not wanting in the physical speculations of the ancients, we are naturally led to ask, were they then deficient in ideas? Was there a want among them of mental activity and logical connection of thought? But it is so obvious that the answer to this inquiry must be in the negative that we need not dwell upon it. No one who knows anything of the 87 history of the ancient Greek mind can question that in acuteness, in ingenuity, in the power of close and distinct reasoning, they have never been surpassed. The common opinion, which considers the defect of their philosophical character to reside rather in the exclusive activity of such qualities than in the absence of them, is at least so far just. 5. We come back again, therefore, to the question, what was the radical and fatal defect in the physical speculations of the Greek philosophical schools? To this I answer. The defect was that though they had in their possession facts and ideas, the ideas were not distinct and appropriate to the facts. The peculiar characteristics of scientific ideas, which I have endeavored to express by speaking of them as distinct and appropriate to the facts, must be more fully and formally set forth when we come to the philosophy of the subject. In the meantime, the reader will probably have no difficulty in conceiving that, for each class of facts, there is some special set of ideas, by means of which the facts can be included in general scientific truths, and that these ideas, which may thus be termed appropriate, must be possessed with entire distinctness and clearness, in order that they may be successfully applied. It was the want of ideas having this reference to material phenomena, which rendered the ancient philosophers, with very few exceptions, helpless and unsuccessful speculators on physical subjects. This must be illustrated by 1 or 2 examples. One of the facts which Aristotle endeavors to explain is this, that when the sun's light passes through a hole, whatever be the form of the hole, the bright image, if formed at any considerable distance from the hole, is round, instead of imitating the figure of the hole, as shadows resemble their objects in form. We shall easily perceive this appearance to be a necessary consequence of the circular figure of the sun. If we conceive light to be diffused from the luminary by means of straight rays proceeding from every point of the sun's disk and passing through every point within the boundary of the whole. By attending to the consequences of this mode of conception, it will be seen that each point of the whole will be the vertex of a double cone of rays, which has the sun's disk for its base on one side and an image of the sun on the other. And the figure of the image of the whole will be determined by supposing a series of equal bright circles, images of the sun, to be placed along the boundary of an image equal to the whole itself. The figure of the image thus determined will partake of the form of the whole, and 88 of the circular form of the sun's image. But these circular images become larger and larger as they are further from the whole, while the central image of the whole remains always of the original size. And thus, at a considerable distance from the whole, the trace of the whole's form is nearly obliterated, and the image is nearly a perfect circle. Instead of this distinct conception of a cone of rays which has the sun's disk for its basis, Aristotle has the following loose conjecture. Is it because light is emitted in a conical form, and of a cone the base is a circle, so that on whatever the rays of the sun fall, they appear more circular? And thus, though he applies the notion of rays to this problem, he possesses this notion so indistinctly that his explanation is of no value. He does not introduce into his explanation the consideration of the sun's circular figure, and is thus prevented from giving a true account of this very simple optical phenomenon. Again, to pass to a more extensive failure. Why was it that Aristotle, knowing the property of the lever and many other mechanical truths, was unable to form them into a science of mechanics, as Archimedes afterwards did? The reason was that, instead of considering rest and motion directly, and distinctly with reference to the idea of cause, that is force, he wandered in search of reasons among other ideas and notions, which could not be brought into steady connection with the facts, the ideas of properties of circles, of proportions of velocities, the notions of strain and common, of natural and unnatural. Thus, in the proem to his mechanical problems, after stating some of the difficulties which he has to attack, he says, of all such cases, the circle contains the principle of the cause. And this is what might be looked for it is nothing absurd if something wonderful is derived from something more wonderful still. Now the most wonderful thing is that opposites should be combined, and the circle is constituted of such combinations of opposites. For it is constructed by a stationary point and a moving line, which are contrary to each other in nature, and hence we may the less be surprised at the resulting contrarieties. And in the first place, the circumference of the circle, though a line without breadth, has opposite qualities, for it is both convex and concave. In the next place, it has, at the same time, opposite motions, for it moves forward and backward at the same time. For the circumference, setting out from any point, comes to the same point again, so 89 that by a continuous progression, the last point becomes the first. So that, as was before stated, it is not surprising that the circle should be the principle of all wonderful properties. Aristotle afterwards proceeds to explain more specially how he applies the properties of the circle in this case. The reason, he says in his fourth problem, why a force, acting at a greater distance from the fulcrum, moves a weight more easily, is that it describes a greater circle. He had already asserted that when a body at the end of a lever is put in motion, it may be considered as having two motions, one in the direction of the tangent and one in the direction of the radius. The former motion is, he says, according to nature, the latter, contrary to nature. Now in the smaller circle, the motion, contrary to nature, is more considerable than it is in the larger circle. Therefore, he adds, the mover or weight at the larger arm will be transferred further by the same force than the weight moved, which is at the extremity of the shorter arm. These loose and inappropriate notions of natural and unnatural motions were unfit to lead to any scientific truths, and, with the habits of thought which dictated these speculations, a perception of the true grounds of mechanical properties was impossible. 7. Thus, in this instance, the error of Aristotle was the neglect of the idea appropriate to the facts, namely, the idea of mechanical cause, which is force, and the substitution of vague or inapplicable notions involving only relations of space or emotions of wonder. The errors of those who failed similarly in other instances were of the same kind. To detail or classify, these would lead us too far into the philosophy of science, since we should have to enumerate the ideas which are appropriate, and the various classes of facts on which the different sciences are founded, a task not to be now lightly undertaken. But it will be perceived, without further explanation, that it is necessary, in order to obtain from facts any general truth, that we should apply to them that appropriate idea, by which permanent and definite relations are established among them. In such ideas the ancients were very poor, and the stunted and deformed growth of their physical science was the result of this penury. The ideas of space and time, number and motion, they did indeed possess distinctly, and so far as these went, their science was tolerably healthy. They also caught a glimpse of the idea of a medium by which the qualities of bodies, as colors and sounds, are perceived. But the idea of substance remained barren in their hands. In speculating about elements and qualities, they went the wrong way, assuming that the properties of compounds must resemble those of the elements which determine them, and their loose notions of contrariety never approached the form of those ideas of polarity, which, in modern times, regulate many parts of physics and chemistry. If this statement should seem to anyone to be technical or arbitrary, we must refer, for the justification of it, to the philosophy of science, of which we hope hereafter to treat. But it will appear, even from what has been here said, that there are certain ideas or forms of mental apprehension, which may be applied to facts in such a manner as to bring into view fundamental principles of science. While the same facts, however arrayed or reasoned about, so long as these appropriate ideas are not employed, cannot give rise to any exact or substantial knowledge. This account of the cause of failure in the physical speculations of the ancient Greek philosophers has been objected to as unsatisfactory. I will offer a few words in explanation of it. The mode of accounting for the failure of the Greeks in physics is, in substance, that the Greeks in their physical speculations fixed their attention upon the wrong aspects and relations of the phenomena, and that the aspects and relations in which phenomena are to be viewed in order to arrive at scientific truths may be arranged under certain heads, which I have termed ideas, such as space, time, number, cause, likeness. In every case, there is an idea to which the phenomena may be referred, so as to bring into view the laws by which they are governed. This idea I term the appropriate idea in such case, and in order that the reference of the phenomena to the law may be clearly seen, the idea must be distinctly possessed. Thus, the reason of Aristotle's failure in his attempts at mechanical science is that he did not refer the facts to the appropriate idea, namely force, the cause of motion, but to relations of space and the like. That is, he introduces geometrical instead of mechanical ideas. It may be said that we learn little by being told that Aristotle's failure in this and the like cases arose from his referring to the wrong class of ideas, or, as I have otherwise expressed it, fixing his attention upon the wrong aspects and relations of the facts, since, it may be said, this is only to state in other words that he did fail. But this criticism is, I think, ill-founded. The account which I have given is not only a statement that Aristotle and others who took a like course did fail, but also that they failed in one certain point out of several 91, which are enumerated. They did not fail because they neglected to observe facts. They did not fail because they omitted to class facts. They did not fail because they had not ideas to reason from, but they failed because they did not take the right ideas in each case. And so long as they were in the wrong in this point, no industry in collecting facts or ingenuity in classing them and reasoning about them could lead them to solid truth. Nor is this account of the nature of their mistake without its instruction for us, although we are not to expect to derive from the study of their failure any technical rule which shall necessarily guide us to scientific discovery. For their failure teaches us that, in the formation of science, an error in the ideas is as fatal to the discovery of truth as an error in the facts, and may as completely impede the progress of knowledge. I have in books Roman 2. To X, of the philosophy, shown historically how large a portion of the progress of science consists in the establishment of appropriate ideas as the basis of each science. Of the two main processes by which science is constructed, as stated in Book 11. Of that work, namely the explication of conceptions and the colligation of facts, the former must precede the latter. In Book 12. Chapter 5 of the Philosophy, I have stated the maxim concerning appropriate ideas in this form, that the idea and the facts must be homogeneous. When I say that the failure of the Greeks in physical science arose from their not employing appropriate ideas to connect the facts, I do not use the term appropriate in a loose popular sense, but I employ it as a somewhat technical term to denote the appropriate idea, out of that series of ideas which have been made, as I have shown in the philosophy, the foundation of sciences, namely, space, time, number, cause, likeness, substance, and the rest. It appears to me just to say that Aristotle's failure in his attempts to deal with problems of equilibrium arose from his referring to circles, velocities, notions of natural and unnatural, and the like, conceptions depending upon ideas of space, of nature, and sea, which are not appropriate to these problems, and from his missing the idea of mechanical force or pressure, which is the appropriate idea. I give this not as an account of all failures in attempts at science, but only as the account of such radical and fundamental failures as this of Aristotle, who, with a knowledge of the facts, failed to connect them into a really scientific view. If I had to compare rival theories of a more complex kind, I should not necessarily say that one involved 92 an appropriate idea and the other did not, though I might judge one to be true and the other to be false. For instance, in comparing the emissive and the undulatory theory of light, we see that both involve the same idea, the idea of a medium acting by certain mechanical properties. The question there is, what is the true view of the mechanism of the medium? It may be remarked, however, that the example of Aristotle's failure in physics, given in p. 87, namely, his attempted explanation of the round image of a square hole, is a specimen rather of indistinct than of inappropriate ideas. The geometrical explanation of this phenomenon, which I have there inserted, was given by Maurolycus, and before him by Leonardo da Vinci. We shall, in the next book, see the influence of the appropriate general ideas in the formation of various sciences. It need only be observed, before we proceed, that, in order to do full justice to the physical knowledge of the Greek schools of philosophy, it is not necessary to study their course after the time of their founders. Their fortunes, in respect of such acquisitions as we are now considering, were not progressive. The later chiefs of the schools followed the earlier masters, and though they varied much, they added little. The Romans adopted the philosophy of their Greek subjects, but they were always, and indeed, acknowledged themselves to be, inferior to their teachers. They were as arbitrary and loose in their ideas as the Greeks, without possessing their invention acuteness and spirit of system. In addition to the vagueness which was combined with the more elevated trains of philosophical speculation among the Greeks, the Romans introduced into their treatises a kind of declamatory rhetoric, which arose probably from their forensic and political habits, and which still further obscured the waning gleams of truth. Yet we may also trace in the Roman philosophers to whom this charge mostly applies, Lucretius, Pliny, Seneca, the national vigor and ambition. There is something Roman in the public spirit and anticipation of universal empire which they display, as citizens of the intellectual republic. Though they speak sadly or slightingly of the achievements of their own generation, they betray a more abiding and vivid belief in the dignity and destined advance of human knowledge as a whole than is obvious among the Greeks. We must, however, turn back, in order to describe steps of more definite value to the progress of science than those which we have hitherto noticed. 93, Book 2. History of the Physical Sciences in Ancient Greece. Nu alpha rho theta eta cap omicron pi lambda eta rho. Mega tau omicron u delta letter 1 f7 2, theta eta rho letter 1 f6, mu alpha iota pi upsilon rho letter 1 f7 8, sigma pi eta gamma letter 1 f7 4, nu kappa lambda omicron pi alpha iota alpha nu. Letter 1 f23 delta iota delta alpha sigma cap alpha lambda omicron sigma, tau epsilon chi nu eta sigma, pi alpha sigma eta sigma, beta rho omicron tau omicron letter 1 fd6, sigma pi epsilon phi letter 1 fc6, nu epsilon kappa alpha letter 1 f76, mu epsilon gamma alpha sigma, pi omicron rho omicron sigma. Prom. Vinct. 109. I brought to earth the spark of heavenly fire, concealed at first and small, but spreading soon among the sons of men, and burning on teacher of art and use, and fount of power. 95. Introduction. In order to the acquisition of any such exact and real knowledge of nature as that which we properly call physical science, it is requisite, as has already been said, that men should possess ideas both distinct and appropriate, and should apply them to ascertained facts. They are thus led to propositions of a general character, which are obtained by induction, as will elsewhere be more fully explained. We proceed now to trace the formation of sciences among the Greeks by such processes. The provinces of knowledge which thus demand our attention are astronomy, mechanics and hydrostatics, optics and harmonics, of which I must relate, first, the earliest stages and next, the subsequent progress. Of these portions of human knowledge, astronomy is, beyond doubt or comparison, much the most ancient and the most remarkable, and probably existed, in somewhat of a scientific form, in Chaldea and Egypt and other countries, before the period of the intellectual activity of the Greeks. But I will give a brief account of some of the other sciences before I proceed to astronomy, for two reasons. First, because the origin of astronomy is lost in the obscurity of a remote antiquity, and therefore we cannot exemplify the conditions of the first rise of science so well in that subject as we can in others which assumed their scientific form at known periods. And next, in order that I may not have to interrupt, after I have once begun it, the history of the only progressive science which the ancient world produced. It has been objected to the arrangement here employed that it is not symmetrical, and that astronomy, as being one of the physical sciences, ought to have occupied a chapter in this second book, instead of having a whole book to itself, Book 3. I do not pretend that the arrangement is symmetrical, and have employed it only on the ground of convenience. The importance and extent of the history of astronomy are such that this science could not, with a view to our purposes, be made coordinate with mechanics or optics. 96. Chapter 1. Earliest stages of mechanics and hydrostatics. Sect 1. Mechanics. Astronomy is a science so ancient that we can hardly ascend to a period when it did not exist. Mechanics, on the other hand, is a science which did not begin to be till after the time of Aristotle, for Archimedes must be looked upon as the author of the first sound knowledge on this subject. What is still more curious, and shows remarkably how little the continued progress of science follows inevitably from the nature of man, this department of knowledge, after the right road had been fairly entered upon, remained absolutely stationary for nearly 2,000 years. No single step was made, in addition to the propositions established by Archimedes, till the time of Galileo and Stevinus. This extraordinary halt will be a subject of attention hereafter. At present, we must consider the original advance. The great step made by Archimedes in mechanics was the establishing upon true grounds the general proposition concerning a straight lever, loaded with two heavy bodies and resting upon a fulcrum. The proposition is that two bodies so circumstanced will balance each other, when the distance of the smaller body from the fulcrum is greater than the distance of the other, in exactly the same proportion in which the weight of the body is less. This proposition is proved by Archimedes in a work which is still extant, and the proof holds its place in our treatises to this day as the simplest which can be given. The demonstration is made to rest on assumptions which amount in effect to such definitions and axioms as these: that those bodies are of equal weight which balance each other at equal arms of a straight lever, and that in every heavy body there is a definite point called a center of gravity, in which point we may suppose the weight of the body collected. The principle, which is really the foundation of the validity of the demonstration thus given, and which is the condition of all experimental knowledge on the subject, is this: that when two equal weights are supported on a lever, they act on the fulcrum of the lever with the 97, same effect as if they were both together supported immediately at that point. Or more generally, we may state the principle to be this: that the pressure by which a heavy body is supported continues the same, however we alter the form or position of the body, so long as the magnitude and material continue the same. The experimental truth of this principle is a matter of obvious and universal experience. The weight of a basket of stones is not altered by shaking the stones into new positions. We cannot make the direct burden of a stone less by altering its position in our hands, and if we try the effect on a balance or a machine of any kind, we shall see still more clearly and exactly that the altered position of one weight, or the altered arrangement of several, produces no change in their effect, so long as their point of support remains unchanged. This general fact is obvious when we possess in our minds the ideas which are requisite to apprehend it clearly. But when we are so prepared, the truth appears to be manifest, even independent of experience, and is seen to be a rule to which experience must conform. What, then, is the leading idea which thus enables us to reason effectively upon mechanical subjects? By attention to the course of such reasonings, we perceive that it is the idea of pressure. Pressure being conceived as a measurable effect of heavy bodies at rest, distinguishable from all other effects, such as motion, change of figure, and the like. It is not here necessary to attempt to trace the history of this idea in our minds, but it is certain that such an idea may be distinctly formed, and that upon it the whole science of statics may be built. Pressure, load, weight are names by which this idea is denoted when the effect tends directly downwards. But we may have pressure without motion, or dead pull in other cases, as at the critical instant when two nicely matched wrestlers are balanced by the exertion of the utmost strength of each. Pressure in any direction may thus exist without any motion whatever. But the causes which produce such pressure are capable of producing motion, and are generally seen producing motion, as in the above instance of the wrestlers, or in a pair of scales employed in weighing. And thus men come to consider pressure as the exception, and motion as the rule, or perhaps they image to themselves the motion which might or would take place. For instance, the motion which the arms of a lever would have if they did move. They turn away from the case really before them, which is that of bodies at rest, and balancing each other, and pass to another case, which is arbitrarily 98, assumed to represent the first. Now this arbitrary and capricious evasion of the question we consider as opposed to the introduction of the distinct and proper idea of pressure, by means of which the true principles of this subject can be apprehended. We have already seen that Aristotle was in the number of those who thus evaded the difficulties of the problem of the lever, and consequently lost the reward of success. He failed, as has before been stated, in consequence of his seeking his principles and notions, either vague and loose, as the distinction of natural and unnatural motions, or else inappropriate, as the circle which the weight would describe, the velocity which it would have if it moved, circumstances which are not part of the fact under consideration. The influence of such modes of speculation was the main hindrance to the prosecution of the true Archimedean form of the science of mechanics. The mechanical doctrine of equilibrium is statics. It is to be distinguished from the mechanical doctrine of motion, which is termed dynamics, and which was not successfully treated till the time of Galileo. Sect 2 Hydrostatics. Archimedes not only laid the foundations of the statics of solid bodies, but also solved the principal problem of hydrostatics, or the statics of fluids, namely, the conditions of the floating of bodies. This is the more remarkable, since not only did the principles which Archimedes established on this subject remain unpursued till the revival of science in modern times, but when they were again put forward, the main proposition was so far from obvious that it was termed, and is to this day called, the hydrostatic paradox. The true doctrine of hydrostatics, however, assuming the idea of pressure, which it involves, in common with the mechanics of solid bodies, requires also a distinct idea of a fluid, as a body of which the parts are perfectly movable among each other by the slightest partial pressure, and in which all pressure exerted on one part is transferred to all other parts. From this idea of fluidity necessarily follows that multiplication of pressure which constitutes the hydrostatic paradox, and the notion being seen to be verified in nature, the consequences were also realized as facts. This notion of fluidity is expressed in the postulate which stands at the head of Archimedes' treatise on floating bodies. And from this principle are deduced the solutions, not only of the simple problems of the science, but of some problems of considerable complexity. 99. The difficulty of holding fast this idea of fluidity so as to trace its consequences with infallible strictness of demonstration may be judged of from the circumstance that, even at the present day, men of great talents, not unfamiliar with the subject, sometimes admit into their reasonings an oversight or fallacy with regard to this very point. The importance of the idea when clearly apprehended and securely held may be judged of from this, that the whole science of hydrostatics in its most modern form is only the development of the idea. And what kind of attempts at science would be made by persons destitute of this idea, we may see in the speculations of Aristotle concerning light and heavy bodies, which we have already quoted, where, by considering light and heavy as opposite qualities, residing in things themselves, and by an inability to apprehend the effect of surrounding fluids in supporting bodies, the subject was made a mass of false or frivolous assertions, which the utmost ingenuity could not reconcile with facts, and could still less deduce from the asserted doctrines any new practical truths. In the case of statics and hydrostatics, the most important condition of their advance was undoubtedly the distinct apprehension of these two appropriate ideas: statical pressure and hydrostatical pressure, as included in the idea of fluidity. For the ideas being once clearly possessed, the experimental laws which they serve to express, that the whole pressure of a body downwards was always the same, and that water and the like were fluids according to the above idea of fluidity, were so obvious that there was no doubt nor difficulty about them. These two ideas lie at the root of all mechanical science, and the firm possession of them is, to this day, the first requisite for a student of the subject. After being clearly awakened in the mind of Archimedes, these ideas slept for many centuries, till they were again called up in Galileo, and more remarkably in Stevinus. This time, they were not destined again to slumber, and the results of their activity have been the formation of two sciences, which are as certain and severe in their demonstrations as geometry itself, and as copious and interesting in their conclusions, but which, besides this recommendation, possess one of a different order, that they exhibit the exact impress of the laws of the physical world, and unfold a portion of the rules according to which the phenomena of nature take place, and must take place, till nature herself shall alter. 100. Chapter 2. Earliest stages of optics. The progress made by the ancients in optics was nearly proportional to that which they made in statics. As they discovered the true grounds of the doctrine of equilibrium, without obtaining any sound principles concerning motion, so they discovered the law of the reflection of light, but had none but the most indistinct notions concerning refraction. The extent of the principles which they really possessed is easily stated. They knew that vision is performed by rays which proceed in straight lines, and that these rays are reflected by certain surfaces, mirrors, in such manner that the angles which they make with the surface on each side are equal. They drew various conclusions from these premises by the aid of geometry, as, for instance, the convergence of rays which fall on a concave speculum. It may be observed that the idea which is here introduced is that of visual rays, or lines along which vision is produced and light carried. This idea once clearly apprehended, it was not difficult to show that these lines are straight lines, both in the case of light and of sight. In the beginning of Euclid's Treatise on Optics, some of the arguments are mentioned by which this was established. We are told in the proem, in explaining what concerns the sight, he adduced certain arguments from which he inferred that all light is carried in straight lines. The greatest proof of this is shadows, and the bright spots which are produced by light coming through windows and cracks, and which could not be, except the rays of the sun were carried in straight lines. So in fires, the shadows are greater than the bodies if the fire be small, but less than the bodies if the fire be greater. A clear comprehension of the principle would lead to the perception of innumerable proofs of its truth on every side. The law of equality of angles of incidence and reflection was not quite so easy to verify, but the exact resemblance of the object and its image in a plane mirror, as the surface of still water, for instance, which is a consequence of this law, would afford convincing evidence of its truth in that case, and would be confirmed by the examination of other cases. 101. With these true principles was mixed much error and indistinctness, even in the best writers. Euclid and the Platonists maintain that vision is exercised by rays proceeding from the eye, not to it, so that when we see objects, we learn their form as a blind man would do, by feeling it out with his staff. This mistake, however, though Montucla speaks severely of it, was neither very discreditable nor very injurious, for the mathematical conclusions on each supposition are necessarily the same. Another curious and false assumption is that those visual rays are not close together, but separated by intervals, like the fingers when the hand is spread. The motive for this invention was the wish to account for the fact that in looking for a small object, as a needle, we often cannot see it when it is under our nose, which it was conceived would be impossible if the visual rays reached to all points of the surface before us. These errors would not have prevented the progress of the science, but the Aristotelian physics, as usual, contained speculations more essentially faulty. Aristotle's views led him to try to describe the kind of causation by which vision is produced, instead of the laws by which it is exercised, and the attempt consisted, as in other subjects, of indistinct principles and ill-combined facts. According to him, vision must be produced by a medium by something between the object and the eye, for if we press the object on the eye, we do not see it. This medium is light, or the transparent in action. Darkness occurs when the transparency is potential, not actual. Color is not the absolute visible, but something which is on the absolute visible. Color has the power of setting the transparent in action. It is not, however, all colors that are seen by means of light, but only the proper color of each object. For some things, as the heads and scales and eyes of fish, are seen in the dark, but they are not seen with their proper color. In all this there is no steady adherence either to one notion or to one class of facts. The distinction of power and act is introduced to modify the idea of transparency, according to the formula of the school. Then color is made to be something unknown in addition to visibility, and the distinction of proper and improper colors is assumed as sufficient to account for a phenomenon. Such classifications have in them nothing of which the mind can take steady hold, nor is it difficult to see that they do not come under those 102 conditions of successful physical speculation, which we have laid down. It is proper to notice more distinctly the nature of the geometrical propositions contained in Euclid's work. The Optica contains propositions concerning vision and shadows, derived from the principle that the rays of light are rectilinear. For instance, the proposition that the shadow is greater than the object, if the illuminating body be less, and vice versa. The Catoptrica contains propositions concerning the effects of reflection, derived from the principle that the angles of incidence and reflection are equal, as that in a convex mirror the object appears convex and smaller than the object. We see here an example of the promptitude of the Greeks in deduction. When they had once obtained a knowledge of a principle, they followed it to its mathematical consequences with great acuteness. The subject of concave mirrors is pursued further in Ptolemy's optics. The Greek writers also cultivated the subject of perspective speculatively, in mathematical treatises, as well as practically, in pictures. The whole of this theory is a consequence of the principle that vision takes place in straight lines drawn from the object to the eye. The ancients were in some measure acquainted with the refraction as well as the reflection of light, as I have shown in Book 9. Chapter 2 of the Philosophy. The current knowledge on this subject must have been very slight and confused, for it does not appear to have enabled them to account for one of the simplest results of refraction, the magnifying effect of convex transparent bodies. I have noticed in the passage just referred to Seneca's crude notions on this subject, and in like manner Ptolemy in his optics asserts that an object placed in water must always appear larger than when taken out. Aristotle uses the term letter 1F00 nu alpha kappa lambda alpha sigma iota sigma, meteoral. Roman 3. 2, but apparently in a very vague manner. It is not evident that he distinguished refraction from reflection. His commentators, however, do distinguish these as delta iota alpha kappa lambda alpha sigma iota sigma and letter 1F00 nu alpha kappa lambda alpha sigma iota sigma. See Olympiodorus in Schneider's Eclogi Physici, Volume IP. 397, and refraction had been the subject of special attention among the Greek mathematicians. Archimedes had noticed, as we learn from the same writer, that in certain cases, a ring which cannot be seen over the edge of the empty vessel in which it is placed becomes visible when the vessel is filled with water. The same fact is stated in the Optics of Euclid. We do not find this fact explained in that work as we now have it, but in Ptolemy's Optics, the fact is explained by a flexure of the visual ray. It is 103, noticed that this flexure is different at different angles from the perpendicular, and there is an elaborate collection of measures of the flexure at different angles, made by means of an instrument devised for the purpose. There is also a collection of similar measures of the refraction when the ray passes from air to glass and when it passes from glass to water. This part of Ptolemy's work is, I think, the oldest extant example of a collection of experimental measures in any other subject than astronomy, and in astronomy our measures are the result of observation rather than of experiment. As D'Alembert says, Astron. Inc., Volume Roman II. p. 427, on why voit des expériences de physique bien faites, si qui est sans exemple chez les anciens. Ptolemy's optical work was known only by Roger Bacon's references to it, Opus Majus, p. 286, and c. till 1816, but copies of Latin translations of it were known to exist in the Royal Library at Paris and in the Bodleian at Oxford. D'Alembert has given an account of the contents of the Paris copy in his Astron. Inc. Roman II, 414, and in the Connaissance des Temps for 1816. And Prof. Rigaud's account of the Oxford copy is given in the article Optics, in the Encyclopaedia Britannica. Ptolemy shows great sagacity in applying the notion of refraction to the explanation of the displacement of astronomical objects, which is produced by the atmosphere astronomical refraction, as it is commonly called. He represents the visual ray as refracted in passing from the ether, which is above the air, into the air. The air being bounded by a spherical surface which has for its center the center of all the elements, the center of the earth, and the refraction being a flexure towards the line drawn perpendicular to this surface. He thus constructs, says D'Alembert, the same figure on which Cassini afterwards founded the whole of his theory, and gives a theory more complete than that of any astronomer previous to him. Tycho, for instance, believed that astronomical refraction was caused only by the vapors of the atmosphere and did not exist above the altitude of 45 degrees. Cleombes, about the time of Augustus, had guessed at refraction as an explanation of an eclipse in which the sun and moon are both seen at the same time. Is it not possible, he says, that the ray which proceeds from the eye and traverses moist and cloudy air may bend downwards to the sun, even when he is below the horizon? And Sextus Empiricus, a century later, says, the air being dense, by the refraction of the visual ray, a constellation may be seen above the horizon when it is yet below the horizon. But from what follows, it 104 appears doubtful whether he clearly distinguished refraction and reflection. In order that we may not attach too much value to the vague expressions of Cleombes and Sextus Empiricus, we may remark that Cleombes conceives such an eclipse as he describes not to be possible, though he offers an explanation of it if it be. The fact must really occur whenever the moon is seen in the horizon in the middle of an eclipse. And that Sextus Empiricus gives his suggestion of the effect of refraction as an argument why the Chaldean astrology cannot be true, since the constellation which appears to be rising at the moment of a birth is not the one which is truly rising. The Chaldeans might have answered, says D'Alembert, that the star begins to shed its influence, not when it is really in the horizon, but when its light is seen. Ast. Inc., Volume IP, 231 and Volume Roman II. p. 548. It has been said that Vitalio, or Vitalo, whom we shall hereafter have to speak of in the history of optics, took his tables of refractions from Ptolemy. This is contrary to what D'Alembert states. He says that Vitalo may be accused of plagiarism from Alhazen, and that Alhazen did not borrow his tables from Ptolemy. Roger Bacon had said Opus Majus, p. 288, Ptolemaeus in libro de opticis, id est de aspectibus, su in perspectiva sua, qui prius quam Alhazen dedit hanc sententiam, quam a Ptolemeo acceptem Alhazen exposut. This refers only to the opinion that visual rays proceed from the eye, but this also is erroneous, for Alhazen maintains the contrary, visio fit radiis of visibili extrinsecus ad visum manentibus. Opt. Lib. I cap. 5. Vitalo says of his table of refractions, exceptis instrumentaliter, prout potuimus propinquius, angulis omnium refractionum, invenimus quad semper eidem sunt anguli refractionum, secundum hoc fecimus has tabulas. Having measured, by means of instruments, as exactly as we could, the whole range of the angles of refraction, we found that the refraction is always the same for the same angle, and hence we have constructed these tables. 105. Chapter 3. Earliest stages of harmonics. Among the ancients, the science of music was an application of arithmetic, as optics and mechanics were of geometry. The story which is told concerning the origin of their arithmetical music is the following, as it stands in the arithmetical treatise of Nicomachus. Pythagoras, walking one day, meditating on the means of measuring musical notes, happened to pass near a blacksmith's shop, and had his attention arrested by hearing the hammers, as they struck the anvil, produce the sounds which had a musical relation to each other. On listening further, he found that the intervals were a fourth, a fifth, and an octave, and on weighing the hammers, it appeared that the one which gave the octave was 1/2 the heaviest, the one which gave the fifth was 2/3, and the one which gave the fourth was 3/4. He returned home, reflected upon this phenomenon, made trials, and finally discovered that if he stretched musical strings of equal lengths, by weights which have the proportion of 1/2, 2/3, and 3/4, they produced intervals which were an octave, a fifth, and a fourth. This observation gave an arithmetical measure of the principal musical intervals and made music an arithmetical subject of speculation. This story, if not entirely a philosophical fable, is undoubtedly inaccurate, for the musical intervals thus spoken of would not be produced by striking with hammers of the weights there stated. But it is true that the notes of strings have a definite relation to the forces which stretch them, and this truth is still the groundwork of the theory of musical concords and discords. Nicomachus says that Pythagoras found the weights to be, as I have mentioned, in the proportion of 12, 6, 8, 9, and the intervals an octave corresponding to the proportion 12 to 6 or 2 to 1, a fifth corresponding to the proportion 12 to 8 or 3 to 2, and a fourth corresponding to the proportion 12 to 9 or 4 to 3. There is no doubt that this statement of the ancient writer is inexact as to the physical fact, for the rate of vibration of a string, on which its note depends, is 106, other things being equal, not as the weight, but as the square root of the weight. But he is right as to the essential point, that those ratios of 2 to 1, 3 to 2, and 4 to 3 are the characteristic ratios of the octave, fifth, and fourth. In order to produce these intervals, the appended weights must be not as 12, 9, 8, and 6, but as 12, 6 3/4, 5 1/3, and 3. The numerical relations of the other intervals of the musical scale, as well as of the octave, fifth, and fourth, were discovered by the Greeks. Thus they found that the proportion in a major third was 5 to 4, in a minor third, 6 to 5, in a major tone, 9 to 8, in a semitone or diesis, 16 to 15. They even went so far as to determine the comma, in which the interval of two notes is so small that they are in the proportion of 81 to 80. This is the interval between two notes, each of which may be called the 17th above the keynote, the one note being obtained by ascending a fifth 4 times over, the other being obtained by ascending through 2 octaves and a major third. The want of exact coincidence between these two notes is an inherent arithmetical imperfection in the musical scale, of which the consequences are very extensive. The numerical properties of the musical scale were worked out to a very great extent by the Greeks, and many of their treatises on this subject remain to us. The principal ones are the 7 authors published by Meibomius. These arithmetical elements of music are to the present day important and fundamental portions of the science of harmonics. It may at first appear that the truth, or even the possibility of this history, by referring the discovery to accident, disproves our doctrine, that this, like all other fundamental discoveries, required a distinct and well-pondered idea as its condition. In this, however, as in all cases of supposed accidental discoveries in science, it will be found that it was exactly the possession of such an idea which made the accident possible. Pythagoras, assuming the truth of the tradition, must have had an exact and ready apprehension of those relations of musical sounds, which are called respectively an octave, a fifth, and a fourth. If he had not been able to conceive distinctly this relation, and to apprehend it when heard, the sounds of the anvil would have struck his ears to no more purpose than they did those of the smiths themselves. He, 107, must have had, too, a ready familiarity with numerical ratios, and, moreover, that in which, probably, his superiority most consisted, a disposition to connect one notion with the other, the musical relation with the arithmetical, if it were found possible. When the connection was once suggested, it was easy to devise experiments by which it might be confirmed. The philosophers of the Pythagorean school, and in particular, Lassus of Hermione and Hippasus of Metapontum, made many such experiments upon strings, varying both their lengths and the weights which stretched them, and also upon vessels filled with water in a greater or less degree. And thus was established that connection of the idea with the fact, which this science, like all others, requires. I shall quit the physical sciences of ancient Greece, with the above brief statement of the discovery of the fundamental principles which they involved. Not only because such initial steps must always be the most important in the progress of science, but because, in reality, the Greeks made no advances beyond these. There took place among them no additional inductive processes, by which new facts were brought under the dominion of principles, or by which principles were presented in a more comprehensive shape than before. Their advance terminated in a single stride. Archimedes had stirred the intellectual world, but had not put it in progressive motion. The science of mechanics stopped where he left it. And though, in some objects, as in harmonics, much was written, the works thus produced consisted of deductions from the fundamental principles by means of arithmetical calculations, occasionally modified, indeed, by reference to the pleasures which music, as an art, affords, but not enriched by any new scientific truths. We should, however, quit the philosophy of the ancient Greeks without a due sense of the obligations which physical science in all succeeding ages owes to the acute and penetrating spirit in which their inquiries in that region of human knowledge were conducted, and to the large and lofty aspirations which were displayed, even in their failure, if we did not bear in mind both the multifarious and comprehensive character of their attempts, and some of the causes which limited their progress in positive science. They speculated and 108 theorized under a lively persuasion that a science of every part of nature was possible, and was a fit object for the exercise of man's best faculties, and they were speedily led to the conviction that such a science must clothe its conclusions in the language of mathematics. This conviction is eminently conspicuous in the writings of Plato. In the Republic, in the Eponomus, and above all in the Timaeus, this conviction makes him return again and again to a discussion of the laws which had been established or conjectured in his time, respecting harmonics and optics, such as we have seen, and still more, respecting astronomy, such as we shall see in the next book. Probably no succeeding step in the discovery of the laws of nature was of so much importance as the full adoption of this pervading conviction, that there must be mathematical laws of nature, and that it is the business of philosophy to discover these laws. This conviction continues, through all the succeeding ages of the history of science, to be the animating and supporting principle of scientific investigation and discovery. And especially in astronomy, many of the erroneous guesses which the Greeks made contain, if not the germ, at least the vivifying lifeblood of great truths reserved for future ages. Moreover, the Greeks not only sought such theories of special parts of nature, but a general theory of the universe. An essay at such a theory is the Timaeus of Plato, too wide and too ambitious an attempt to succeed at that time, or, indeed, on the scale on which he unfolds it, even in our time, but a vigorous and instructive example of the claim which man's intellect feels that it may make to understand the universal frame of things, and to render a reason for all that is presented to it by the outward senses. Further, we see in Plato that one of the grounds of the failure in this attempt was the assumption that the reason why everything is what it is and as it is must be that so it is best, according to some view of better or worse attainable by man. Socrates, in his dying conversation, as given in the Phaedo, declares this to have been what he sought in the philosophy of his time, and tells his friends that he turned away from the speculations of Anaxagoras because they did not give him such reasons for the constitution of the world. And Plato's Timaeus is, in reality, an attempt to supply this deficiency, and to present a theory of the universe in which everything is accounted for by such reasons. Though this is a failure, it is a noble as well as an instructive failure. 109, Book 3. History of Greek Astronomy. Tau omicron delta epsilon delta, letter 1 F72, mu eta delta epsilon iota sigma, pi omicron tau epsilon, phi, omicron beta eta theta letter 1 FC7, tau, letter 1 FF6, nu letter 1 F11 lambda lambda to nu omega nu. Letter 1 F61 sigma, omicron letter 1 F50, chi rho letter 1 F74, pi epsilon rho letter 1 F76 tau letter 1 F70, theta epsilon letter 1 FD6, alpha pi omicron tau letter 1 F72, pi rho alpha gamma mu alpha tau epsilon 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 sigma theta alpha iota, theta nu eta tau omicron letter 1 F7a, sigma letter 1 F44 nu tau alpha sigma, pi letter 1 FB6, nu delta epsilon. Tau omicron epsilon, delta iota alpha, nu omicron eta theta letter 1 FC6, nu alpha iota tau omicron letter 1 F50, nu alpha nu tau iota omicron nu letter 1 F61 sigma, omicron letter 1 F54 tau, epsilon letter 1 F04 phi rho omicron nu, letter 1 F14 sigma tau iota, pi omicron tau letter 1 F72 tau letter 1 F78, theta epsilon letter 1 FD6 omicron nu. Omicron letter 1 F54 tau, epsilon letter 1 F00, gamma nu omicron epsilon letter 1 FD6, pi omicron epsilon tau letter 1 F74, nu letter 1 F00 nu theta rho omega pi iota nu eta nu, phi epsilon sigma iota nu letter 1 F00 lambda lambda. Omicron letter 1 F36, delta epsilon nu letter 1 F45 tau iota. Delta iota delta alpha sigma cap omicron nu tau omicron sigma, alpha letter 1 F50, tau omicron letter 1 FE6. Xi epsilon nu alpha cap omicron lambda omicron epsilon theta eta sigma epsilon iota, kappa alpha letter 1 F76, mu alpha theta eta sigma epsilon tau alpha iota, tau letter 1 F70, delta iota delta alpha sigma cap omicron mu epsilon nu alpha. Plato, Eponymous, p. 988. Nor should any Greek have any misgiving of this kind, that it is not fitting for us to inquire narrowly into the operations of superior powers, such as those by which the motions of the heavenly bodies are produced. But, on the contrary, men should consider that the divine powers never act without purpose, and that they know the nature of man. They know that by their guidance and aid, man may follow and comprehend the lessons which are vouchsafed him on such subjects. 111. Introduction. The earliest and fundamental conceptions of men respecting the objects with which astronomy is concerned are formed by familiar processes of thought, without appearing to have in them anything technical or scientific. Days, years, months, the sky, the constellations, are notions which the most uncultured and incurious minds possess. Yet these are elements of the science of astronomy. The reasons why, in this case alone, of all the provinces of human knowledge, men were able, at an early and unenlightened period, to construct a science out of the obvious facts of observation, with the help of the common furniture of their minds, will be more apparent in the course of the philosophy of science. But I may here barely mention two of these reasons. They are first that the familiar act of thought, exercised for the common purposes of life, by which we give to an assemblage of our impressions such a unity as is implied in the above notions and terms, a month, a year, the sky, and the like, is in reality an inductive act and shares the nature of the processes by which all sciences are formed. And in the next place, that the ideas appropriate to the induction in this case are those which, even in the least cultivated minds, are very clear and definite. Namely, the ideas of space and figure, time and number, motion and recurrence. Hence, from their first origin, the modifications of those ideas assume a scientific form. We must now trace in detail the peculiar course which, in consequence of these causes, the knowledge of man respecting the heavenly bodies took, from the earliest period of his history. 112. Chapter 1. Earliest stages of astronomy. Sect 1. Formation of the notion of a year. The notion of a day is early and obviously impressed upon man in almost any condition in which we can imagine him. The recurrence of light and darkness, of comparative warmth and cold, of noise and silence, of the activity and repose of animals, the rising, mounting, descending, and setting of the sun, the varying colors of the clouds, generally, notwithstanding their variety, marked by a daily progression of appearances, the calls of the desire of food and of sleep in man himself, either exactly adjusted to the period of this change, or at least readily capable of being accommodated to it, the recurrence of these circumstances at intervals, equal, so far as our obvious judgment of the passage of time can decide, and these intervals so short that the repetition is noticed with no effort of attention or memory. This assemblage of suggestions makes the notion of a day necessarily occur to man, if we suppose him to have the conception of time and of recurrence. He naturally marks by a term such a portion of time and such a cycle of recurrence. He calls each portion of time, in which this series of appearances and occurrences come round, a day, and such a group of particulars are considered as appearing or happening in the same day. A year is a notion formed in the same manner, implying in the same way the notion of recurring facts, and also the faculty of arranging facts in time and of appreciating their recurrence. But the notion of a year, though undoubtedly very obvious, is, on many accounts, less so than that of a day. The repetition of similar circumstances at equal intervals is less manifest in this case, and the intervals being much longer, some exertion of memory becomes requisite in order that the recurrence may be perceived. A child might easily be persuaded that successive years were of unequal length, or, if the summer were cold and the spring and autumn warm, might be made to believe, if all who spoke in its hearing agreed to support the delusion, that 1 year was 2. It would be impossible to practice such a deception with regard to the day without the use of some artifice beyond mere words. 113. Still, the recurrence of the appearances which suggest the notion of a year is so obvious that we can hardly conceive man without it. But though, in all climes and times, there would be a recurrence, and at the same interval in all, the recurring appearances would be extremely different in different countries, and the contrasts and resemblances of the seasons would be widely varied. In some places, the winter utterly alters the face of the country, converting grassy hills, deep leafy woods of various hues of green, and running waters into snowy and icy wastes and bare snow-laden branches, while in others, the field retains its herbage, and the tree its leaves all the year, and the rains and the sunshine alone, or various agricultural employments quite different from ours, mark the passing seasons. Yet in all parts of the world, the yearly cycle of changes has been singled out from all others, and designated by a peculiar name. The inhabitant of the equatorial regions has the sun vertically over him at the end of every period of 6 months, and similar trains of celestial phenomena fill up each of these intervals, yet we do not find years of 6 months among such nations. The Arabs alone, who practice neither agriculture nor navigation, have a year depending upon the moon only, and borrow the word from other languages when they speak of the solar year. In general, nations have marked this portion of time by some word which has a reference to the returning circle of seasons and employments. Thus the Latin annus signified a ring, as we see in the derivative annulus. The Greek term letter 1F10, nu iota alpha upsilon, tau letter 1F78 sigma, implies something which returns into itself. And the word as it exists in Teutonic languages, of which our word year is an example, is said to have its origin in the word era, which means a ring in Swedish, and is perhaps connected with the Latin gyrus. Sect 2 Fixation of the civil year. The year, considered as a recurring cycle of seasons and of general appearances, must attract the notice of man as soon as his attention and memory suffice to bind together the parts of a succession of the length of several years. But to make the same term imply a certain fixed number of days, we must know how many days the cycle of the seasons occupies, a knowledge which requires faculties and artifices beyond what we have already mentioned. For instance, men cannot reckon as far as any number at all approaching the number of days in the year, without possessing a system of numeral terms and methods, 114, of practical numeration on which such a system of terms is always founded. The South American Indians, the Coosa Kaffirs and Hottentots, and the natives of New Holland, all of whom are said to be unable to reckon further than the fingers of their hands and feet, cannot, as we do, include in their notion of a year the fact of its consisting of 365 days. This fact is not likely to be known to any nation, except those which have advanced far beyond that which may be considered as the earliest scientific process which we can trace in the history of the human race, the formation of a method of designating the successive numbers to an indefinite extent by means of names, framed according to the decimal, quinary, or vigenary scale. But even if we suppose men to have the habit of recording the passage of each day, and of counting the score thus recorded, it would be by no means easy for them to determine the exact number of days in which the cycle of the seasons recurs. For the indefiniteness of the appearances which mark the same season of the year. And the changes to which they are subject, as the seasons are early or late, would leave much uncertainty respecting the duration of the year. They would not obtain any accuracy on this head till they had attended for a considerable time to the motions and places of the sun, circumstances which require more precision of notice than the general facts of the degrees of heat and light. The motions of the sun, the succession of the places of his rising and setting at different times of the year, the greatest heights which he reaches, the proportion of the length of day and night, would all exhibit several cycles. The turning back of the sun, when he had reached the greatest distance to the south or to the north, as shown either by his rising or by his height at noon, would perhaps be the most observable of such circumstances. Accordingly, the tau rho omicron pi alpha letter 1f76 letter 1f20 epsilon lambda iota omicron, the turnings of the sun, are used repeatedly by Hesiod as a mark from which he reckons the seasons of various employments. 50 days, he says, after the turning of the sun is a seasonable time for beginning a voyage. Note 4/3. Letter 1f24 mu alpha tau alpha, pi epsilon u tau eta cap omicron u tau alpha, mu epsilon tau letter 1f70, tau rho omicron pi letter 1f70, sigma letter 1f20 epsilon lambda iota omicron, letter 1f10 sigma, tau epsilon lambda omicron sigma, letter 1f10 lambda theta omicron u tau omicron sigma, theta epsilon rho epsilon omicron sigma, op. Et dies, 661. The phenomena would be different in different climates, but the recurrence would be common to all. Any one of these kinds of phenomena, noted with moderate care for a year, would show what was the number of days of which a year consisted. And if several years, 115, were included in the interval through which the scrutiny extended, the knowledge of the length of the year so acquired would be proportionally more exact. Besides those notices of the sun which offered exact indications of the seasons, other more indefinite natural occurrences were used, as the arrival of the swallow, chi epsilon lambda iota delta omega nu, and the kite, letter 1f30 kappa tau, ota nu. The birds, in Aristophanes' play of that name, mention it as one of their offices to mark the seasons. Hesiod similarly notices the cry of the crane as an indication of the departure of winter. Among the Greeks, the seasons were at first only summer and winter, theta epsilon rho omicron sigma and chi epsilon iota mu omega nu, the latter including all the rainy and cold portion of the year. The winter was then subdivided into the chi epsilon iota mu omega nu and letter 1f14 alpha rho, winter proper and spring, and the summer, less definitely, into theta epsilon rho omicron sigma and letter 1f40 pi omega rho alpha, summer and autumn. Tacitus says that the Germans knew neither the blessings nor the name of autumn, autumni parent nomen ac bona ignoranter. Yet harvest, Herbst, is certainly an old German word. In the same period in which the sun goes through his cycle of positions, the stars also go through a cycle of appearances belonging to them, and these appearances were perhaps employed at as early a period as those of the sun in determining the exact length of the year. Many of the groups of fixed stars are readily recognized as exhibiting always the same configuration, and particular bright stars are singled out as objects of attention. These are observed at particular seasons to appear in the west after sunset, but it is noted that when they do this, they are found nearer and nearer to the sun every successive evening, and at last disappear in his light. It is observed also that at a certain interval after this, they rise visibly before the dawn of day renders the stars invisible, and after they are seen to do this, they rise every day at a longer interval before the sun. The risings and settings of the stars under these circumstances, or under others which are easily recognized, were, in countries where the sky is usually clear, employed at an early period to mark the seasons of the year. Aeschylus makes Prometheus mention this among the benefits of which, 116, he, the teacher of arts to the earliest race of men, was the communicator. Note 7/3. Omicron letter 1f54, kappa letter 1f24 nu gamma alpha rho, alpha letter 1f50, tau omicron letter 1fd6, sigma omicron letter 1f54 tau, epsilon chi epsilon iota mu alpha tau omicron sigma, tau epsilon kappa mu alpha rho, omicron letter 1f54 tau, letter 1f00 nu theta epsilon mu omega delta omicron epsilon sigma, letter 1f26 rho omicron sigma. Omicron letter 1f54 delta, epsilon kappa alpha rho pi iota mu omicron epsilon, theta epsilon rho omicron epsilon sigma, beta epsilon beta alpha iota omicron u, letter 1 F00 lambda lambda, letter 1 F04 tau epsilon rho, gamma nu mega mu sigma, tau letter 1 F78, pi letter 1 FB6, nu letter 1 F14 pi rho alpha sigma sigma omicron u. Letter 1 F14 sigma tau epsilon del theta, sigma phi iota nu letter 1 F00, nu alpha tau, omicron lambda letter 1 F70, sigma letter 1 F10, gamma letter 1 F7c, letter 1 F04 sigma tau rho omega nu, letter 1 F14 delta epsilon iota psi alpha. Tau alpha sigma, tau epsilon delta epsilon sigma kappa rho iota tau omicron epsilon sigma, delta epsilon sigma epsilon iota sigma. Prom. V454. Thus, for instance, the rising of the Pleiades in the evening was a mark of the approach of winter. The rising of the waters of the Nile in Egypt coincided with the heliacal rising of Sirius, which star the Egyptians called Sothis. Even without any artificial measure of time or position, it was not difficult to carry observations of this kind to such a degree of accuracy as to learn from them the number of days which compose the year, and to fix the precise season from the appearance of the stars. Note 8/3, Idler Chronal. I-242 says that this rising of the Pleiades took place at a time of the year which corresponds to our 11th May and the setting to the 20th October, but this does not agree with the 40 days of their being concealed, which from the context must mean, I conceive, the interval between their setting and rising. Pliny, however, says, Virgiliarum exordu istas incipit, occasu hemes, semestri spatio intrasemeses vindemiasque et omnium maturitatem complexi. H. N. Roman 18. 69. The autumn of the Greeks, letter 1 F40 pi omega rho alpha, was earlier than our autumn. For Homer calls Sirius letter 1 F00, sigma tau, letter 1 F74, rho letter 1 F40 pi omega rho iota nu omicron sigma, which rose at the end of July. A knowledge concerning the stars appears to have been first cultivated with the last mentioned view, and makes its first appearance in literature with this for its object. Thus Hesiod directs the husbandman when to reap by the rising, and when to plow by the setting of the Pleiades. In like manner Sirius, Arcturus, the Hyades, and Orion are noticed. 117. Note 9/3. Pi lambda iota alpha delta omega nu, letter 1 F00 tau lambda alpha gamma epsilon nu epsilon omega nu, letter 1 F10 pi iota tau epsilon lambda lambda omicron mu epsilon nu alpha omega nu, letter 1 F04 o chi epsilon sigma theta, letter 1 F00, mu eta tau omicron letter 1 Fe6, letter 1 F00 rho omicron tau omicron iota omicron, delta letter 1 F72, delta epsilon sigma omicron mu epsilon nu alpha omega nu. Alpha letter 1 F35 del theta, tau omicron iota, nu epsilon kappa tau alpha sigma, tau epsilon kappa alpha letter 1 F76, letter 1 F24 mu alpha tau epsilon sigma sigma epsilon rho alpha kappa omicron nu tau alpha, kappa epsilon kappa rho epsilon phi alpha tau alpha iota. Alpha letter 1 F54 tau iota sigma delta letter 1 F72, pi epsilon rho iota pi lambda omicron mu epsilon nu omicron epsilon, letter 1 F10, nu iota alpha epsilon tau omicron letter 1 Fe6, phi alpha iota nu omicron nu tau alpha iota. Op. Et dies, L381. Note 11/3. Epsilon letter 1 F56 tau, letter 1 F02 nu delta, letter 1 F11 psi eta kappa omicron nu tau alpha, mu epsilon tau letter 1 F70, tau rho omicron pi letter 1 F70, sigma letter 1 F20 epsilon lambda iota omicron, chi epsilon iota mu epsilon rho iota. Letter 1 F10 kappa tau, epsilon lambda, epsilon sigma letter 1 FC3, zeta epsilon letter 1 F7a, sigma letter 1 F24 mu alpha tau alpha. Del theta letter 1 Fe5 alpha, tau omicron tau, letter 1 F00, sigma tau, letter 1 F74 rho letter 1 F00, rho kappa tau, omicron letter 1 Fe6, rho omicron sigma. Pi rho omicron lambda iota pi letter 1 F7c, nu letter 1 F31, epsilon rho letter 1 F78, nu letter 1 Fe5 omicron nu letter 1 F60, kappa epsilon alpha, nu omicron letter 1 FD6 omicron, pi rho letter 1 FF6, tau omicron, nu pi alpha mu phi alpha iota nu omega nu, letter 1 F10 pi iota tau epsilon lambda lambda epsilon tau alpha iota, letter 1 F00 kappa rho omicron kappa nu epsilon phi alpha iota omicron sig. Op. Et dies, L562. Epsilon letter 1 F56 tau, letter 1 F02 nu delta, letter 1 F60 rho iota omega nu, kappa alpha letter 1 F76, sigma epsilon iota rho ode omicron sigma, letter 1 F10 sigma, mu epsilon sigma omicron u, letter 1 F14 lambda theta letter 1 FC3, omicron letter 1 F50, rho alpha nu letter 1 F78 nu. Letter 1 F00, rho kappa tau, omicron letter 1 Fe6, rho omicron nu delta. Letter 1 F10, sigma letter 1 F76, delta letter 1 FC3, letter 1 Fe5 omicron delta alpha kappa tau epsilon lambda omicron sigma, letter 1 F20 letter 1 F7c sigma. Ib. 607. Note 12/3. Alpha letter 1 F50 tau letter 1 F70, rho letter 1 F10, pi letter 1 F74, nu delta letter 1 F74, pi lambda iota alpha delta epsilon sigma, letter 1 F51 alpha delta epsilon sigma, tau epsilon tau letter 1 F78, tau epsilon sigma theta epsilon nu omicron sigma, letter 1 F60 rho ode omega nu omicron sigma, delta epsilon nu omega sigma iota nu. Ib. 612. These methods were employed to a late period, because the Greek months, being lunar, did not correspond to the seasons. Tables of such motions were called pi alpha rho alpha pi eta gamma mu alpha tau alpha, Idler, Hist, Untersuchungen, p. 209. By such means it was determined that the year consisted at least nearly of 365 days. The Egyptians, as we learn from Herodotus, claimed the honor of this discovery. The priests informed him, he says, that the Egyptians were the first men who discovered the year, dividing it into 12 equal parts, and this they asserted that they discovered from the stars. Each of these parts or months consisted of 30 days, and they added 5 days more at the end of the year, and thus the circle of the seasons come round. It seems, also, that the Jews at an early period had a similar reckoning of time, for the deluge, which continued 150 days, Gen. Romans 7. 24, is stated to have lasted from the 17th day of the second month, Gen. Romans 7. 11, to the 17th day of the seventh month, Gen. Roman 8. 4, that is, 5 months of 30 days. A year thus settled as a period of a certain number of days is called a civil year. It is one of the earliest discoverable institutions of states possessing any germ of civilization, and one of the earliest portions of human systematic knowledge is the discovery of the length of the civil year, so that it should agree with the natural year or year of the seasons. Sect 3 Correction of the civil year, Julian calendar. In reality, by such a mode of reckoning as we have described, the circle of the seasons would not come round exactly. The real length of the year is very nearly 365 days and a quarter. If a year of 365 days were used, in 4 years the year would begin a day too soon, when considered with reference to the sun and stars, and in 60 years it would begin 15 days too soon, a quantity perceptible to the loosest degree of attention. The civil year would be found not to coincide with the year of the seasons. The beginning of the former would take place at different periods of the latter. It would wander into various seasons, instead of remaining fixed to the same season. The term year, and any number of years, would become ambiguous. Some correction, at least some comparison, would be requisite. We do not know by whom the insufficiency of the year of 365 days was first discovered. We find this knowledge diffused among all civilized nations, and various artifices used in making the correction. The method which we employ, and which consists in reckoning an 118 additional day at the end of February every 4th or leap year, is an example of the principle of intercalation, by which the correction was most commonly made. Methods of intercalation for the same purpose were found to exist in the New World. The Mexicans added 13 days at the end of every 52 years. The method of the Greeks was more complex by means of the octoeteris or cycle of 8 years, but it had the additional object of accommodating itself to the motions of the moon, and therefore must be treated of hereafter. The Egyptians, on the other hand, knowingly permitted their civil year to wander, at least so far as their religious observances were concerned. They do not wish, says Geminus, the same sacrifices of the gods to be made perpetually at the same time of the year, but that they should go through all the seasons, so that the same feast may happen in summer and winter, in spring and autumn. The period in which any festival would thus pass through all the seasons of the year is 1461 years. For 1460 years of 365, a quarter days are equal to 1,461 years of 365 days. This period of 1461 years is called the Sothic period, from Sothis, the name of the dog star, by which their fixed year was determined, and for the same reason it is called the canicular period. Note 14:3. Syncellus, Chronographia, p. 123, says that according to the legend, it was King Aseth who first added the 5 additional days to 360 for the year in the 18th century BC. Other nations did not regulate their civil year by intercalation at short intervals, but rectified it by a reform when this became necessary. The Persians are said to have added a month of 30 days every 120 years. The Roman calendar, at first very rude in its structure, was reformed by Numa and was directed to be kept in order by the perpetual interposition of the augurs. This, however, was, from various causes, not properly done, and the consequence was that the reckoning fell into utter disorder, in which state it was found by Julius Caesar when he became dictator. By the advice of Sosigenes, he adopted the mode of intercalation of 1 day in 4 years, which we still retain. And in order to correct the derangement which had already been produced, he added 90 days to a year of the usual length, which thus became what was called the year of confusion. The Julian calendar, thus reformed, came into use, January 1, BC 45. Sect 4 attempts at the fixation of the month. The circle of changes through which the moon passes in about 30 days is marked, in the earliest stages of language, by a word which implies the space of time which one such circle occupies. Just 119, as the circle of changes of the seasons is designated by the word year. The lunar changes are, indeed, more obvious to the sense, and strike a more careless person than the annual. The moon, when the sun is absent, is almost the sole natural object which attracts our notice, and we look at her with a far more tranquil and agreeable attention than we bestow on any other celestial object. Her changes of form and place are definite and striking to all eyes, they are uninterrupted, and the duration of their cycle is so short as to require no effort of memory to embrace it. Hence it appears to be more easy, and in earlier stages of civilization more common, to count time by moons than by years. The words by which this period of time is designated in various languages seem to refer us to the early history of language. Our word month is connected with the word moon, and a similar connection is noticeable in the other branches of the Teutonic. The Greek word mu letter 1f7 for new in like manner is related to muita nuita, which, though not the common word for the moon, is found in Homer with that signification. The Latin word mensis is probably connected with the same group. Note 17:3. Cicero derives this word from the verb to measure, quia mensa spatia conficiant, menses nominanter, and other etymologists with similar views connect the above-mentioned words with the Hebrew manna, to measure, with which the Arabic word almanac is connected. Such a derivation would have some analogy with that of annis, and c, noticed above. But if we are to attempt to ascend to the earliest condition of language, we must conceive it probable that men would have a name for a most conspicuous visible object, the moon, before they would have a verb denoting the very abstract and general notion, to measure. The month is not any exact number of days, being more than 29 and less than 30. The latter number was first tried, for men more readily select numbers possessing some distinction of regularity. It existed for a long period in many countries. A very few months of 30 days, however, would suffice to derange the agreement between the days of the months and the moon's appearance. A little further trial would show that months of 29 and 30 days alternately would preserve, for a considerable period, this agreement. The Greeks adopted this calendar, and, in consequence, considered the days of their month as representing the changes of the moon. The last day of the month was called letter 1f14 nu eta kappa alpha, letter 1f76 nu epsilon alpha, the old and new, as belonging to both the waning and the reappearing moon. And their 120 festivals and sacrifices, as determined by the calendar, were conceived to be necessarily connected with the same periods of the cycles of the sun and moon. The laws and the oracles, says Geminus, which directed that they should in sacrifices observe 3 things, months, days, years, were so understood. With this persuasion, a correct system of intercalation became a religious duty. Note 18:3, Aratus says of the moon, in a passage quoted by Geminus p. 33. Alpha letter 1 F34, epsilon iota delta. Letter 1 F04 lambda lambda omicron theta epsilon nu, letter 1 F04 lambda lambda alpha, pi alpha rho alpha kappa lambda iota nu omicron epsilon sigma alpha, mu epsilon tau omega, pi letter 1 F70, epsilon letter 1 F34, rho letter 1 FC3. Letter 1 F41 pi omicron sigma tau alpha iota eta, mu eta nu omicron sigma, pi epsilon rho iota tau epsilon lambda lambda epsilon tau alpha iota, letter 1 F21 letter 1 F7c sigma, as still her shifting visage-changing turns. By her we count the monthly round of morns. The above rule of alternate months of 29 and 30 days supposes the length of the months 29 days and a half, which is not exactly the length of a lunar month. Accordingly, the months and the moon were soon at variance. Aristophanes, in The Clouds, makes the moon complain of the disorder when the calendar was deranged. Omicron letter 1 F50, kappa letter 1 F04 gamma epsilon iota nu, tau letter 1 F70, sigma letter 1 F21 mu epsilon rho alpha sigma, omicron letter 1 F50, delta letter 1 F72, nu letter 1 F40, rho theta letter 1 FF6 sigma. Letter 1 F00 lambda lambda, letter 1 F00 nu omega, tau epsilon kappa alpha letter 1 F76 kappa alpha tau omega, kappa upsilon delta omicron iota delta omicron, pi letter 1 FB6, nu letter 1 F65 sigma tau, letter 1 F00, pi epsilon iota lambda epsilon letter 1 FD6, nu phi eta sigma letter 1 F76, nu alpha letter 1 F50, tau letter 1 FC7, tau omicron, letter 1 F50 sigma. Theta epsilon omicron letter 1 F7a, sigma letter 1 F11 kappa alpha sigma tau omicron tau epsilon, letter 1 F21 nu iota kappa, letter 1 F02 nu, psi epsilon upsilon sigma theta letter 1 FF6, sigma iota delta epsilon iota pi nu omicron upsilon, kappa letter 1 F00, pi iota omega, sigma iota nu omicron letter 1 F34, kappa alpha delta, epsilon tau, letter 1 FC6 sigma. Letter 1 F11 omicron rho tau letter 1 FC6, sigma mu letter 1 F74, tau upsilon chi omicron nu tau epsilon sigma, kappa alpha tau letter 1 F70, lambda omicron gamma omicron nu, tau letter 1 FF6, nu letter 1 F21, mu epsilon rho letter 1 FF6 nu nubs. 615-19. Chorus of Clouds. The moon by us to you her greeting sends, but bids us say that she's an ill-used moon, and takes it much amiss that you should still shuffle her days and turn them topsy-turvy, and that the gods, who know their feast days well, by your false count are sent home supperless, and scold and storm at her for your neglect. Note 19:3. This passage is supposed by the commentators to be intended as a satire upon those who had introduced the cycle of meton, spoken of insect. 5, which had been done at Athens a few years before The Clouds was acted. The correction of this inaccuracy, however, was not pursued separately, but was combined with another object, the securing a correspondence between the lunar and solar years, the main purpose of all early cycles. Sect 5 Invention of lunisolar years. There are 12 complete lunations in a year, which according to the above rule of 29.5 days to a lunation, would make 354 days, leaving 12 1/4 days of difference between such a lunar year and a solar year. It is said that, at an early period, this was attempted to be corrected by interpolating a month of 30 days every alternate year, and Herodotus relates a conversation of Solon, implying a still ruder mode of 121 intercalation. This can hardly be considered as an improvement in the Greek calendar already described. The first cycle which produced any near correspondence of the reckoning of the moon and the sun was the octoeteris, or period of 8 years. 8 years of 354 days, together with 3 months of 30 days each, making up in 99 lunations, 2922 days, which is exactly the amount of 8 years of 365 1/4 days each. Hence this period would answer its purpose, so far as the above lengths of the lunar and solar cycles are exact, and it might assume various forms according to the manner in which the 3 intercalary months were distributed. The customary method was to add a 13th month at the end of the 3rd, 5th, and 8th year of the cycle. This period is ascribed to various persons and times. Probably different persons proposed different forms of it. Dodwell places its introduction in the 59th Olympiad, or in the 6th century BC. But Idler thinks the astronomical knowledge of the Greeks of that age was too limited to allow of such a discovery. This cycle, however, was imperfect. The duration of 99 lunations is something more than 2922 days. It is more nearly 2,923 a half. Hence, in 16 years, there was a deficiency of 3 days with regard to the motions of the moon. This cycle of 16 years, hekidekateris, with 3 interpolated days at the end, was used, it is said, to bring the calculation right with regard to the moon. But in this way, the origin of the year was displaced with regard to the sun. After 10 revolutions of this cycle, or 160 years, the interpolated days would amount to 30, and hence the end of the lunar year would be a month in advance of the end of the solar. By terminating the lunar year at the end of the preceding month, the 2 years would again be brought into agreement, and we have thus a cycle of 160 years. This cycle of 160 years, however, was calculated from the cycle of 16 years, and it was probably never used in civil reckoning, which the others, or at least that of 8 years, appear to have been. The cycles of 16 and 160 years were corrections of the cycle of 8 years, and were readily suggested when the length of the solar and lunar periods became known with accuracy. But a much more exact cycle, independent of these, was discovered and introduced by Meton. 432 years BC, this cycle consisted of 19 years, and is so correct and convenient that it is in use among ourselves to this day. The time occupied by 19 years and by 235 lunations is very nearly the same. 122. The former time is less than 6940 days by 9.5 hours, the latter by 7.5 hours. Hence, if the 19 years be divided into 235 months, so as to agree with the changes of the moon, at the end of that period the same succession may begin again with great exactness. In order that 235 months, of 30 and 29 days, may make up 6940 days, we must have 125 of the former, which were called full months, and 110 of the latter, which were termed hollow. An artifice was used in order to distribute 110 hollow months among 6940 days. It will be found that there is a hollow month for each 63 days nearly. Hence, if we reckon 30 days to every month, but at every 63d day leap over a day in the reckoning, we shall, in the 19 years, omit 110 days, and this accordingly was done. Thus the 3d day of the 3d month, the 6th day of the 5th month, the 9th day of the 7th must be omitted so as to make these months hollow. Of the 19 years, 7 must consist of 13 months, and it does not appear to be known according to what order these 7 years were selected. Some say they were the 3d, 6th, 8th, 11th, 14th, 17th, and 19th. Others, the 3d, 5th, 8th, 11th, 13th, 16th, and 19th. The near coincidence of the solar and lunar periods in this cycle of 19 years was undoubtedly a considerable discovery at the time when it was first accomplished. It is not easy to trace the way in which such a discovery was made at that time, for we do not even know the manner in which men then recorded the agreement or difference between the calendar day and the celestial phenomenon which ought to correspond to it. It is most probable that the length of the month was obtained with some exactness by the observation of eclipses at considerable intervals of time from each other. For eclipses are very noticeable phenomena and must have been very soon observed to occur only at new and full moon. Note 23/3. Thucid, Roman 7. 50. Letter 1 F21 sigma epsilon lambda eta nu eta, letter 1 F10 kappa lambda epsilon iota pi epsilon iota, letter 1 F10 tau upsilon gamma chi alpha nu epsilon, gamma, letter 1 F70, rho pi alpha nu sigma epsilon lambda eta nu omicron sigma, omicron, letter 1 F56 sigma alpha. Roman 4. 52. Tau omicron letter 1 Fe6, letter 1 F21 lambda iota omicron upsilon, letter 1 F10 kappa lambda iota pi epsilon sigma, tau iota, letter 1 F10 gamma epsilon nu epsilon tau omicron, pi epsilon rho letter 1 F76, nu omicron upsilon mu eta nu iota alpha nu. Roman 2. 28. Nu omicron upsilon mu eta nu iota letter 1 FB3, kappa alpha tau letter 1 F70, sigma epsilon lambda nu eta nu, letter 1 F65 sigma pi epsilon rho, kappa alpha letter 1 F76, mu omicron nu delta omicron, kappa epsilon letter 1 FD6, epsilon letter 1 F36, nu alpha iota gamma nu epsilon sigma theta alpha iota, delta upsilon nu alpha tau, letter 1F78 nu letter 1F41. Letter 1F21 lambda iota omicron sigma, letter 1F10 psi epsilon lambda iota pi epsilon, mu epsilon tau, letter 1F70, mu epsilon sigma eta mu beta rho ode alpha nu, kappa alpha letter 1F76, pi alpha lambda iota nu, letter 1F00 nu, letter 1F10 pi lambda eta rho omega theta eta. Gamma epsilon nu omicron sigma, mu eta nu omicron, epsilon iota delta letter 1F74, sigma kappa alpha, letter 1F76, letter 1F00 sigma tau epsilon rho omega nu, tau iota nu letter 1F6, nu letter 1F10 kappa phi alpha nu epsilon nu tau omega nu. The exact length of a certain number of months being thus known, the discovery of a cycle which should regulate the calendar with sufficient accuracy would be a business of arithmetical skill, and would depend, in part, on the existing knowledge of arithmetical methods. But in making the discovery, a natural arithmetical sagacity was probably more efficacious than method. It is very possible that the cycle of Meton is correct more nearly than its author was aware, and 123 nearly than he could ascertain from any evidence and calculation known to him. It is so exact that it is still used in calculating the new moon for the time of Easter, and the golden number, which is spoken of in stating such rules, is the number of this cycle corresponding to the current year. Note 24/3. The same cycle of 19 years has been used by the Chinese for a very great length of time, their civil year consisting, like that of the Greeks, of months of 29 and 30 days. The Siamese also have this period. Astron, Lib. UK. Meton's cycle was corrected 100 years later, 330 BC, by Callippus, who discovered the error of it by observing an eclipse of the moon 6 years before the death of Alexander. In this corrected period, 4 cycles of 19 years were taken, and a day left out at the end of the 76 years, in order to make allowance for the hours by which, as already observed, 6940 days are greater than 19 years, and than 235 lunations. And this Calippic period is used in Ptolemy's Almagest, in stating observations of eclipses. The Metonic and Calippic periods undoubtedly imply a very considerable degree of accuracy in the knowledge which the astronomers, to whom they are due, had of the length of the month. And the first is a very happy invention for bringing the solar and lunar calendars into agreement. The Roman calendar, from which our own is derived, appears to have been a much less skillful contrivance than the Greek. Though scholars are not agreed on the subject of its construction, we can hardly doubt that months, in this as in other cases, were intended originally to have a reference to the moon. In whatever manner the solar and lunar motions were intended to be reconciled, the attempt seems altogether to have failed and to have been soon abandoned. The Roman months, both before and after the Julian correction, were portions of the year, having no reference to full and new moons. And we, having adopted this division of the year, have thus, in our common calendar, the traces of one of the early attempts of mankind to seize the law of the succession of celestial phenomena, in a case where the attempt was a complete failure. Considered as a part of the progress of our astronomical knowledge, improvements in the calendar do not offer many points to our observation, but they exhibit a few very important steps. Calendars which, belonging apparently to unscientific ages and nations, possess a great degree of accordance with the true motions of the sun and moon, like 124, the solar calendar of the Mexicans and the lunar calendar of the Greeks, contain the only record now extant of discoveries which must have required a great deal of observation, of thought, and probably of time. The later improvements in calendars, which take place when astronomical observation has been attentively pursued, are of little consequence to the history of science, for they are generally founded on astronomical determinations and are posterior in time and inferior in accuracy to the knowledge on which they depend. But cycles of correction, which are both short and close to exactness, like that of Meton, may perhaps be the original form of the knowledge which they imply, and certainly require both accurate facts and sagacious arithmetical reasonings. The discovery of such a cycle must always have the appearance of a happy guess, like other discoveries of laws of nature. Beyond this point, the interest of the study of calendars, as bearing on our subject, ceases. They may be considered as belonging rather to art than to science, rather as an application of a part of our knowledge to the uses of life than a means or an evidence of its extension. Sect 6. The constellations. Some tendency to consider the stars as formed into groups is inevitable when men begin to attend to them. But how men were led to the fanciful system of names of stars and of constellations, which we find to have prevailed in early times, it is very difficult to determine. Single stars and very close groups, as the Pleiades, were named in the time of Homer and Hesiod, and at a still earlier period, as we find in the Book of Job. Note 26/3, Job Roman 38, 31. Canst thou bind the sweet influences of Chima, the Pleiades, or loose the bands of Kessel, Orion? Canst thou bring forth Mazzaroth, Sirius in his season, or canst thou guide Ash or Aish, Arcturus with his sons? And Roman 9, which maketh Arcturus, Orion, and Pleiades, and the chambers of the south. Dupuy, Roman 6, 545, thinks that Aish was alpha letter 1F34 Xi, the goat and kids. See Hyde, Ulugbe. Two remarkable circumstances with respect to the constellations are first, that they appear in most cases to be arbitrary combinations, the artificial figures which are made to include the stars, not having any resemblance to their obvious configurations. And second, that these figures in different countries are so far similar as to imply some communication. The arbitrary nature of these figures shows that they 125 were rather the work of the imaginative and mythological tendencies of man than of mere convenience and love of arrangement. The constellations, says an astronomer of our own time, seem to have been almost purposely named and delineated to cause as much confusion and inconvenience as possible. Innumerable snakes twine through long and contorted areas of the heavens where no memory can follow them. Bears, lions, and fishes, large and small, northern and southern, confuse all nomenclature. A better system of constellations might have been a material help as an artificial memory. When men indicate the stars by figures, borrowed from obvious resemblances, they are led to combinations quite different from the received constellations. Thus the common people in our own country find a wain or wagon, or a plow, in a portion of the Great Bear. Note 28/3. So also the Greeks, Homer, Roman 18. 487, letter 1F040 kappa tau omicron u, letter 1F22 nu, kappa alpha letter 1F76, letter 1F04 mu alpha xi alpha nu, letter 1F10 pi iota kappa lambda to sigma iota nu, kappa alpha lambda epsilon omicron epsilon sigma iota nu. The northern bear which oft the wain they call. Letter 1F040 kappa tau omicron sigma was the traditional name. Letter 1F04 mu alpha xi alpha, that suggested by the form. The similarity of the constellations recognized in different countries is very remarkable. The Chaldean, the Egyptian, and the Grecian skies have a resemblance which cannot be overlooked. Some have conceived that this resemblance may be traced also in the Indian and Arabic constellations, at least in those of the zodiac. But while the figures are the same, the names and traditions connected with them are different, according to the histories and localities of each country. The river among the stars which the Greeks called the Eridanus, the Egyptians asserted to be the Nile. Some conceive that the signs of the zodiac, or path along which the sun and moon pass, had its divisions marked by signs which had a reference to the course of the seasons, to the motion of the sun, or the employments of the husbandman. If we take the position of the heavens, which, from the knowledge we now possess, we are sure they must have had 15,000 years ago, the significance of the signs of the zodiac, in which the sun was, as referred to the Egyptian year, becomes very marked, and has led some to suppose that the zodiac was invented at such a period. Others have rejected this as an improbably great antiquity, and have thought it more likely that the constellation assigned to each season was that which, at that season, rose at the beginning of the night. 126. Thus the balance, which is conceived to designate the equality of days and nights, was placed among the stars which rose in the evening when the spring began. This would fix the origin of these signs 2,500 years before our era. Note 29/3, Dupuy, Roman 6, 548. The Indian zodiac contains, in the place of our Capricorn, a ram and a fish, which proves the resemblance without chance of mistake. Bailey, IP 157. It is clear, as has already been said, that fancy, and probably superstition, had a share in forming the collection of constellations. It is certain that, at an early period, superstitious notions were associated with the stars. Astrology is of very high antiquity in the East. The stars were supposed to influence the character and destiny of man, and to be in some way connected with superior natures and powers. We may, I conceive, look upon the formation of the constellations, and the notions thus connected with them, as a very early attempt to find a meaning in the relations of the stars, and as an utter failure. The first effort to associate the appearances and motions of the skies by conceptions implying unity and connection was made in a wrong direction, as may very easily be supposed. Instead of considering the appearances only with reference to space, time, number in a manner purely rational, a number of other elements, imagination, tradition, hope, fear, awe of the supernatural, belief in destiny, were called into action. Man, still young as a philosopher at least, had yet to learn what notions his successful guesses on these subjects must involve, and what they must exclude. At that period, nothing could be more natural or excusable than this ignorance. But it is curious to see how long and how obstinately the belief lingered, if indeed it be yet extinct, that the motions of the stars and the dispositions and fortunes of men may come under some common conceptions and laws, by which a connection between the one and the other may be established. We cannot, therefore, agree with those who consider astrology in the early ages as only a degraded astronomy, the abuse of a more ancient science. It was the first step to astronomy by leading to habits and means of grouping phenomena, and after a while, by showing that pictorial and mythological relations among the stars had no very obvious value. From that time, the inductive process went on steadily in the true road, under the guidance of ideas of space, time, and number. Sect 7. The planets. While men were becoming familiar with the fixed stars, the planets must have attracted their notice. Venus, from her brightness, and 127 from her accompanying the sun at no great distance, and thus appearing as the morning and evening star, was very conspicuous. Pythagoras is said to have maintained that the evening and morning star are the same body, which certainly must have been one of the earliest discoveries on this subject. And indeed, we can hardly conceive men noticing the stars for a year or two without coming to this conclusion. Jupiter and Mars, sometimes still brighter than Venus, were also very noticeable. Saturn and Mercury were less so, but in fine climates they and their motion would soon be detected by persons observant of the heavens. To reduce to any rule the movements of these luminaries must have taken time and thought. Probably before this was done, certainly very early, these heavenly bodies were brought more peculiarly under those views which we have noticed as leading to astrology. At a time beyond the reach of certain history, the planets, along with the sun and moon, had been arranged in a certain recognized order by the Egyptians or some other ancient nation. Probably this arrangement had been made according to the slowness of their motions among the stars, for though the motion of each is very variable, the gradation of their velocities is, on the whole, very manifest. And the different rate of traveling of the different planets, and probably other circumstances of difference, led, in the ready fancy of early times, to the attribution of a peculiar character to each luminary. Thus Saturn was held to be of a cold and jellied nature. Jupiter, who, from his more rapid motion, was supposed to be lower in place, was temperate. Mars, fiery, and the like. Note 34/3, Achilles Tatius, Urinal, pp. 135-136, gives the Grecian and Egyptian names of the planets, Egyptian, Greek. Saturn nu epsilon sigma epsilon omega sigma, Capro omicron nu omicron epsilon, letter 1 F00. Sigma tau, letter 1 F74, rho phi alpha iota nu omega nu, Jupiter, letter 1 F40 sigma iota rho iota delta omicron sigma, delta, letter 1 FD6 omicron, sigma phi alpha epsilon theta omega nu, Mars, letter 1 F21, rho alpha kappa lambda, epsilon omicron, letter 1 Fe6, sigma, letter 1 F00 rho epsilon omicron sigma. Pi epsilon rho omicron epsilon iota sigma. Venus, letter 1 F00 phi rho omicron delta iota tau eta sigma. Letter 1 F11 omega sigma phi omicron rho omicron sigma. Mercury, letter 1 F00 pi omicron lambda lambda omega nu omicron sigma, letter 1 F11, rho mu omicron, letter 1 Fe6, sigma tau iota lambda beta omega nu. It is not necessary to dwell on the details of these speculations, but we may notice a very remarkable evidence of their antiquity and generality in the structure of one of the most familiar of our measures of time, the week. This distribution of time according to periods of 7 days comes down to us, as we learn from the Jewish scriptures, from the beginning of man's existence on the earth. The same usage is found over all the East. It existed among the Arabians, Assyrians, 128 Egyptians. The same week is found in India among the Brahmins. It has there, also, its days marked by those of the heavenly bodies, and it has been ascertained that the same day has, in that country, the name corresponding with its designation in other nations. The notion which led to the usual designations of the days of the week is not easily unraveled. The days each correspond to one of the heavenly bodies, which were, in the earliest systems of the world, conceived to be the following, enumerating them in the order of their remoteness from the earth: Saturn, Jupiter, Mars, the Sun, Venus, Mercury, the Moon. At a later period, the received systems placed the 7 luminaries in the 7 spheres. The knowledge which was implied in this view, and the time when it was obtained, we must consider hereafter. The order in which the names are assigned to the days of the week, beginning with Saturday, is Saturn, the Sun, the Moon, Mars, Mercury, Jupiter, Venus, and various accounts are given of the manner in which one of these orders is obtained from the other. All the methods proceeding upon certain arbitrary arithmetical processes connected in some way with astrological views. It is perhaps not worth our while here to examine further the steps of this process. It would be difficult to determine with certainty why the former order of the planets was adopted, and how and why the latter was deduced from it. But there is something very remarkable in the universality of the notions, apparently so fantastic, which have produced this result, and we may probably consider the week, with Laplace, as the most ancient monument of astronomical knowledge. This period has gone on without interruption or irregularity from the earliest recorded times to our own days, traversing the extent of ages and the revolutions of empires. The names of the ancient deities which were associated with the stars have been replaced by those of the objects of the worship of our Teutonic ancestors, according to their views of the correspondence of the two mythologies. And the Quakers, in rejecting these names of days, have cast aside the most ancient existing relic of astrological as well as idolatrous superstition. Sect 8. The circles of the sphere. The inventions hitherto noticed, though undoubtedly they were steps in astronomical knowledge, can hardly be considered as purely abstract and scientific speculations. For the exact reckoning of time is one of 129 the wants, even of the least civilized nations. But the distribution of the places and motions of the heavenly bodies by means of a celestial sphere with imaginary lines drawn upon it is a step in speculative astronomy, and was occasioned and rendered important by the scientific propensities of man. It is not easy to say with whom this notion originated. Some parts of it are obvious. The appearance of the sky naturally suggests the idea of a concave sphere with the stars fixed on its surface. Their motions during any one night, it would be readily seen, might be represented by supposing this sphere to turn round a pole or axis, for there is a conspicuous star in the heavens which apparently stands still, the pole star. All the others travel round this in circles and keep the same positions with respect to each other. This stationary star is every night the same, and in the same place. The other stars also have the same relative position, but their general position at the same time of night varies gradually from night to night, so as to go through its cycle of appearances once a year. All this would obviously agree with the supposition that the sky is a concave sphere or dome, that the stars have fixed places on this sphere, and that it revolves perpetually and uniformly about the pole or fixed point. But this supposition does not at all explain the way in which the appearances of different nights succeed each other. This, however, may be explained, it appears, by supposing the sun also to move among the stars on the surface of the concave sphere. The sun by his brightness makes the stars invisible which are on his side of the heavens. This we can easily believe. For the moon, when bright, also puts out all but the largest stars, and we see these stars appearing in the evening, each in its place, according to their degree of splendor, as fast as the declining light of day allows them to become visible. And as the sun brings day, and his absence night, if he move through the circuit of the stars in a year, we shall have, in the course of that time, every part of the starry sphere in succession presented to us as our nocturnal sky. This notion, that the sun moves round among the stars in a year, is the basis of astronomy, and a considerable part of the science is only the development and particularization of this general conception. It is not easy to ascertain either the exact method by which the path of the sun among the stars was determined, or the author and date of the discovery. That there is some difficulty in tracing the course of the sun among the stars will be clearly seen when it is considered that no 130 star can ever be seen at the same time with the sun. If the whole circuit of the sky be divided into 12 parts or signs, it is estimated by Autolycus, the oldest writer on these subjects whose works remain to us, that the stars which occupy one of these parts are absorbed by the solar rays so that they cannot be seen. Hence the stars which are seen nearest to the place of the setting and the rising sun in the evening and in the morning are distant from him by the half of a sign, the evening stars being to the west, and the morning stars to the east of him. If the observer had previously obtained a knowledge of the places of all the principal stars, he might in this way determine the position of the sun each night, and thus trace his path in a year. In this, or some such way, the sun's path was determined by the early astronomers of Egypt. Thales, who is mentioned as the father of Greek astronomy, probably learnt among the Egyptians the results of such speculations and introduced them into his own country. His knowledge, indeed, must have been a great deal more advanced than that which we are now describing, if it be true, as is asserted, that he predicted an eclipse. But his having done so is not very consistent with what we are told of the steps which his successors had still to make. The circle of the signs, in which the sun moves among the stars, is obliquely situated with regard to the circles in which the stars move about the poles. Pliny states that Anaximander, a scholar of Thales, was the first person who pointed out this obliquity, and thus, as he says, opened the gate of nature. Certainly, the person who first had a clear view of the nature of the sun's path in the celestial sphere made that step which led to all the rest. But it is difficult to conceive that the Egyptians and Chaldeans had not already advanced so far. Note 40/3, Plutarch de Plaque, Phil, Lib. Roman 2, Cap. Roman 12, says Pythagoras was the author of this discovery. The diurnal motion of the celestial sphere and the motion of the moon in the circle of the signs gave rise to a mathematical science, the doctrine of the sphere, which was one of the earliest branches of applied mathematics. A number of technical conceptions and terms were soon introduced. The sphere of the heavens was conceived to be complete, though we see but a part of it. It was supposed to turn about the visible pole and another pole opposite to this, and these poles were connected by an imaginary axis. The circle which divided the sphere exactly midway between these poles was called the equator, letter 1F30 sigma eta mu epsilon rho, ota nu omicron sigma. 131. The two circles parallel to this, which bounded the sun's path among the stars, were called tropics, tau rho omicron pi iota cap alpha iota, because the sun turns back again towards the equator when he reaches them. The stars which never set are bounded by a circle called the Arctic Circle, letter 1F04 rho kappa tau, ota cap omicron sigma, from letter 1F04 rho kappa tau omicron sigma, the Bear, the constellation to which some of the principal stars within that circle belong. A circle about the opposite pole is called Antarctic, and the stars which are within it can never rise to us. The sun's path or circle of the signs is called the zodiac, or circle of animals. The points where this circle meets the equator are the equinoctial points, the days and nights being equal when the sun is in them. The solstitial points are those where the sun's path touches the tropics. His motion to the south or to the north ceases when he is there, and he appears in that respect to stand still. The colures, kappa omicron lambda omicron upsilon rho omicron iota, mutilated, are circles which pass through the poles and through the equinoctial and solstitial points. They have their name because they are only visible in part, a portion of them being below the horizon. Note 41/3. The Arctic and Antarctic circles of modern astronomers are different from these. The horizon, letter 1F41 rho go to zeto meganu, is commonly understood as the boundary of the visible earth and heaven. In the doctrine of the sphere, this boundary is a great circle, that is, a circle of which the plane passes through the center of the sphere, and therefore, an entire hemisphere is always above the horizon. The term occurs for the first time in the work of Euclid, called Phenomena, phi alpha iota nu omicron mu epsilon nu alpha. We possess two treatises written by Autolycus, who lived about 300 BC, which trace deductively the results of the doctrine of the sphere. Supposing its diurnal motion to be uniform, in a work entitled Pi epsilon rho letter 1F76 kappa iota nu omicron epsilon mu eta sigma sigma phi alpha letter 1F d6 rho alpha sigma, on the moving sphere, he demonstrates various properties of the diurnal risings, settings, and motions of the stars. In another work, Pi epsilon rho letter 1F76 letter 1F10, pi iota tau omicron lambda letter 1FF6 nu kappa alpha letter 1F76 delta epsilon sigma epsilon omega nu, on risings and settings. Tacitly assuming the sun's motion in his circle to be uniform, he proves certain propositions with regard to those risings and settings of the stars, which take place at the same time when the sun rises and sets, or vice versa. And also their apparent risings and settings when they cease to be visible after sunset, or begin to be visible after sunrise. 132. Several of the propositions contained in the former of these treatises are still necessary to be understood, as fundamental parts of astronomy. Note 45-3. Acronycal rising and setting. Letter 1F00 kappa rho omicron u epsilon kappa iota omicron sigma, happening at the extremity of the night. The work of Euclid, just mentioned, is of the same kind. D'Alembert finds in it evidence that Euclid was merely a book astronomer who had never observed the heavens. We may here remark the first instance of that, which we shall find abundantly illustrated in every part of the history of science. That man is prone to become a deductive reasoner, that as soon as he obtains principles which can be traced to details by logical consequence, he sets about forming a body of science by making a system of such reasonings. Geometry has always been a favorite mode of exercising this propensity, and that science, along with trigonometry, plane and spherical, to which the early problems of astronomy gave rise, have, up to the present day, been a constant field for the exercise of mathematical ingenuity. A few simple astronomical truths being assumed as the basis of the reasoning. Sect 9. The globular form of the Earth. The establishment of the globular form of the Earth is an important step in astronomy, for it is the first of those convictions, directly opposed to the apparent evidence of the senses, which astronomy irresistibly proves. To make men believe that up and down are different directions in different places, that the sea which seems so level is in fact convex, that the earth, which appears to rest on a solid foundation, is in fact not supported at all, are great triumphs both of the power of discovering and the power of convincing. We may readily allow this, when we recollect how recently the doctrine of the antipodes, or the existence of inhabitants of the earth, who stand on the opposite side of it, with their feet turned towards ours, was considered both monstrous and heretical. Yet the different positions of the horizon at different places necessarily led the student of spherical astronomy towards this notion of the Earth as a round body. Anaximander is said by some to have held the Earth to be globular and to be detached or suspended. He is also stated to have constructed a sphere, on which were shown the extent of land and water. As, however, we do not know the arguments upon which he maintained the Earth's globular form, we cannot judge of the 133 value of his opinion. It may have been no better founded than a different opinion ascribed to him by Laertius, that the earth had the shape of a pillar. Probably, the authors of the doctrine of the globular form of the earth were led to it, as we have said, by observing the different height of the pole at different places. They would find that the space which they passed over from north to south on the earth was proportional to the change of place of the horizon in the celestial sphere. And as the horizon is, at every place, in the direction of the Earth's apparently level surface, this observation would naturally suggest to them the opinion that the Earth is placed within the celestial sphere, as a small globe in the middle of a much larger one. We find this doctrine so distinctly insisted on by Aristotle that we may almost look on him as the establisher of it. As to the figure of the Earth, it must necessarily be spherical. This he proves, first by the tendency of things, in all places, downwards. He then adds, and, moreover, from the phenomena according to the sense, for if it were not so, the eclipses of the moon would not have such sections as they have. For in the configurations in the course of a month, the deficient part takes all different shapes. It is straight, and concave, and convex, but in eclipses it always has the line of division convex. Wherefore, since the moon is eclipsed in consequence of the interposition of the Earth, the periphery of the Earth must be the cause of this by having a spherical form. And again, from the appearances of the stars, it is clear not only that the Earth is round, but that its size is not very large. For when we make a small removal to the south or the north, the circle of the horizon becomes palpably different, so that the stars overhead undergo a great change, and are not the same to those that travel to the north and to the south. For some stars are seen in Egypt or at Cyprus, but are not seen in the countries to the north of these, and the stars that in the north are visible while they make a complete circuit, there undergo a setting. So that from this it is manifest, not only that the form of the Earth is round, but also that it is a part of not a very large sphere. For otherwise the difference would not be so obvious to persons making so small a change of place. Wherefore we may judge that those persons who connect the region in the neighborhood of the Pillars of Hercules with that towards India, and who assert that in this way the sea is one, do not assert things very improbable. They confirm this conjecture moreover by the 134 elephants, which are said to be of the same species, gamma epsilon nu omicron sigma, towards each extreme, as if this circumstance was a consequence of the conjunction of the extremes. The mathematicians, who try to calculate the measure of the circumference, make it amount to 400,000 stadia, whence we collect that the Earth is not only spherical, but is not large compared with the magnitude of the other stars. Note 49/3, Arist, De Silo Lib Roman 2, Cap Roman 14, ed. Kassob, p. 290. When this notion was once suggested, it was defended and confirmed by such arguments as we find in later writers. For instance, that the tendency of all things was to fall to the place of heavy bodies, and that this place being the center of the Earth, the whole Earth had no such tendency, that the inequalities on the surface were so small as not materially to affect the shape of so vast a mass, that drops of water naturally form themselves into figures with a convex surface, that the end of the ocean would fall if it were not rounded off, that we see ships, when they go out to sea, disappearing downwards, which shows the surface to be convex. These are the arguments still employed in impressing the doctrines of astronomy upon the student of our own days, and thus we find that, even at the early period of which we are now speaking, truths had begun to accumulate which form a part of our present treasures. Sect 10. The phases of the moon. When men had formed a steady notion of the moon as a solid body, revolving about the Earth, they had only further to conceive it spherical, and to suppose the sun to be beyond the region of the moon, and they would find that they had obtained an explanation of the varying forms which the bright part of the moon assumes in the course of a month. For the convex side of the crescent moon, and her full edge when she is gibbous, are always turned towards the sun. And this explanation, once suggested, would be confirmed the more it was examined. For instance, if there be near us a spherical stone, on which the sun is shining, and if we place ourselves so that this stone and the moon are seen in the same direction, the moon appearing just over the top of the stone, we shall find that the visible part of the stone, which is then illuminated by the sun, is exactly similar in form to the moon, at whatever period of her changes she may be. The stone and the moon being in the same position with respect to us, and both being enlightened by the sun, the bright parts are the same in figure. 135. The only difference is that the dark part of the moon is usually not visible at all. This doctrine is ascribed to Anaximander. Aristotle was fully aware of it. It could not well escape the Chaldeans and Egyptians if they speculated at all about the causes of the appearances in the heavens. Sect 11. Eclipses. Eclipses of the sun and moon were from the earliest tunes regarded with a peculiar interest. The notions of superhuman influences and relations, which, as we have seen, were associated with the luminaries of the sky, made men look with alarm at any sudden and striking change in those objects. And as the constant and steady course of the celestial revolutions was contemplated with a feeling of admiration and awe, any marked interruption and deviation in this course was regarded with surprise and terror. This appears to be the case with all nations at an early stage of their civilization. This impression would cause eclipses to be noted and remembered, and accordingly, we find that the records of eclipses are the earliest astronomical information which we possess. When men had discovered some of the laws of succession of other astronomical phenomena, for instance, of the usual appearances of the moon and sun, it might then occur to them that these unusual appearances also might probably be governed by some rule. The search after this rule was successful at an early period. The Chaldeans were able to predict eclipses of the moon. This they did probably by means of their cycle of 223 months, or about 18 years, for at the end of this time, the eclipses of the moon begin to return at the same intervals and in the same order as at the beginning. Probably this was the first instance of the prediction of peculiar astronomical phenomena. The Chinese have, indeed, a legend in which it is related that a solar eclipse happened in the reign of Ti Chongkeng, above 2,000 years before Christ, and that the emperor was so much irritated against two great officers of state, who had neglected to predict this eclipse, that he put them to death. But this cannot be accepted as a real event, for, during the next 10 centuries, we find no single observation or fact connected with astronomy in the Chinese, 136 histories, and their astronomy has never advanced beyond a very rude and imperfect condition. Note 53/3. The eclipses of the sun are more difficult to calculate since they depend upon the place of the spectator on the earth. We can only conjecture the mode in which the Chaldeans discovered their period of 18 years, and we may make very different suppositions with regard to the degree of science by which they were led to it. We may suppose, with D'Alembert, that they carefully recorded the eclipses which happened, and then, by the inspection of their registers, discovered that those of the moon recurred after a certain period. Or we may suppose, with other authors, that they sedulously determined the motions of the moon, and having obtained these with considerable accuracy, sought and found a period which should include cycles of these motions. This latter mode of proceeding would imply a considerable degree of knowledge. It appears probable rather that such a period was discovered by noticing the recurrence of eclipses than by studying the moon's motions. After 6,585 1/3 days or 223 lunations, the same eclipses nearly will recur. It is not contested that the Chaldeans were acquainted with this period, which they called Saros, or that they calculated eclipses by means of it. Sect 12 sequel to the early stages of astronomy. Every stage of science has its train of practical applications and systematic inferences, arising both from the demands of convenience and curiosity, and from the pleasure which, as we have already said, ingenuous and active-minded men feel in exercising the process of deduction. The earliest condition of astronomy, in which it can be looked upon as a science, exhibits several examples of such applications and inferences, of which we may mention a few. Prediction of eclipses, the cycles which served to keep in order the calendar of the early nations of antiquity, in some instances enabled them also, as has just been stated, to predict eclipses, and this application of knowledge necessarily excited great notice. Cleombes, in the time of Augustus, says, "We never see an eclipse happen which has not been predicted by those who made use of the tables." Letter 1 F51, pi letter 1 F78, tau letter 1 FF6, nu kappa alpha, nu omicron, nu iota kappa letter 1 FF6 nu. Terrestrial zones, the globular form of the Earth being assented to, the doctrine of the sphere was applied to the Earth as well as the heavens, and the Earth's surface was divided by various imaginary 137 circles. Among the rest, the equator, the tropics, and circles at the same distance from the poles as the tropics are from the equator. One of the curious consequences of this division was the assumption that there must be some marked difference in the stripes or zones into which the Earth's surface was thus divided. In going to the south, Europeans found countries hotter and hotter, in going to the north, colder and colder, and it was supposed that the space between the tropical circles must be uninhabitable from heat, and that within the polar circles, again, uninhabitable from cold. This fancy was, as we now know, entirely unfounded. But the principle of the globular form of the Earth, when dealt with by means of spherical geometry, led to many true and important propositions concerning the lengths of days and nights at different places. These propositions still form a part of our elementary astronomy. Mnemonic. Another important result of the doctrine of the sphere was mnemonic, or dialing. Anaximenes is said by Pliny to have first taught this art in Greece, and both he and Anaximander are reported to have erected the first dial at Lacedaemon. Many of the ancient dials remain to us. Some of these are of complex forms and must have required great ingenuity and considerable geometrical knowledge in their construction. Measure of the sun's distance. The explanation of the phases of the moon led to no result so remarkable as the attempt of Aristarchus of Samos to obtain from this doctrine a measure of the distance of the sun as compared with that of the moon. If the moon was a perfectly smooth sphere, when she was exactly midway between the new and full in position, that is, a quadrant from the sun, she would be somewhat more than a half moon. And the place when she was dichotomized, that is, was an exact semicircle, the bright part being bounded by a straight line, would depend upon the sun's distance from the earth. Aristarchus endeavored to fix the exact place of this dichotomy, but the irregularity of the edge which bounds the bright part of the moon, and the difficulty of measuring with accuracy, by means then in use, either the precise time when the boundary was most nearly a straight line, or the exact distance of the moon from the sun at that time, rendered his conclusion false and valueless. He collected that the sun is at 18 times the distance of the moon from us. We now know that he is at 400 times the moon's distance. It would be easy to dwell longer on subjects of this kind, but we have already perhaps entered too much in detail. We have been 138 tempted to do this by the interest which the mathematical spirit of the Greeks gave to the earliest astronomical discoveries, when these were the subjects of their reasonings. But we must now proceed to contemplate them engaged in a worthier employment, namely, in adding to these discoveries. Chapter 2. Prelude to the Inductive Epoch of Hipparchus. Without pretending that we have exhausted the consequences of the elementary discoveries which we have enumerated, we now proceed to consider the nature and circumstances of the next great discovery, which makes an epoch in the history of astronomy. And this we shall find to be the theory of epicycles and eccentrics. Before, however, we relate the establishment of this theory, we must, according to the general plan we have marked out, notice some of the conjectures and attempts by which it was preceded, and the growing acquaintance with facts, which made the want of such an explanation felt. In the steps previously made in astronomical knowledge, no ingenuity had been required to devise the view which was adopted. The motions of the stars and sun were most naturally and almost irresistibly conceived as the results of motion in a revolving sphere. The indications of position which we obtain from different places on the Earth's surface, when clearly combined, obviously imply a globular shape. In these cases, the first conjectures, the supposition of the simplest form, of the most uniform motion, required no after-correction. But this manifest simplicity, this easy and obvious explanation, did not apply to the movement of all the heavenly bodies. The planets, the wandering stars, could not be so easily understood, the motion of each, as Cicero says, undergoing very remarkable changes in its course, going before and behind, quicker and slower, appearing in the evening but gradually lost there, and emerging again in the morning. A continued attention to these stars would, however, 139 detect a kind of intricate regularity in their motions, which might naturally be described as a dance. The Chaldeans are stated by Diodorus to have observed assiduously the risings and settings of the planets, from the top of the Temple of Belus. By doing this, they would find the times in which the forward and backward movements of Saturn, Jupiter, and Mars recur, and also the time in which they come round to the same part of the heavens. Venus and Mercury never recede far from the Sun, and the intervals which elapse while either of them leaves its greatest distance from the Sun and returns again to the greatest distance on the same side would easily be observed. Note 55/3, Sic, de nat, D-lib, Roman 2, p. 450. Equi Saturni stella dissiter, phi alpha iot nu omega nuca grisis nominator, quia terra abest plurimum, xxx sphere annis cursum suum conficit, in quo cursu multa mirabiliter efficiens, tum antecedendo, tum retardando, tum vespertinis temporibus delightsendo, tum matutinis si rersum appieriendo, nihil immudet sempiternis seculorum editibus, quin idem eistum temporibus efficit. And so of the other planets. Probably the manner in which the motions of the planets were originally reduced to rule was something like the following. In about 30 of our years, Saturn goes 29 times through his anomaly. That is, the succession of varied motions by which he sometimes goes forwards and sometimes backwards among the stars. During this time, he goes once round the heavens and returns nearly to the same place. This is the cycle of his apparent motions. Perhaps the Eastern nations contented themselves with thus referring these motions to cycles of time, so as to determine their recurrence. Something of this kind was done at an early period, as we have seen. But the Greeks soon attempted to frame to themselves a sensible image of the mechanism by which these complex motions were produced, nor did they find this difficult. Venus, for instance, who, upon the whole, moves from west to east among the stars, is seen, at certain intervals, to return or move retrograde a short way back from east to west, then to become for a short time stationary, then to turn again and resume her direct motion westward, and so on. Now this can be explained by supposing that she is placed in the rim of a wheel, which is turned edgeways to us, and of which the center turns round in the heavens from west to east, while the wheel, carrying the planet in its motion, moves round its own center. In this way, the motion of the wheel about its center would, in some situations, counterbalance the general motion of the center and make the planet retrograde, while, on the whole, the westerly motion would prevail. Just as if we suppose that a person, holding a lamp in his hand in the dark, and at a 140 distance, so that the lamp alone is visible, should run on turning himself round. We should see the light sometimes stationary, sometimes retrograde, but on the whole progressive. A mechanism of this kind was imagined for each of the planets, and the wheels of which we have spoken were in the end called epicycles. The application of such mechanism to the planets appears to have arisen in Greece about the time of Aristotle. In the works of Plato, we find a strong taste for this kind of mechanical speculation. In the 10th book of the Polity, we have the apologue of Alcinous the Pamphylian, who, being supposed to be killed in battle, revived when he was placed on the funeral pyre, and related what he had seen during his trance. Among other revelations, he beheld the machinery by which all the celestial bodies revolve. The axis of these revolutions is the adamantine distaff which Destiny holds between her knees. On this are fixed, by means of different sockets, flat rings, by which the planets are carried. The order and magnitude of these spindles are minutely detailed. Also, in the epilogue to the laws, Eponomus, he again describes the various movements of the sky, so as to show a distinct acquaintance with the general character of the planetary motions. And after speaking of the Egyptians and Syrians as the original cultivators of such knowledge, he adds some very remarkable exhortations to his countrymen to prosecute the subject. Whatever we Greeks, he says, receive from the barbarians, we improve and perfect. There is good hope and promise, therefore, that Greeks will carry this knowledge far beyond that which was introduced from abroad. To this task, however, he looks with a due appreciation of the qualities and preparation which it requires. An astronomer must be, he says, the wisest of men. His mind must be duly disciplined in youth. Especially is mathematical study necessary, both an acquaintance with the doctrine of number and also with that other branch of mathematics, which, closely connected as it is with the science of the heavens, we very absurdly call geometry, the measurement of the earth. Those anticipations were very remarkably verified in the subsequent career of the Greek astronomy. The theory, once suggested, probably made rapid progress. Simplicius relates that Eudoxus of Cnidus introduced the hypothesis of revolving circles or spheres. Callippus of Cyzicus, having visited 141 Polemarchus, an intimate friend of Eudoxus, they went together to Athens and communicated to Aristotle the invention of Eudoxus, and with his help improved and corrected it. Probably at first, this hypothesis was applied only to account for the general phenomena of the progressions, retrogradations, and stations of the planet. But it was soon found that the motions of the sun and moon, and the circular motions of the planets, which the hypothesis supposed, had other anomalies or irregularities, which made a further extension of the hypothesis necessary. The defect of uniformity in these motions of the sun and moon, though less apparent than in the planets, is easily detected as soon as men endeavor to obtain any accuracy in their observations. We have already stated, Chapter I, that the Chaldeans were in possession of a period of about 18 years, which they used in the calculation of eclipses, and which might have been discovered by close observation of the moon's motions, although it was probably rather hit upon by noting the recurrence of eclipses. The moon moves in a manner which is not reducible to regularity without considerable care and time. If we trace her path among the stars, we find that, like the path of the sun, it is oblique to the equator, but it does not, like that of the sun, pass over the same stars in successive revolutions. Thus its latitude, or distance from the equator, has a cycle different from its revolution among the stars, and its nodes, or the points where it cuts the equator, are perpetually changing their position. In addition to this, the moon's motion in her own path is not uniform. In the course of each lunation, she moves alternately slower and quicker, passing gradually through the intermediate degrees of velocity, and goes through the cycle of these changes in something less than a month. This is called a revolution of anomaly. When the moon has gone through a complete number of revolutions of anomaly, and has, in the same time, returned to the same position with regard to the sun, and also with regard to her nodes, her motions with respect to the sun will thenceforth be the same as at the first, and all the circumstances on which lunar eclipses depend being the same, the eclipses will occur in the same order. In 6,580, 5 days, there are 239 revolutions of anomaly, 241 revolutions with regard to one of the nodes, and, as we have said, 223 lunations, or revolutions, with regard to the sun. Hence, this period will bring about a succession of the same lunar eclipses. If the Chaldeans observed the moon's motion among the stars with any considerable accuracy, so as to detect this period by that means, 142, they could hardly avoid discovering the anomaly or unequal motion of the moon. For in every revolution, her daily progression in the heavens varies from about 22 to 26 times her own diameter. But there is not, in their knowledge of this period, any evidence that they had measured the amount of this variation, and D'Alembert is probably right in attributing all such observations to the Greeks. The sun's motion would also be seen to be irregular as soon as men had any exact mode of determining the lengths of the 4 seasons by means of the passage of the sun through the equinoctial and solstitial points. For spring, summer, autumn, and winter, which would each consist of an equal number of days if the motions were uniform, are, in fact, found to be unequal in length. It was not very difficult to see that the mechanism of epicycles might be applied so as to explain irregularities of this kind. A wheel traveling round the earth, while it revolved upon its center, might produce the effect of making the sun or moon fixed in its rim go sometimes faster and sometimes slower in appearance, just in the same way as the same suppositions would account for a planet going sometimes forwards and sometimes backwards. The epicycles of the sun and moon would, for this purpose, be less than those of the planets. Accordingly, it is probable that, at the time of Plato and Aristotle, philosophers were already endeavoring to apply the hypothesis to these cases, though it does not appear that anyone fully succeeded before Hipparchus. The problem which was thus present to the minds of astronomers, and which Plato is said to have proposed to them in a distinct form, was to reconcile the celestial phenomena by the combination of equable circular motions. That the circular motions should be equable as well as circular was a condition which, if it had been merely tried at first as the most simple and definite conjecture, would have deserved praise. But this condition, which is, in reality, inconsistent with nature, was, in the sequel, adhered to with a pertinacity which introduced endless complexity into the system. The history of this assumption is one of the most marked instances of that love of simplicity and symmetry which is the source of all general truths, though it so often produces and perpetuates error. At present, we can easily see how fancifully the notion of simplicity and perfection was interpreted in the arguments by which the opinion was defended, that the 143 real motions of the heavenly bodies must be circular and uniform. The Pythagoreans, as well as the Platonists, maintained this dogma. According to Geminus, they supposed the motions of the sun, and the moon and the 5 planets to be circular and equable. For they would not allow of such disorder among divine and eternal things, as that they should sometimes move quicker, and sometimes slower, and sometimes stand still. For no one would tolerate such anomaly in the movements, even of a man who was decent and orderly. The occasions of life, however, are often reasons for men going quicker or slower, but in the incorruptible nature of the stars, it is not possible that any cause can be alleged of quickness and slowness. Whereupon they propounded this question, how the phenomena might be represented by equable and circular motions. These conjectures and assumptions led naturally to the establishment of the various parts of the theory of epicycles. It is probable that this theory was adopted with respect to the planets at or before the time of Plato, and Aristotle gives us an account of the system thus devised. Eudoxus, he says, attributed 4 spheres to each planet. The first revolved with the fixed stars, and this produced the diurnal motion. The second gave the planet a motion along the ecliptic, the mean motion in longitude. The third had its axis perpendicular to the ecliptic, and this gave the inequality of each planetary motion, really arising from its special motion about the sun. The fourth produced the oblique motion transverse to this, the motion in latitude. He is also said to have attributed a motion in latitude and a corresponding sphere to the sun as well as to the moon, of which it is difficult to understand the meaning, if Aristotle has reported rightly of the theory. For it would be absurd to ascribe to Eudoxus a knowledge of the motions by which the sun deviates from the ecliptic. Callippus conceived that 2 additional spheres must be given to the sun and to the moon in order to explain the phenomena. Probably he was aware of the inequalities of the motions of these luminaries. He also proposed an additional sphere for each planet, to account, we may suppose, for the results of the eccentricity of the orbits. Note 62/3, Aristotle says, has its poles in the ecliptic, but this must be a mistake of his. He professes merely to receive these opinions from the mathematical astronomers. Letter 1 F10 kappa, tau, letter 1 FC6, sigma omicron, letter 1 F30, kappa epsilon iota omicron tau alpha tau, eta sigma phi iota lambda omicron phi o, alpha sigma, tau letter 1 FF6, mu alpha theta eta mu alpha tau iota kappa letter 1 FF6 nu. The hypothesis in this form does not appear to have been reduced to measure, and was, moreover, unnecessarily complex. The resolution, 144, of the oblique motion of the moon into 2 separate motions, by Eudoxus, was not the simplest way of conceiving it, and Callippus imagined the connection of these spheres in some way which made it necessary nearly to double their number. In this manner his system had no less than 55 spheres. Such was the progress which the idea of the hypothesis of epicycles had made in men's minds, previously to the establishment of the theory by Hipparchus. There had also been a preparation for this step, on the other side, by the collection of facts. We know that observations of the eclipses of the moon were made by the Chaldeans 367 BC at Babylon, and were known to the Greeks, for Hipparchus and Ptolemy founded their theory of the moon on these observations. Perhaps we cannot consider, as equally certain, the story that, at the time of Alexander's conquest, the Chaldeans possessed a series of observations, which went back 1903 years, and which Aristotle caused Callisthenes to bring to him in Greece. All the Greek observations which are of any value begin with the school of Alexandria. Aristillus and Timacharis appear, by the citations of Hipparchus, to have observed the places of stars and planets, and the times of the solstices, at various periods from BC 295 to BC 269 without their observations. Indeed, it would not have been easy for Hipparchus to establish either the theory of the sun or the precession of the equinoxes. In order that observations at distant intervals may be compared with each other, they must be referred to some common era. The Chaldeans dated by the era of Nabonassar, which commenced 749 BC. The Greek observations were referred to the Calippic periods of 76 years, of which the first began 331 BC. These are the dates used by Hipparchus and Ptolemy. 145. Chapter 3. Inductive Epoch of Hipparchus. Sect 1. Establishment of the theory of epicycles and eccentrics. Although, as we have already seen, at the time of Plato, the idea of epicycles had been suggested, and the problem of its general application proposed, and solutions of this problem offered by his followers. We still consider Hipparchus as the real discoverer and founder of that theory, inasmuch as he not only guessed that it might, but showed that it must, account for the phenomena, both as to their nature and as to their quantity. The assertion that he only discovers who proves is just, not only because, until a theory is proved to be the true one, it has no preeminence over the numerous other guesses among which it circulates, and above which the proof alone elevates it, but also because he who takes hold of the theory so as to apply calculation to it possesses it with a distinctness of conception which makes it peculiarly his. In order to establish the theory of epicycles, it was necessary to assign the magnitudes, distances, and positions of the circles or spheres in which the heavenly bodies were moved, in such a manner as to account for their apparently irregular motions. We may best understand what was the problem to be solved by calling to mind what we now know to be the real motions of the heavens. The true motion of the earth round the sun, and therefore the apparent annual motion of the sun, is performed not in a circle of which the earth is the center, but in an ellipse or oval, the earth being nearer to one end than to the other. And the motion is most rapid when the sun is at the nearer end of this oval. But instead of an oval, we may suppose the sun to move uniformly in a circle, the earth being now not in the center, but nearer to one side. For on this supposition, the sun will appear to move most quickly when he is nearest to the earth, or in his perigee, as that point is called. Such an orbit is called an eccentric, and the distance of the earth from the center of the circle is called the eccentricity. It may easily be shown by geometrical reasoning that the inequality of apparent motion so produced is exactly the same in 146 detail as the inequality which follows from the hypothesis of a small epicycle turning uniformly on its axis and carrying the sun in its circumference, while the center of this epicycle moves uniformly in a circle of which the earth is the center. This identity of the results of the hypothesis of the eccentric and the epicycle is proved by Ptolemy in the third book of the Almagest. The sun's eccentric when Hipparchus had clearly conceived these hypotheses as possible ways of accounting for the sun's motion. The task which he had to perform, in order to show that they deserved to be adopted, was to assign a place to the perigee, a magnitude to the eccentricity, and an epoch at which the sun was at the perigee, and to show that, in this way, he had produced a true representation of the motions of the sun. This, accordingly, he did, and having thus determined, with considerable exactness, both the law of the solar irregularities and the numbers on which their amount depends, he was able to assign the motions and places of the sun for any moment of future time with corresponding exactness. He was able, in short, to construct solar tables, by means of which the sun's place with respect to the stars could be correctly found at any time. These tables, as they are given by Ptolemy, give the anomaly or inequality of the sun's motion, and this they exhibit by means of the prostaphoresis, the quantity of which, at any distance of the sun from the apogee, it is requisite to add to or subtract from the arc, which he would have described if his motion had been equable. The reader might perhaps expect that the calculations which thus exhibited the motions of the sun for an indefinite future period must depend upon a considerable number of observations made at all seasons of the year. That, however, was not the case, and the genius of the discoverer appeared, as such genius usually does appear, in his perceiving how small a number of facts, rightly considered, were sufficient to form a foundation for the theory. The number of days contained in 2 seasons of the year sufficed for this purpose to Hipparchus. Having ascertained, says Ptolemy, that the time from the vernal equinox to the summer tropic is 94½ days, and the time from the summer tropic to the autumnal equinox 92½ days. From these phenomena alone, he demonstrates that the straight line joining the center of the sun's eccentric path with the center of the zodiac, the spectator's eye, is nearly the 24th part of the radius of the eccentric path, and that 147, its apogee precedes the summer solstice by 24½ degrees nearly, the zodiac containing 360. The exactness of the solar tables, or canon, which was founded on these data, was manifested, not only by the coincidence of the sun's calculated place with such observations as the Greek astronomers of this period were able to make, which were indeed very rude, but by its enabling them to calculate solar and lunar eclipses. Phenomena which are a very precise and severe trial of the accuracy of such tables, inasmuch as a very minute change in the apparent place of the sun or moon would completely alter the obvious features of the eclipse. Though the tables of this period were by no means perfect, they bore with tolerable credit this trying and perpetually recurring test, and thus proved the soundness of the theory on which the tables were calculated. The moon's motions have many irregularities, but when the hypothesis of an eccentric or an epicycle had sufficed in the case of the sun, it was natural to try to explain, in the same way, the motions of the moon. And it was shown by Hipparchus that such hypotheses would account for the more obvious anomalies. It is not very easy to describe the several ways in which these hypotheses were applied, for it is, in truth, very difficult to explain in words even the mere facts of the moon's motion. If she were to leave a visible bright line behind her in the heavens wherever she moved, the path thus exhibited would be of an extremely complex nature, the circle of each revolution slipping away from the preceding, and the traces of successive revolutions forming a sort of band of network running round the middle of the sky. In each revolution, the motion in longitude is affected by an anomaly of the same nature as the sun's anomaly already spoken of. But besides this, the path of the moon deviates from the ecliptic to the north and to the south of the ecliptic, and thus she has a motion in latitude. This motion in latitude would be sufficiently known if we knew the period of its restoration, that is, the time which the moon occupies in moving from any latitude till she is restored to the same latitude. As, for instance, from the ecliptic on one side of the heavens to the ecliptic on the same side of the heavens again. But it is found that the period of the restoration of the latitude is not the same as the period of the restoration of the longitude. That is, as the period of the moon's revolution among the 148 stars, and thus the moon describes a different path among the stars in every successive revolution, and her path, as well as her velocity, is constantly variable. Note 64/3. The reader will find an attempt to make the nature of this path generally intelligible in the companion to the British Almanac for 1814. Hipparchus, however, reduced the motions of the moon to rule and to tables, as he did those of the sun, and in the same manner. He determined, with much greater accuracy than any preceding astronomer, the mean or average equable motions of the moon in longitude and in latitude, and he then represented the anomaly of the motion in longitude by means of an eccentric, in the same manner as he had done for the sun. But here there occurred still an additional change, besides those of which we have spoken. The apogee of the sun was always in the same place in the heavens, or at least so nearly so, that Ptolemy could detect no error in the place assigned to it by Hipparchus 250 years before. But the apogee of the moon was found to have a motion among the stars. It had been observed before the time of Hipparchus that in 6,585 1/3 days, there are 241 revolutions of the moon with regard to the stars, but only 239 revolutions with regard to the anomaly. This difference could be suitably represented by supposing the eccentric, in which the moon moves, to have itself an angular motion, perpetually carrying its apogee in the same direction in which the moon travels. But this supposition being made, it was necessary to determine not only the eccentricity of the orbit and place of the apogee at a certain time, but also the rate of motion of the apogee itself, in order to form tables of the moon. This task, as we have said, Hipparchus executed, and in this instance, as in the problem of the reduction of the sun's motion to tables, the data which he found it necessary to employ were very few. He deduced all his conclusions from 6 eclipses of the moon. 3 of these, the records of which were brought from Babylon, where a register of such occurrences was kept, happened in the 366th and 367th years from the era of Nabonassar, and enabled Hipparchus to determine the eccentricity and apogee of the moon's orbit at that time. The 3 others were observed at Alexandria in the 547th year of Nabonassar, which gave him another position of the orbit at an interval of 180 years, and he thus became acquainted with the motion of the orbit itself, as well as its form. 149. Note 66/3. Ptolemy uses the hypothesis of an epicycle for the moon's first inequality, but Hipparchus employs an eccentric. The moon's motions are really affected by several other inequalities, a very considerable amount, besides those which were thus considered by Hipparchus. But the lunar paths, constructed on the above data, possessed a considerable degree of correctness, and especially when applied, as they were principally, to the calculation of eclipses. For the greatest of the additional irregularities which we have mentioned disappear at new and full moon, which are the only times when eclipses take place. The numerical explanation of the motions of the sun and moon, by means of the hypothesis of eccentrics and the consequent construction of tables, was one of the great achievements of Hipparchus. The general explanation of the motions of the planets, by means of the hypothesis of epicycles, was in circulation previously, as we have seen. But the special motions of the planets in their epicycles are, in reality, affected by anomalies of the same kind as those which render it necessary to introduce eccentrics in the cases of the sun and moon. Hipparchus determined, with great exactness, the mean motions of the planets, but he was not able, from want of data, to explain the planetary irregularities by means of eccentrics. The whole mass of good observations of the planets which he received from preceding ages did not contain so many, says Ptolemy, as those which he has transmitted to us of his own. Hence it was, he adds, that while he labored, in the most assiduous manner to represent the motions of the sun and moon by means of equable circular motions, with respect to the planets, so far as his works show, he did not even make the attempt, but merely put the extant observations in order, added to them himself more than the whole of what he received from preceding ages, and showed the insufficiency of the hypothesis current among astronomers to explain the phenomena. It appears that preceding mathematicians had already pretended to construct a perpetual canon, that is, tables which should give the places of the planets at any future time. But these being constructed without regard to the eccentricity of the orbits must have been very erroneous. Ptolemy declares, with great reason, that Hipparchus showed his usual love of truth, and his right sense of the responsibility of his task, in leaving this part of it to future ages. The theories of the sun and moon, which we have already described, constitute him a great astronomical discoverer and justify the reputation he has always, 150, possessed. There is, indeed, no philosopher who is so uniformly spoken of in terms of admiration. Ptolemy, to whom we owe our principal knowledge of him, perpetually couples with his name epithets of praise. He is not only an excellent and careful observer, but a most truth-loving and labor-loving person, one who had shown extraordinary sagacity and remarkable desire of truth in every part of science. Pliny, after mentioning him and Thales, breaks out into one of his passages of declamatory vehemence. Great men, elevated above the common standard of human nature, by discovering the laws which celestial occurrences obey, and by freeing the wretched mind of man from the fears which eclipses inspired hail to you and to your genius, interpreters of heaven, worthy recipients of the laws of the universe, authors of principles which connect gods and men. Modern writers have spoken of Hipparchus with the same admiration, and even the exact but severe historian of astronomy, D'Alembert, who bestows his praise so sparingly, and his sarcasm so generally, who says that it is unfortunate for the memory of Aristarchus that his work has come to us entire, and who cannot refer to the statement of an eclipse rightly predicted by Halican of Cyzicus without adding that if the story be true, Halican was more lucky than prudent, loses all his bitterness when he comes to Hipparchus. In Hipparchus, says he, we find one of the most extraordinary men of antiquity, the very greatest, in the sciences which require a combination of observation with geometry. D'Alembert adds, apparently in the wish to reconcile this eulogium with the depreciating manner in which he habitually speaks of all astronomers whose observations are inexact. A long period and the continued efforts of many industrious men are requisite to produce good instruments, but energy and assiduity depend on the man himself. Hipparchus was the author of other great discoveries and improvements in astronomy, besides the establishment of the doctrine of eccentrics and epicycles. But this, being the greatest advance in the theory of the celestial motions which was made by the ancients, must be the leading subject of our attention in the present work. our object being to discover in what the progress of real theoretical knowledge consists, and under what circumstances it has gone on. 151. Sect 2. Estimate of the value of the theory of eccentrics and epicycles. It may be useful here to explain the value of the theoretical step which Hipparchus thus made. And the more so, as there are, perhaps, opinions in popular circulation, which might lead men to think lightly of the merit of introducing or establishing the doctrine of epicycles. For, in the first place, this doctrine is now acknowledged to be false, and some of the greatest men in the more modern history of astronomy owe the brightest part of their fame to their having been instrumental in overturning this hypothesis. And moreover, in the next place, the theory is not only false, but extremely perplexed and entangled, so that it is usually looked upon as a mass of arbitrary and absurd complication. Most persons are familiar with passages in which it is thus spoken of. He his fabric of the heavens hath left to their disputes, perhaps to move his laughter at their quaint opinions wide. Hereafter, when they come to model heaven and calculate the stars, how will they wield the mighty frame? How build, unbuild, contrive, to save appearances? How gird the sphere with centric and eccentric scribbled o'er, cycle in epicycle, orb in orb? And every one will recollect the celebrated saying of Alfonso X, King of Castile, when this complex system was explained to him, that, if God had consulted him at the creation, the universe should have been on a better and simpler plan. In addition to this, the system is represented as involving an extravagant conception of the nature of the orbs which it introduces, that they are crystalline spheres, and that the vast spaces which intervene between the celestial luminaries are a solid mass, formed by the fitting together of many masses perpetually in motion, an imagination which is presumed to be incredible and monstrous. We must endeavor to correct or remove these prejudices, not only in order that we may do justice to the Hipparchian, or, as it is usually called, Ptolemaic system of astronomy, and to its founder, but for another reason much more important to the purpose of this work. 152, namely, that we may see how theories may be highly estimable, though they contain false representations of the real state of things, and may be extremely useful, though they involve unnecessary complexity. In the advance of knowledge, the value of the true part of a theory may much outweigh the accompanying error, and the use of a rule may be little impaired by its want of simplicity. The first steps of our progress do not lose their importance because they are not the last, and the outset of the journey may require no less vigor and activity than its close. That which is true in the Hipparchian theory, and which no succeeding discoveries have deprived of its value, is the resolution of the apparent motions of the heavenly bodies into an assemblage of circular motions. The test of the truth and reality of this resolution is that it leads to the construction of theoretical tables of the motions of the luminaries, by which their places are given at any time, agreeing nearly with their places as actually observed. The assumption that these circular motions, thus introduced, are all exactly uniform is the fundamental principle of the whole process. This assumption is, it may be said, false, and we have seen how fantastic some of the arguments were, which were originally urged in its favor. But some assumption is necessary, in order that the motions at different points of a revolution may be somehow connected, that is, in order that we may have any theory of the motions, and no assumption more simple than the one now mentioned can be selected. The merit of the theory is this, that obtaining the amount of the eccentricity, the place of the apogee, and, it may be, other elements from few observations it deduces from these, results agreeing with all observations, however numerous and distant. To express an inequality by means of an epicycle implies not only that there is an inequality, but further, that the inequality is at its greatest value at a certain known place, diminishes in proceeding from that place by a known law, continues its diminution for a known portion of the revolution of the luminary, then increases again, and so on. That is, the introduction of the epicycle represents the inequality of motion, as completely as it can be represented with respect to its quantity. We may further illustrate this by remarking that such a resolution of the unequal motions of the heavenly bodies into equable circular motions is, in fact, equivalent to the most recent and improved processes by which modern astronomers deal with such motions. Their universal method is to resolve all unequal motions into a series of 153 terms or expressions of partial motions. And these terms involve sines and cosines, that is, certain technical modes of measuring circular motion, the circular motion having some constant relation to the time. And thus the problem of the resolution of the celestial motions into equable circular ones, which was propounded above 2,000 years ago in the school of Plato, is still the great object of the study of modern astronomers, whether observers or calculators. That Hipparchus should have succeeded in the first great steps of this resolution for the sun and moon, and should have seen its applicability in other cases, is a circumstance which gives him one of the most distinguished places in the roll of great astronomers. As to the charges or the sneers against the complexity of his system, to which we have referred, it is easy to see that they are of no force. As a system of calculation, his is not only good, but, as we have just said, in many cases no better has yet been discovered. If, when the actual motions of the heavens are calculated in the best possible way, the process is complex and difficult, and if we are discontented at this, nature, and not the astronomer, must be the object of our displeasure. This plea of the astronomers must be allowed to be reasonable. We must not be repelled, says Ptolemy, by the complexity of the hypotheses, but explain the phenomena as well as we can. If the hypotheses satisfy each apparent inequality separately, the combination of them will represent the truth. And why should it appear wonderful to any that such a complexity should exist in the heavens, when we know nothing of their nature which entitles us to suppose that any inconsistency will result? But it may be said, we now know that the motions are more simple than they were thus represented, and that the theory of epicycles was false, as a conception of the real construction of the heavens. And to this we may reply that it does not appear that the best astronomers of antiquity conceived the cycles and epicycles to have a material existence. Though the dogmatic philosophers, as the Aristotelians, appear to have taught that the celestial spheres were real solid bodies, they are spoken of by Ptolemy as imaginary, and it is clear, from his proof of the identity of the results of the hypothesis of an eccentric and an epicycle, that they are intended to pass for no more than geometrical conceptions, in which view they are true representations of the apparent motions. 154. It is true that the real motions of the heavenly bodies are simpler than the apparent motions, and that we, who are in the habit of representing to our minds their real arrangement, become impatient of the seeming confusion and disorder of the ancient hypotheses. But this real arrangement never could have been detected by philosophers if the apparent motions had not been strictly examined and successfully analyzed. How far the connection between the facts and the true theory is from being obvious or easily traced, anyone may satisfy himself by endeavoring, from a general conception of the moon's real motions, to discover the rules which regulate the occurrences of eclipses, or even to explain to a learner of what nature the apparent motions of the moon among the stars will be. The unquestionable evidence of the merit and value of the theory of epicycles is to be found in this circumstance, that it served to embody all the most exact knowledge then extant, to direct astronomers to the proper methods of making it more exact and complete, to point out new objects of attention and research. And that, after doing this at first, it was also able to take in and preserve all the new results of the active and persevering labors of a long series of Greek, Latin, Arabian, and modern European astronomers, till a new theory arose which could discharge this office. It may, perhaps, surprise some readers to be told that the author of this next great step in astronomical theory, Copernicus, adopted the theory of epicycles. That is, he employed that which we have spoken of as its really valuable characteristic. We must confess, he says, that the celestial motions are circular or compounded of several circles, since their inequalities observe a fixed law and recur in value at certain intervals, which could not be, except that they were circular. For a circle alone can make that which has been recur again. In this sense, therefore, the Hipparchian theory was a real and indestructible truth, which was not rejected and replaced by different truths, but was adopted and incorporated into every succeeding astronomical theory, and which can never cease to be one of the most important and fundamental parts of our astronomical knowledge. A moment's reflection will show that, in the events just spoken of, the introduction and establishment of the theory of epicycles, those characteristics were strictly exemplified, which we have asserted to be the conditions of every real advance in progressive science, namely, 155, the application of distinct and appropriate ideas to a real series of facts. The distinctness of the geometrical conceptions, which enabled Hipparchus to assign the orbits of the sun and moon, requires no illustration, and we have just explained how these ideas combined into a connected whole the various motions and places of those luminaries. To make this step in astronomy required diligence and care, exerted in collecting observations, and mathematical clearness and steadiness of view, exercised in seeing and showing that the theory was a successful analysis of them. Sect 3. Discovery of the precession of the equinoxes. The same qualities which we trace in the researches of Hipparchus already examined diligence in collecting observations, and clearness of idea in representing them appear also in other discoveries of his, which we must not pass unnoticed. The precession of the equinoxes, in particular, is one of the most important of these discoveries. The circumstance here brought into notice was a change of longitude of the fixed stars. The longitudes of the heavenly bodies, being measured from the point where the sun's annual path cuts the equator, will change if that path changes. Whether this happens, however, is not very easy to decide, for the sun's path among the stars is made out not by merely looking at the heavens, but by a series of inferences from other observable facts. Hipparchus used for this purpose eclipses of the moon, for these, being exactly opposite to the sun, afford data in marking out his path. By comparing the eclipses of his own time with those observed at an earlier period by Timacharis, he found that the bright star, Spica Virginis, was 6 degrees behind the equinoctial point in his own time, and had been 8 degrees behind the same point at an earlier epoch. The suspicion was thus suggested that the longitudes of all the stars increase perpetually, but Hipparchus had too truly philosophical a spirit to take this for granted. He examined the places of Regulus and those of other stars as he had done those of Spica, and he found, in all these instances, a change of place which could be explained by a certain alteration of position in the circles to which the stars are referred, which alteration is described as the precession of the equinoxes. The distinctness with which Hipparchus conceived this change of relation of the heavens is manifested by the question which, as we are told by Ptolemy, he examined and decided, that this motion of the 156 heavens takes place about the poles of the ecliptic and not about those of the equator. The care with which he collected this motion from the stars themselves may be judged from this, that having made his first observations for this purpose on Spica and Regulus zodiacal stars, his first suspicion was that the stars of the zodiac alone changed their longitude, which suspicion he disproved by the examination of other stars. By his processes, the idea of the nature of the motion, and the evidence of its existence, the two conditions of a discovery were fully brought into view. The scale of the facts which Hipparchus was thus able to reduce to law may be in some measure judged of by recollecting that the precession, from his time to ours, has only carried the stars through one sign of the zodiac, and that, to complete one revolution of the sky by the motion thus discovered, would require a period of 25,000 years. Thus, this discovery connected the various aspects of the heavens at the most remote periods of human history, and accordingly, the novel and ingenious views which Newton published in his chronology are founded on this single astronomical fact, the precession of the equinoxes. The two discoveries which have been described, the mode of constructing solar and lunar tables, and the precession, were advances of the greatest importance in astronomy, not only in themselves, but in the new objects and undertakings which they suggested to astronomers. The one discovery detected a constant law and order in the midst of perpetual change and apparent disorder. The other disclosed mutation and movement perpetually operating where everything had been supposed fixed and stationary. Such discoveries were well adapted to call up many questionings in the minds of speculative men. For, after this, nothing could be supposed constant till it had been ascertained to be so by close examination, and no apparent complexity or confusion could justify the philosopher in turning away in despair from the task of simplification. To answer the inquiries thus suggested, new methods of observing the facts were requisite, more exact and uniform than those hitherto employed. Moreover, the discoveries which were made, and others which could not fail to follow in their train, led to many consequences, required to be reasoned upon, systematized, completed, enlarged. In short, the epoch of induction led, as we have stated, that such epochs must always lead to a period of development, of verification, application, and extension. 157. Chapter 4. Sequel to the inductive epoch of Hipparchus. Sect, researches which verified the theory. The discovery of the leading laws of the solar and lunar motions, and the detection of the precession may be considered as the great positive steps in the Hipparchian astronomy, the parent discoveries, from which many minor improvements proceeded. The task of pursuing the collateral and consequent researches, which now offered themselves of bringing the other parts of astronomy up to the level of its most improved portions, was prosecuted by a succession of zealous observers and calculators, first in the school of Alexandria, and afterwards in other parts of the world. We must notice the various labors of this series of astronomers, but we shall do so very briefly, for the ulterior development of doctrines once established is not so important an object of contemplation for our present purpose as the first conception and proof of those fundamental truths on which systematic doctrines are founded. Yet periods of verification, as well as epochs of induction, deserve to be attended to, and they can nowhere be studied with so much advantage as in the history of astronomy. In truth, however, Hipparchus did not leave to his successors the task of pursuing into detail those views of the heavens to which his discoveries led him. He examined with scrupulous care almost every part of the subject. We must briefly mention some of the principal points which were thus settled by him. The verification of the laws of the changes which he assigned to the skies implied that the condition of the heavens was constant, except so far as it was affected by those changes. Thus, the doctrine that the changes of position of the stars were rightly represented by the precession of the equinoxes supposed that the stars were fixed with regard to each other, and the doctrine that the unequal number of days, in certain subdivisions of months and years, was adequately explained by the theory of epicycles, assumed that years and days were always of constant lengths. But Hipparchus was not content with assuming these bases of his theory. He endeavored to prove them. 158. One fixity of the stars. The question necessarily arose after the discovery of the precession, even if such a question had never suggested itself before, whether the stars which were called fixed, and to which the motions of the other luminaries are referred, do really retain constantly the same relative position. In order to determine this fundamental question, Hipparchus undertook to construct a map of the heavens, for though the result of his survey was expressed in words, we may give this name to his catalogue of the positions of the most conspicuous stars. These positions are described by means of alineations. That is, 3 or more such stars are selected as can be touched by an apparent straight line drawn in the heavens. Thus Hipparchus observed that the southern claw of Cancer, the bright star in the same constellation which precedes the head of the Hydra, and the bright star Procyon were nearly in the same line. Ptolemy quotes this and many other of the configurations which Hipparchus had noted, in order to show that the positions of the stars had not changed in the intermediate time, a truth which the catalogue of Hipparchus thus gave astronomers the means of ascertaining. It contained 1080 stars. The construction of this catalogue of the stars by Hipparchus is an event of great celebrity in the history of astronomy. Pliny, who speaks of it with admiration as a wonderful and superhuman task, ossis rem etiam dio improbam, animarere posteris stellas, asserts the undertaking to have been suggested by a remarkable astronomical event, the appearance of a new star. Novum stellam et alium in evo seu genitam deprehendit, ejusque modu, quae fulsit, ad dubitationem est adductus an hoc sepius ferit, moverenturc et equas pudemus affixis. There is nothing inherently improbable in this tradition, but we may observe with D'Alembert that we are not informed whether this new star remained in the sky or soon disappeared again. Ptolemy makes no mention of the star or the story, and his catalogue contains no bright star which is not found in the catasterisms of Eratosthenes. These catasterisms were an enumeration of 475 of the principal stars, according to the constellations in which they are, and were published about 60 years before Hipparchus. Constant length of years Hipparchus also attempted to ascertain whether successive years are all of the same length. And though, with his scrupulous love of accuracy, he does not appear to have, 159, thought himself justified in asserting that the years were always exactly equal. He showed, both by observations of the time when the sun passed the equinoxes, and by eclipses, that the difference of successive years, if there were any difference, must be extremely slight. The observations of succeeding astronomers, and especially of Ptolemy, confirmed this opinion, and proved, with certainty, that there is no progressive increase or diminution in the duration of the year. Constant length of days. Equation of time. The equality of days was more difficult to ascertain than that of years, for the year is measured, as on a natural scale, by the number of days which it contains. But the day can be subdivided into hours only by artificial means, and the mechanical skill of the ancients did not enable them to attain any considerable accuracy in the measure of such portions of time, though clepsydras and similar instruments were used by astronomers. The equality of days could only be proved, therefore, by the consequences of such a supposition. And in this manner it appears to have been assumed, as the fact really is, that the apparent revolution of the stars is accurately uniform, never becoming either quicker or slower. It followed, as a consequence of this, that the solar days, or rather the nocthamers, compounded of a night and a day, would be unequal, in consequence of the sun's unequal motion, thus giving rise to what we now call the equation of time. The interval by which the time, as marked on a dial, is before or after the time, as indicated by the accurate timepieces which modern skill can produce. This inequality was fully taken account of by the ancient astronomers, and they thus, in fact, assumed the equality of the sidereal days. Sect. 2 researches which did not verify the theory. Some of the researches of Hipparchus and his followers fell upon the weak parts of his theory, and if the observations had been sufficiently exact, must have led to its being corrected or rejected. Among these, we may notice the researches which were made concerning the parallax of the heavenly bodies, that is, their apparent displacement by the alteration of position of the observer from one part of the Earth's surface to the other. This subject is treated of at length by Ptolemy, and there can be no doubt that it was well examined by Hipparchus, who invented a parallactic instrument for that purpose. The idea of parallax as a geometrical possibility was indeed too obvious to be overlooked by geometers at any time, and when the doctrine of the sphere was established, it must have appeared strange, 160, to the student, that every place on the Earth's surface might alike be considered as the center of the celestial motions. But if this was true with respect to the motions of the fixed stars, was it also true with regard to those of the sun and moon? The displacement of the sun by parallax is so small that the best observers among the ancients could never be sure of its existence, but with respect to the moon, the case is different. She may be displaced by this cause to the amount of twice her own breadth, a quantity easily noticed by the rudest process of instrumental observation. The law of the displacement thus produced is easily obtained by theory, the globular form of the Earth being supposed known. But the amount of the displacement depends upon the distance of the moon from the Earth and requires at least one good observation to determine it. Ptolemy has given a table of the effects of parallax, calculated according to the apparent altitude of the moon, assuming certain supposed distances. These distances, however, do not follow the real law of the moon's distances, in consequence of their being founded upon the hypothesis of the eccentric and epicycle. In fact, this hypothesis, though a very close representation of the truth, so far as the positions of the luminaries are concerned, fails altogether when we apply it to their distances. The radius of the epicycle, or the eccentricity of the eccentric, are determined so as to satisfy the observations of the apparent motions of the bodies. But inasmuch as the hypothetical motions are different altogether from the real motions, the hypothesis does not, at the same time, satisfy the observations of the distances of the bodies, if we are able to make any such observations. Parallax is one method by which the distances of the moon, at different times, may be compared. Her apparent diameters afford another method. Neither of these modes, however, is easily capable of such accuracy as to overturn at once the hypothesis of epicycles, and, accordingly, the hypothesis continued to be entertained in spite of such measures. the measures being, indeed, in some degree falsified in consequence of the reigning opinion. In fact, however, the imperfection of the methods of measuring parallax and magnitude, which were in use at this period, was such their results could not lead to any degree of conviction deserving to be set in opposition to a theory which was so satisfactory with regard to the more certain observations, namely, those of the motions. The eccentricity, or the radius of the epicycle, which would satisfy 161, the inequality of the motions of the moon, would, in fact, double the inequality of the distances. The eccentricity of the moon's orbit is determined by Ptolemy as 1/12 of the radius of the orbit, but its real amount is only half as great. This difference is a necessary consequence of the supposition of uniform circular motions, on which the epicyclic hypothesis proceeds. We see, therefore, that this part of the Hipparchian theory carries in itself the germ of its own destruction. As soon as the art of celestial measurement was so far perfected that astronomers could be sure of the apparent diameter of the moon within 1/30 or 1/40 of the whole, the inconsistency of the theory with itself would become manifest. We shall see, hereafter, the way in which this inconsistency operated. In reality, a very long period elapsed before the methods of observing were sufficiently good to bring it clearly into view. Sect 3 Methods of Observation of the Greek Astronomers. We must now say a word concerning the methods above spoken of. Since one of the most important tasks of verification is to ascertain with accuracy the magnitude of the quantities which enter, as elements into the theory which occupies men during the period, the improvement of instruments and the methods of observing and experimenting are principal features in such periods. We shall, therefore, mention some of the facts which bear upon this point. The estimation of distances among the stars by the eye is an extremely inexact process. In some of the ancient observations, however, this appears to have been the method employed, and stars are described as being a cubit or 2 cubits from other stars. We may form some notion of the scale of this kind of measurement from what Cleombes remarks that the sun appears to be about a foot broad, an opinion which he confutes at length. A method of determining the positions of the stars, susceptible of a little more exactness than the former, is the use of alineations, already noticed in speaking of Hipparchus's catalogue. Thus, a straight line passing through 2 stars of the Great Bear passes also through the pole star. This is, indeed, even now a method usually employed to enable us readily to fix on the pole star, and the 2 stars Beta and Alpha of Ursa Major are hence often called the pointers. 162. But nothing like accurate measurements of any portions of the sky were obtained, till astronomers adopted the method of making visual coincidences of the objects with the instruments, either by means of shadows or of sights. Probably the oldest and most obvious measurements of the positions of the heavenly bodies were those in which the elevation of the sun was determined, by comparing the length of the shadow of an upright staff or gnomon with the length of the staff itself. It appears from a memoir of Gödel, first printed in the Connaissance des Temps for 1809, that at the lower town of Loyang, now called Hananfu, Tichongkong found the length of the shadow of the gnomon, at the summer solstice, equal to 1 foot and a half, the gnomon itself being 8 feet in length. This was about 1100 BC. The Greeks, at an early period, used the same method. Strabo says that Byzantium and Marseille are on the same parallel of latitude, because the shadows at those places have the same proportion to the gnomon, according to the statement of Hipparchus, who follows Pythias. But the relations of position which astronomy considers are, for the most part, angular distances, and these are most simply expressed by the intercepted portion of a circumference described about the angular point. The use of the gnomon might lead to the determination of the angle by the graphical methods of geometry, but the numerical expression of the circumference required some progress in trigonometry. For instance, a table of the tangents of angles. Instruments were soon invented for measuring angles, by means of circles, which had a border or limb divided into equal parts. The whole circumference was divided into 360 degrees, perhaps because the circles, first so divided, were those which represented the sun's annual path. One such degree would be the sun's daily advance, more nearly than any other convenient aliquot part which could be taken. The position of the sun was determined by means of the shadow of one part of the instrument upon the other. The most ancient instrument of this kind appears to be the hemisphere of Berossus. A hollow hemisphere was placed with its rim horizontal, and a style was erected in such a manner that the extremity of the style was exactly at the center of the sphere. The shadow of this extremity, on the concave surface, had the same position with regard to the lowest point of the sphere, which the sun had with regard to the highest point of the heavens. 163. But this instrument was in fact used rather for dividing the day into portions of time than for determining position. Eratosthenes observed the amount of the obliquity of the sun's path to the equator. We are not informed what instruments he used for this purpose, but he is said to have obtained, from the munificence of Ptolemy Euergetes, 2 armils or instruments composed of circles, which were placed in the portico at Alexandria and long used for observations. If a circular rim or hoop were placed so as to coincide with the plane of the equator, the inner concave edge would be enlightened by the sun's rays which came under the front edge, when the sun was south of the equator, and by the rays which came over the front edge, when the sun was north of the equator. The moment of the transition would be the time of the equinox. Such an instrument appears to be referred to by Hipparchus, as quoted by Ptolemy. The circle of copper, which stands at Alexandria in what is called the square porch, appears to mark, as the day of the equinox, that on which the concave surface begins to be enlightened from the other side. Such an instrument was called an equinoctial armil. A solstitial armil is described by Ptolemy, consisting of 2 circular rims, one sliding round within the other, and the inner one furnished with 2 pegs standing out from its surface at right angles and diametrically opposite to each other. These circles being fixed in the plane of the meridian, and the inner one turned, till, at noon, the shadow of the peg in front falls upon the peg behind. The position of the sun at noon would be determined by the degrees on the outer circle. In calculation, the degree was conceived to be divided into 60 minutes, the minute into 60 seconds, and so on. But in practice, it was impossible to divide the limb of the instrument into parts so small. The armils of Alexandria were divided into no parts smaller than sixths of degrees or divisions of 10 minutes. The angles, observed by means of these divisions, were expressed as a fraction of the circumference. Thus, Eratosthenes stated the interval between the tropics to be 1183 of the circumference. Note 85/3. D'Alembert, AAI 87. It is probable that his observation gave him 47 2/3 degrees. The fraction 47 2/360 equals 143 1080 equals 11 13 1080 equals 11/83 plus 1/13, which is very nearly 1183. It was soon remarked that the whole circumference of the circle, 164, was not wanted for such observations. Ptolemy says that he found it more convenient to observe altitudes by means of a square flat piece of stone or wood, with a quadrant of a circle described on one of its flat faces, about a center near one of the angles. A peg was placed at the center, and one of the extreme radii of the quadrant being perpendicular to the horizon, the elevation of the sun above the horizon was determined by observing the point of the arc of the quadrant on which the shadow of the peg fell. As the necessity of accuracy in the observations was more and more felt, various adjustments of such instruments were practiced. The instruments were placed in the meridian by means of a meridian line drawn by astronomical methods on the floor on which they stood. The plane of the instrument was made vertical by means of a plumb line. The bounding radius, from which angles were measured, was also adjusted by the plumb line. Note 87/3. The curvature of the plane of the circle, by warping, was noticed. Tal, Roman 3, 2, p. 155, observes that his equatorial circle was illuminated on the hollow side twice in the same day. He did not know that this might arise from refraction. In this manner, the places of the sun and of the moon could be observed by means of the shadows which they cast. In order to observe the stars, the observer looked along the face of the circle of the armil, so as to see its 2 edges apparently brought together, and the star apparently touching them. Note 89/3, Tal Sint, I1. Letter 1 F65 sigma pi epsilon rho, cap epsilon cap omicron lambda lambda eta mu epsilon nu omicron sigma, letter 1 F00 mu phi omicron tau epsilon rho alpha iota sigma, alpha letter 1 F50, tau letter 1 FF6, nu tau alpha letter 1 f d6, sigma letter 1 f10 pi iota phi alpha nu epsilon iota alpha iota sigma, letter 1 f41 letter 1 f00, sigma tau letter 1 f74 rho letter 1 f10 nu tau letter 1 f7. Delta iota alpha letter 1 f50, tau letter 1 ff6, nu letter 1 f10, pi iota pi epsilon delta letter 1 ff3, delta iota omicron pi tau epsilon epsilon eta tau alpha iota. It was afterwards found important to ascertain the position of the sun with regard to the ecliptic, and, for this purpose, an instrument called an astrolabe was invented, of which we have a description in Ptolemy. This also consisted of circular rims, movable within one another or about poles, and contained circles which were to be brought into the position of the ecliptic, and of a plane passing through the sun and the poles of the ecliptic. The position of the moon with regard to the ecliptic, and its position in longitude with regard to the sun or a star, were thus determined. The astrolabe continued long in use, but not so long as the quadrant described by Ptolemy. This, in a larger form, is the mural quadrant, which has been used up to the most recent times. It may be considered surprising that Hipparchus, after having 165 observed, for some time, right ascensions and declinations, quitted equatorial armals for the astrolabe, which immediately refers the stars to the ecliptic. He probably did this because, after the discovery of precession, he found the latitudes of the stars constant and wanted to ascertain their motion in longitude. To the above instruments may be added the dioptra and the parallactic instrument of Hipparchus and Ptolemy. In the latter, the distance of a star from the zenith was observed by looking through two sights fixed in a rule, this being annexed to another rule, which was kept in a vertical position by a plumb line, and the angle between the two rules was measured. The following example of an observation, taken from Ptolemy, may serve to show the form in which the results of the instruments, just described, were usually stated. In the 2D year of Antoninus, the 9th day of Pharmouthi, the sun being near setting, the last division of Taurus being on the meridian, that is, 5½ equinoctial hours afternoon, the moon was in 3 degrees of Pisces, by her distance from the sun, which was 92 degrees 8 minutes. And half an hour after, the sun being set, and the quarter of Gemini on the meridian, Regulus, appeared, by the other circle of the astrolabe, 57½ degrees more forwards than the moon in longitude. From these data, the longitude of Regulus is calculated. From what has been said respecting the observations of the Alexandrian astronomers, it will have been seen that their instrumental observations could not be depended on for any close accuracy. This defect, after the general reception of the Hipparchian theory, operated very unfavorably on the progress of the science. If they could have traced the moon's place distinctly from day to day, they must soon have discovered all the inequalities which were known to Tycho Brahe. And if they could have measured her parallax or her diameter with any considerable accuracy, they must have obtained a confutation of the epicycloidal form of her orbit. By the badness of their observations, and the imperfect agreement of these with calculation, they not only were prevented making such steps, but were led to receive the theory with a servile assent and an indistinct apprehension, instead of that rational conviction and intuitive clearness which would have given a progressive impulse to their knowledge. 166. Sect 4 period from Hipparchus to Ptolemy. We have now to speak of the cultivators of astronomy from the time of Hipparchus to that of Ptolemy, the next great name which occurs in the history of this science, though even he holds place only among those who verified, developed, and extended the theory of Hipparchus. The astronomers who lived in the intermediate time, indeed, did little even in this way, though it might have been supposed that their studies were carried on under considerable advantages, inasmuch as they all enjoyed the liberal patronage of the kings of Egypt. The divine school of Alexandria, as it is called by Synesius in the 4th century, appears to have produced few persons capable of carrying forwards, or even of verifying, the labors of its great astronomical teacher. The mathematicians of the school wrote much, and apparently they observed sometimes, but their observations are of little value, and their books are expositions of the theory and its geometrical consequences without any attempt to compare it with observation. For instance, it does not appear that anyone verified the remarkable discovery of the precession till the time of Ptolemy, 250 years after. Nor does the statement of this motion of the heavens appear in the treatises of the intermediate writers. Nor does Ptolemy quote a single observation of any person made in this long interval of time, while his references to those of Hipparchus are perpetual, and to those of Aristillus and Timacharis, and of others, as Canon, who preceded Hipparchus, are not unfrequent. This Alexandrian period, so inactive and barren in the history of science, was prosperous, civilized, and literary, and many of the works which belong to it are come down to us, though those of Hipparchus are lost. We have the Uranologion of Geminus, a systematic treatise on astronomy, expounding correctly the Hipparchian theories and their consequences, and containing a good account of the use of the various cycles, which ended in the adoption of the Callippic period. We have likewise the circular theory of the celestial bodies of Cleomes, of which the principal part is a development of the doctrine of the sphere, including the consequences of the globular form of the earth. We have also another work on spherics by Theodosius of Bithynia, which contains some of the most important propositions of the subject, and has been used as a book of 167 instruction even in modern times. Another writer on the same subject is Menelaus, who lived somewhat later, and whose 3 books on spherics still remain. One of the most important kinds of deduction from a geometrical theory, such as that of the doctrine of the sphere, or that of epicycles, is the calculation of its numerical results in particular cases. With regard to the latter theory, this was done in the construction of solar and lunar tables, as we have already seen, and this process required the formation of a trigonometry or system of rules for calculating the relations between the sides and angles of triangles. Such a science had been formed by Hipparchus, who appears to be the author of every great step in ancient astronomy. He wrote a work in 12 books on the construction of the tables of chords of arcs, such a table being the means by which the Greeks solved their triangles. The doctrine of the sphere required, in like manner, a spherical trigonometry in order to enable mathematicians to calculate its results. And this branch of science also appears to have been formed by Hipparchus, who gives results that imply the possession of such a method. Hypsicles, who was a contemporary of Ptolemy, also made some attempts at the solution of such problems. But it is extraordinary that the writers whom we have mentioned as coming after Hipparchus, namely Theodosius, Cleomes, and Menelaus, do not even mention the calculation of triangles, either plane or spherical, though the latter writer is said to have written on the table of chords, a work which is now lost. We shall see, hereafter, how prevalent a disposition in literary ages is that which induces authors to become commentators. This tendency showed itself at an early period in the school of Alexandria. Aratus, who lived 270 BC at the court of Antigonus, king of Macedonia, described the celestial constellations in 2 poems, entitled Phenomena and Prognostics. These poems were little more than a versification of the treatise of Eudoxus on the acronycal and heliacal risings and settings of the stars. The work was the subject of a comment by Hipparchus, who perhaps found this the easiest way of giving connection and circulation to his knowledge. 3 Latin translations of this poem gave the Romans the means of becoming acquainted with it. The first is by Cicero, of which we have numerous fragments, 168, extant. Germanicus Caesar, one of the sons-in-law of Augustus, also translated the poem, and this translation remains almost entire. Finally, we have a complete translation by Avianus. The Astronomica of Manilius, the Poeticon Astronomicon of Hyginus, both belonging to the time of Augustus, are, like the work of Aratus, poems which combine mythological ornament with elementary astronomical exposition, but have no value in the history of science. We may pass nearly the same judgment upon the explanations and declamations of Cicero, Seneca, and Pliny, for they do not apprise us of any additions to astronomical knowledge, and they do not always indicate a very clear apprehension of the doctrines which the writers adopt. Note 102/3. 2 copies of this translation, illustrated by drawings of different ages, one set Roman and the other Saxon, according to Mr. Otley, are described in the Archaeologia, volume Roman 18. Perhaps the most remarkable feature in the 2 last-named writers is the declamatory expression of their admiration for the discoverers of physical knowledge, and in one of them, Seneca, the persuasion of a boundless progress in science to which man was destined. Though this belief was no more than a vague and arbitrary conjecture, it suggested other conjectures in detail, some of which, having been verified, have attracted much notice. For instance, in speaking of comets, Seneca says, "The time will come when those things which are now hidden shall be brought to light by time and persevering diligence. Our posterity will wonder that we should be ignorant of what is so obvious. The motions of the planets," he adds, "complex and seemingly confused, have been reduced to rule, and someone will come hereafter who will reveal to us the paths of comets." Such convictions and conjectures are not to be admired for their wisdom, for Seneca was led rather by enthusiasm than by any solid reasons to entertain this opinion. Nor, again, are they to be considered as merely lucky guesses, implying no merit. They are remarkable as showing how the persuasion of the universality of law and the belief of the probability of its discovery by man grow up in men's minds when speculative knowledge becomes a prominent object of attention. An important practical application of astronomical knowledge was made by Julius Caesar in his correction of the calendar, which we have already noticed, and this was strictly due to the Alexandrian school. Sosigenes, an astronomer belonging to that school, came from Egypt to Rome for the purpose. 169. Sect 5 Measures of the Earth. There were, as we have said, few attempts made, at the period of which we are speaking, to improve the accuracy of any of the determinations of the early Alexandrian astronomers. One question naturally excited much attention at all times: the magnitude of the Earth, its figure being universally acknowledged to be a globe. The Chaldeans, at an earlier period, had asserted that a man walking without stopping might go round the circuit of the Earth in a year, but this might be a mere fancy or a mere guess. The attempt of Eratosthenes to decide this question went upon principles entirely correct. Scene was situated on the tropic, for there, on the day of the solstice, at noon, objects cast no shadow, and a well was enlightened to the bottom by the sun's rays. At Alexandria, on the same day, the sun was, at noon, distant from the zenith by a 50th part of the circumference. Those two cities were north and south from each other, and the distance had been determined, by the royal overseers of the roads, to be 5,000 stadia. This gave a circumference of 250,000 stadia to the Earth, and a radius of about 40,000. Aristotle says that the mathematicians make the circumference 400,000 stadia. Hipparchus conceived that the measure of Eratosthenes ought to be increased by about 1/10. Posidonius, the friend of Cicero, made another attempt of the same kind. At Rhodes, the star Canopus but just appeared above the horizon. At Alexandria, the same star rose to an altitude of 1/48th of the circumference. The direct distance on the meridian was 5,000 stadia, which gave 240,000 for the whole circuit. We cannot look upon these measures as very precise. The stadium employed is not certainly known, and no peculiar care appears to have been bestowed on the measure of the direct distance. When the Arabians, in the 9th century, came to be the principal cultivators of astronomy, they repeated this observation in a manner more suited to its real importance and capacity of exactness. Under the Caliph Al-Ma'mun, the vast plain of Singar, in Mesopotamia, was the scene of this undertaking. The Arabian astronomers there divided themselves into two bands, one under the direction of Khalid ben Abdulmalik, and the other having at its head Ali's ben Issa. These two parties proceeded, the one north, the other south, determining the distance by the actual application of their measuring rods to the ground. 170, till each was found, by astronomical observation, to be a degree from the place at which they started. It then appeared that these terrestrial degrees were respectively 56 miles, and 56 miles and 2/3, the mile being 4,000 cubits. In order to remove all doubt concerning the scale of this measure, we are informed that the cubit is that called the black cubit, which consists of 27 inches, each inch being the thickness of 6 grains of barley. Sect 6 Ptolemy's discovery of evection. By referring, in this place, to the last-mentioned measure of the Earth, we include the labors of the Arabian as well as the Alexandrian astronomers, in the period of mere detail, which forms the sequel to the great astronomical revolution of the Hipparchian epoch. And this period of verification is rightly extended to those later times. not merely because astronomers were then still employed in determining the magnitude of the Earth, and the amount of other elements of the theory for, these are some of their employments to the present day, because no great intervening discovery marks a new epoch and begins a new period, because no great revolution in the theory added to the objects of investigation or presented them in a new point of view. This being the case, it will be more instructive for our purpose to consider the general character and broad intellectual features of this period, than to offer a useless catalogue of obscure and worthless writers, and of opinions either borrowed or unsound. But before we do this, there is one writer whom we cannot leave undistinguished in the crowd, since his name is more celebrated even than that of Hipparchus. His works contain 99 hundredths of what we know of the Greek astronomy, and though he was not the author of a new theory, he made some very remarkable steps in the verification, correction, and extension of the theory which he received. I speak of Ptolemy, whose work, The Mathematical Construction of the Heavens, contains a complete exposition of the state of astronomy in his time, the reigns of Adrian and Antonine. This book is familiarly known to us by a term which contains the record of our having received our first knowledge of it from the Arabic writers. The Megis Syntaxis, or Great Construction, gave rise among them to the title Al-Magisti, or Almagist, by which the work is commonly described. As a mathematical exposition of the theory of epicycles and eccentrics, of the observations and calculations which were employed in 171, order to apply this theory to the sun, moon, and planets, and of the other calculations which are requisite, in order to deduce the consequences of this theory, the work is a splendid and lasting monument of diligence, skill, and judgment. Indeed, all the other astronomical works of the ancients hardly add anything whatever to the information we obtain from the Almagest, and the knowledge which the student possesses of the ancient astronomy must depend mainly upon his acquaintance with Ptolemy. Among other merits, Ptolemy has that of giving us a very copious account of the manner in which Hipparchus established the main points of his theories, an account the more agreeable, in consequence of the admiration and enthusiasm with which this author everywhere speaks of the great master of the astronomical school. In our present survey of the writings of Ptolemy, we are concerned less with his exposition of what had been done before him than with his own original labors. In most of the branches of the subject, he gave additional exactness to what Hipparchus had done, but our main business, at present, is with those parts of the Almagest which contain new steps in the application of the Hipparchian hypothesis. There are two such cases, both very remarkable, that of the moon's epochs and that of the planetary motions. The law of the moon's anomaly, that is, of the leading and obvious inequality of her motion, could be represented, as we have seen, either by an eccentric or an epicycle, and the amount of this inequality had been collected by observations of eclipses. But though the hypothesis of an epicycle, for instance, would bring the moon to her proper place, so far as eclipses could show it, that is, at new and full moon, this hypothesis did not rightly represent her motions at other points of her course. This appeared when Ptolemy set about measuring her distances from the sun at different times. These, he says, sometimes agreed and sometimes disagreed. But by further attention to the facts, a rule was detected in these differences. As my knowledge became more complete and more connected, so as to show the order of this new inequality, I perceived that this difference was small or nothing at new and full moon, and that at both the dichotomies, when the moon is half illuminated, it was small or nothing if the moon was at the apogee or perigee of the epicycle, and was greatest when she was in the middle of the interval, and therefore when the first, 172, inequality was greatest also. He then adds some further remarks on the circumstances according to which the moon's place, as affected by this new inequality, is before or behind the place, as given by the epicyclical hypothesis. Such is the announcement of the celebrated discovery of the moon's second inequality, afterwards called, by Bullialdus, the evection. Ptolemy soon proceeded to represent this inequality by a combination of circular motions, uniting, for this purpose, the hypothesis of an epicycle, already employed to explain the first inequality, with the hypothesis of an eccentric, in the circumference of which the center of the epicycle was supposed to move. The mode of combining these was somewhat complex. More complex, we may perhaps say, than was absolutely requisite. The apogee of the eccentric moved backwards, or contrary to the order of the signs, and the center of the epicycle moved forwards nearly twice as fast upon the circumference of the eccentric, so as to reach a place nearly, but not exactly, the same as if it had moved in a concentric instead of an eccentric path. Thus, the center of the epicycle went twice round the eccentric in the course of 1 month. And in this manner, it satisfied the condition that it should vanish at new and full moon, and be greatest when the moon was in the quarters of her monthly course. Note 109-3. If Ptolemy had used the hypothesis of an eccentric instead of an epicycle for the first inequality of the moon, an epicycle would have represented the second inequality more simply than his method did. Note 110-3. I will insert here the explanation which my German translator, the late distinguished astronomer Littrow, has given of this point. The rule of this inequality, the evection, may be most simply expressed thus. If a denote the excess of the moon's longitude over the sun's, and be the anomaly of the moon reckoned from her perigee, the evection is equal to 1 degrees. 3 sin, 2 ab. At new and full moon, A is 0 or 180 degrees, and thus the evection is 1 degrees, 3 sin b. At both quarters or dichotomies, A is 90 degrees or 270 degrees, and consequently the evection is plus 1 degrees, 3 sin b. The moon's elliptical equation of the center is at all points of her orbit equal to 6 degrees, 3 sin b. The Greek astronomers before Ptolemy observed the moon only at the time of eclipses, and hence they necessarily found for the sum of these two greatest inequalities of the moon's motion the quantity 6 degrees, 3 sin b, 1 degrees, 3 sin b or 5 degrees, sin b. And as they took this for the moon's equation of the center, which depends upon the eccentricity of the moon's orbit, we obtain from this too small equation of the center an eccentricity also smaller than the truth. Ptolemy, who first observed the moon in her quarters, found for the sum of those inequalities at those points the quantity 6 degrees, 3 sin b plus 1 degrees, 3 sin b or 7 degrees, 6 sin b, and thus made the eccentricity of the moon as much too great at the quarters as the observers of eclipses had made it too small. He hence concluded that the eccentricity of the moon's orbit is variable, which is not the case. The discovery of the evection and the reduction of it to the 173 epicyclical theory was, for several reasons, an important step in astronomy. Some of these reasons may be stated. 1. It obviously suggested, or confirmed, the suspicion that the motions of the heavenly bodies might be subject to many inequalities. That when one set of anomalies had been discovered and reduced to rule, another set might come into view, that the discovery of a rule was a step to the discovery of deviations from the rule, which would require to be expressed in other rules. That in the application of theory to observation, we find not only the stated phenomena, for which the theory does account, but also residual phenomena, which remain unaccounted for and stand out beyond the calculation. That thus nature is not simple and regular, by conforming to the simplicity and regularity of our hypotheses, but leads us forwards to apparent complexity and to an accumulation of rules and relations. A fact like the evection, explained by an hypothesis like Ptolemy's, tended altogether to discourage any disposition to guess at the laws of nature from mere ideal views or from a few phenomena. 2. The discovery of evection had an importance which did not come into view till long afterwards, in being the first of a numerous series of inequalities of the moon, which results from the disturbing force of the sun. These inequalities were successfully discovered and led finally to the establishment of the law of universal gravitation. The moon's first inequality arises from a different cause, from the same cause as the inequality of the sun's motion, from the motion in an ellipse, so far as the central attraction is undisturbed by any other. This first inequality is called the elliptic inequality, or, more usually, the equation of the center. All the planets have such inequalities, but the evection is peculiar to the moon. The discovery of other inequalities of the moon's motion, the variation and annual equation, made an immediate sequel in the order of the subject, to 174, the discoveries of Ptolemy, although separated by a long interval of time, for these discoveries were only made by Tycho Brahe in the 16th century. The imperfection of astronomical instruments was the great cause of this long delay. Note 111-3. The equation of the center is the difference between the place of the planet in its elliptical orbit and that place which a planet would have, which revolved uniformly round the Sun as a center in a circular orbit in the same time. An imaginary planet moving in the manner last described is called the mean planet, while the actual planet which moves in the ellipse is called the true planet. The longitude of the mean planet at a given time is easily found because its motion is uniform. By adding to it the equation of the center, we find the longitude of the true planet, and thus its place in its orbit. Littro's note. I may add that the word equation, used in such cases, denotes in general a quantity which must be added to or subtracted from a mean quantity, to make it equal to the true quantity. Or rather, a quantity which must be added to or subtracted from a variably increasing quantity to make it increase equably. 3. The epicyclical hypothesis was found capable of accommodating itself to such new discoveries. These new inequalities could be represented by new combinations of eccentrics and epicycles. All the real and imaginary discoveries by astronomers, up to Copernicus, were actually embodied in these hypotheses. Copernicus, as we have said, did not reject such hypotheses. The lunar inequalities which Tycho detected might have been similarly exhibited, and even Newton represents the motion of the moon's apogee by means of an epicycle. As a mode of expressing the law of the irregularity, and of calculating its results in particular cases, the epicyclical theory was capable of continuing to render great service to astronomy, however extensive the progress of the science might be. It was, in fact, as we have already said, the modern process of representing the motion by means of a series of circular functions. But though the doctrine of eccentrics and epicycles was thus admissible as an hypothesis, and convenient as a means of expressing the laws of the heavenly motions, the successive occasions on which it was called into use gave no countenance to it as a theory. That is, as a true view of the nature of these motions and their causes. By the steps of the progress of this hypothesis, it became more and more complex instead of becoming more simple, which, as we shall see, was the course of the true theory. The notions concerning the position and connection of the heavenly bodies, which were suggested by one set of phenomena, were not confirmed by the indications of another set of phenomena. For instance, those relations of the epicycles which were adopted to account for the motions of the heavenly bodies were not found to fall in with the consequences of their apparent diameters and parallaxes. In reality, as we have said, if the relative distances of the Sun and Moon at different times could have been accurately determined, the theory of epicycles must have been forthwith overturned. The insecurity of such measurements alone maintained the theory to later times. 175. Note 113/3. The alteration of the apparent diameter of the Moon is so great that it cannot escape us, even with very moderate instruments. This apparent diameter contains, when the Moon is nearest the Earth, 2010 seconds, when she is furthest off 1,762 seconds, that is, 248 seconds, or 4 minutes 8 seconds, less than in the former case. The two quantities are in the proportion of 8 to 7, nearly. Littro's note. Sect 7. Conclusion of the history of Greek astronomy. I might now proceed to give an account of Ptolemy's other great step, the determination of the planetary orbits. But as this, though in itself very curious, would not illustrate any point beyond those already noticed, I shall refer to it very briefly. The planets all move in ellipses about the Sun, as the Moon moves about the Earth, and as the Sun apparently moves about the Earth. They will therefore each have an elliptic inequality or equation of the center, for the same reason that the Sun and Moon have such inequalities. And this inequality may be represented, in the cases of the planets, just as in the other two, by means of an eccentric. The epicycle, it will be recollected, had already been used in order to represent the more obvious changes of the planetary motions. To determine the amount of the eccentricities and the places of the apogees of the planetary orbits was the task which Ptolemy undertook. Hipparchus, as we have seen, having been destitute of the observations which such a process required. The determination of the eccentricities in these cases involved some peculiarities which might not at first sight occur to the reader. The asterisk elliptical motion of the planets takes place about the Sun, but Ptolemy considered their movements as altogether independent of the Sun, and referred them to the Earth alone. And thus the apparent eccentricities which he had to account for were the compound result of the eccentricity of the Earth's orbit and of the proper eccentricity of the orbit of the planet. He explained this result by the received mechanism of an eccentric deferent carrying an epicycle. But the motion in the deferent is uniform, not about the center of the circle, but about another point, the equant. Without going further into detail, it may be sufficient to state that, by a combination of eccentrics and epicycles, he did account for the leading features of these motions. And by using his own observations, compared with more ancient ones, for instance, those of Timacharis for Venus, he was able to determine the dimensions and positions of the orbits. 176. Note 114/3. Ptolemy determined the radius and the periodic time of his two circles for each planet in the following manner. For the inferior planets, that is, Mercury and Venus, he took the radius of the deferent equal to the radius of the Earth's orbit, and the radius of the epicycle equal to that of the planet's orbit. For these planets, according to his assumption, the periodic time of the planet in its epicycle was to the periodic time of the epicyclical center on the deferent, as the synodical revolution of the planet to the tropical revolution of the Earth above the Sun. For the three superior planets, Mars, Jupiter, and Saturn, the radius of the deferent was equal to the radius of the planet's orbit, and the radius of the epicycle was equal to the radius of the Earth's orbit. The periodic time on the planet in its epicycle was to the periodic time of the epicyclical center on the deferent, as the synodical revolution of the planet to the tropical revolution of the same planet. Ptolemy might obviously have made the geometrical motions of all the planets correspond with the observations by one of these two modes of construction, but he appears to have adopted this double form of the theory, in order that in the inferior, as well as in the superior planets, he might give the smaller of the two radii to the epicycle. That is, in order that he might make the smaller circle move round the larger, not vice versa. Littrose notes. I shall here close my account of the astronomical progress of the Greek school. My purpose is only to illustrate the principles on which the progress of science depends, and therefore I have not at all pretended to touch upon every part of the subject. Some portion of the ancient theories, as, for instance, the mode of accounting for the motions of the moon and planets in latitude, are sufficiently analogous to what has been explained, not to require any more especial notice. Other parts of Greek astronomical knowledge, as, for instance, their acquaintance with refraction, did not assume any clear or definite form, and can only be considered as the prelude to modern discoveries on the same subject. And before we can with propriety pass on to these, there is a long and remarkable, though unproductive interval, of which some account must be given. Sect 8 Arabian Astronomy. The interval to which I have just alluded may be considered as extending from Ptolemy to Copernicus. We have no advance in Greek astronomy after the former, no signs of a revival of the power of discovery till the latter. During this interval of 1,350 years, the principal cultivators of astronomy were the Arabians, who adopted this science from the Greeks whom they conquered, and from whom the conquerors of Western Europe again received back their treasure, when the love of science and the capacity for it had been awakened in their minds. In the intervening time, the precious deposit had undergone little change. The Arab astronomer had been the scrupulous but unprofitable servant, who kept his talent without apparent danger of loss, but also without prospect of increase. There is little in 177 Arabic literature which bears upon the progress of astronomy, but as the little that there is must be considered as a sequel to the Greek science, I shall notice one or two points before I treat of the stationary period in general. Note 115/3, Ptolemy died about AD 150. Copernicus was living a.d. 1500. When the scepter of Western Asia had passed into the hands of the Abbasid caliphs, Baghdad, the city of peace, rose to splendor and refinement and became the metropolis of science under the successors of Almansor the Victorious, as Alexandria had been under the successors of Alexander the Great. Astronomy attracted peculiarly the favor of the powerful as well as the learned, and almost all the culture which was bestowed upon the science appears to have had its source in the patronage, often also in the personal studies, of Saracen princes. Under such encouragement, much was done in those scientific labors which money and rank can command. Translations of Greek works were made, large instruments were erected, observers were maintained, and accordingly as observation showed the defects and imperfection of the extant tables of the celestial motions, new ones were constructed. Thus under Almanzor, the Grecian works of science were collected from all quarters, and many of them translated into Arabic. The translation of the Megist Syntaxis of Ptolemy, which thus became the Almagest, is ascribed to Isaac ben Hamin in this reign. The greatest of the Arabian astronomers comes half a century later. This is Albaicneus, as he is commonly called, or more exactly, Mohammed ben Jeber al-Batani, the last appellation indicating that he was born at Batin, a city of Mesopotamia. He was a Syrian prince, whose residence was at Arakti or Racha in Mesopotamia. A part of his observations were made at Antioch. His work still remains to us in Latin. After having read, he says, the syntaxis of Ptolemy, and learnt the methods of calculation employed by the Greeks, his observations led him to conceive that some improvements might be made in their results. He found it necessary to add to Ptolemy's observations as Ptolemy had added to those of Abrachas, Hipparchus. He then published tables of the motions of the sun, moon, and planets, which long maintained a high reputation. These, however, did not prevent the publication of others. Under the Caliph Hakam, about AD 1000, Ibn Iones published tables of the sun, moon, and planets, which were hence called the Hakmite tables. Not long after, Arzashel of Toledo published the Tolton, 178 tables. In the 13th century, Nasir Eddin published tables of the stars, dedicated to Ilchan, a Tartar prince, and hence termed the Ilchanic tables. 2 centuries later, Ulugh Bey, the grandson of Tamerlane and prince of the countries beyond the Oxus, was a zealous practical astronomer. And his tables, which were published in Europe by Hyde in 1665, are referred to as important authority by modern astronomers. The series of astronomical tables which we have thus noticed, in which, however, many are omitted, leads us to the Alpensine tables, which were put forth in 1488. And in succeeding years, under the auspices of Alfonso, king of Castile, and thus brings us to the verge of modern astronomy. For all these tables, the Ptolemaic hypotheses were employed, and for the most part, without alteration. The Arabs sometimes felt the extreme complexity and difficulty of the doctrine which they studied, but their minds did not possess that kind of invention and energy by which the philosophers of Europe, at a later period, won their way into a simpler and better system. Thus Alpetragius states, in the outset of his Planetarum Theorica, that he was at first astonished and stupefied with this complexity, but that afterwards God was pleased to open to him the occult secret in the theory of his orbs, and to make known to him the truth of their essence and the rectitude of the quality of their motion. His system consists, according to D'Alembert, in attributing to the planets a spiral motion from east to west, an idea already refuted by Ptolemy. Geber of Seville criticizes Ptolemy very severely, but without introducing any essential alteration into his system. The Arabian observations are in many cases valuable, both because they were made with more skill and with better instruments than those of the Greeks, and also because they illustrate the permanence or variability of important elements, such as the obliquity of the ecliptic and the inclination of the moon's orbit. We must, however, notice one or two peculiar Arabian doctrines. The most important of these is the discovery of the motion of the sun's apogee by Albaicneus. He found the apogee to be in longitude 82 degrees. Ptolemy had placed it in longitude 65 degrees. The difference of 17 degrees was beyond all limit of probable error of calculation, though the process is not capable of great precision, and the inference of the motion of the apogee was so obvious that we cannot, 179, agree with D'Alembert in doubting or extenuating the claim of Albaicneus to this discovery, on the ground of his not having expressly stated it. In detecting this motion, the Arabian astronomers reasoned rightly from facts well observed. They were not always so fortunate. Arzashel, in the 11th century, found the apogee of the sun to be less advanced than Albaicneus had found it, by some degrees. He inferred that it had receded in the intermediate time. But we now know, from an acquaintance with its real rate of moving, that the true inference would have been that Albaicneus, whose method was less trustworthy than that of Arzashel, had made an error to the amount of the difference thus arising. A curious but utterly false hypothesis was founded on observations thus erroneously appreciated, namely, the trepidation of the fixed stars. Arzachel conceived that a uniform precession of the equinoctial points would not account for the apparent changes of position of the stars, and that for this purpose, it was necessary to conceive two circles of about 8 degrees radius described round the equinoctial points of the immovable sphere, and to suppose the first points of Aries and Libra to describe the circumference of these circles in about 800 years. This would produce, at one time a progression and at another a regression of the apparent equinoxes, and would moreover change the latitude of the stars. Such a motion is entirely visionary, but the doctrine made a sect among astronomers and was adopted in the first edition of the Alpensine tables, though afterwards rejected. An important exception to the general unprogressive character of Arabian science has been pointed out recently by M. Sedalat. It appears that Mohammed Abul Wefaa al-Buzjani, an Arabian astronomer of the 10th century, who resided at Cairo and observed at Baghdad in 975, discovered a third inequality of the moon, in addition to the two expounded by Ptolemy, the equation of the center, and the evection. This third inequality, the variation, is usually supposed to have been discovered by Tycho Brahe 6 centuries later. It is an inequality of the moon's motion, in virtue of which she moves quickest when she is at new or full, and slowest at the first and third quarter. In consequence of this, from the first quarter to the full, she is behind her mean place. At the full, she does not differ from her mean place. From the full to the third quarter, she is before her true 180 place, and so on, and the greatest effect of the inequality is in the octants, or points halfway between the 4 quarters. In an Almagest of Abul Wefaa, a part of which exists in the Royal Library at Paris, after describing the two inequalities of the moon, he has a section 9 of the third anomaly of the moon called Muhazel or prosnuses. He there says that taking cases when the moon was in apogee or perigee, and when, consequently, the effect of the two first inequalities vanishes, he found, by observation of the moon, when she was nearly in trine and in sextile with the sun, that she was 1.25 degrees from her calculated place. And hence, he adds, I perceived that this anomaly exists independently of the two first, and this can only take place by a declination of the diameter of the epicycle with respect to the center of the zodiac. Note 121-3, Sedalat, Nouvelles Reches, sur el Hist, de l'Astron, chez les Arabes, Nouveau Journal Asiatique, 1836. We may remark that we have here this inequality of the moon made out in a really philosophical manner. A residual quantity in the moon's longitude being detected by observation, and the cases in which it occurs selected and grouped by an inductive effort of the mind. The advance is not great, for Abul Wefaa appears only to have detected the existence and not to have fixed the law or the exact quantity of the inequality. But still, it places the scientific capacity of the Arabs in a more favorable point of view than any circumstance with which we were previously acquainted. But this discovery of Abul Wefaa appears to have excited no notice among his contemporaries and followers. At least it had been long quite forgotten when Tycho Brahe rediscovered the same lunar inequality. We can hardly help looking upon this circumstance as an evidence of a servility of intellect belonging to the Arabian period. The learned Arabians were so little in the habit of considering science as progressive, and looking with pride and confidence at examples of its progress, that they had not the courage to believe in a discovery which they themselves had made, and were dragged back by the chain of authority, even when they had advanced beyond their Greek masters. As the Arabians took the whole of their theory, with such slight exceptions as we have been noticing from the Greeks, they took from them also the mathematical processes by which the consequences of the theory were obtained. Arithmetic and trigonometry, two main branches of these processes, received considerable improvements at their hands. In the former, especially, they rendered a service to the world which it is difficult to estimate too highly. In abolishing the 181, cumbrous sexagesimal arithmetic of the Greeks, and introducing the notation by means of the digits 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, which we now employ. These numerals appear to be of Indian origin, as is acknowledged by the Arabs themselves, and thus form no exception to the sterility of the Arabian genius as to great scientific inventions. Another improvement of a subordinate kind, but of great utility, was Arabian, being made by Albaicnius. He introduced into calculation the sine, or half-chord of the double arc, instead of the chord of the arc itself, which had been employed by the Greek astronomers. There have been various conjectures concerning the origin of the word sine. The most probable appears to be that sinus is the Latin translation of the Arabic word jib, which signifies a fold, the two halves of the cord being conceived to be folded together. The great obligation which science owes to the Arabians is to have preserved it during a period of darkness and desolation, so that Europe might receive it back again when the evil days were past. We shall see hereafter how differently the European intellect dealt with this hereditary treasure when once recovered. Before quitting the subject, we may observe that astronomy brought back, from her sojourn among the Arabs, a few terms which may still be perceived in her phraseology. Such are the zenith and the opposite imaginary point, the nadir, the circles of the sphere termed almacantors and azimuth circles. The alidad of an instrument is its index, which possesses an angular motion. Some of the stars still retain their Arabic names, Aldebaran, Rigel Fomalhaut. Many others were known by such appellations a little while ago. Perhaps the word almanac is the most familiar vestige of the Arabian period of astronomy. It is foreign to my purpose to note any efforts of the intellectual faculties among other nations, which may have taken place independently of the great system of progressive European culture, from which all our existing science is derived. Otherwise, I might speak of the astronomy of some of the Orientals, for example, the Chinese, who are said by Montucla, I 465, to have discovered the first equation of the moon and the proper motion of the fixed stars, the precession, in the 3rd century of our era. The Greeks had made these discoveries 500 years earlier. 183, Book 4. History of Physical Science in the Middle Ages, or View of the Stationary Period of Inductive Science. In vain, the all-composing hour resistless falls. As one by one, at dread Medea's strain, the sickening stars fade off ethereal plane, as Argus' eyes, by Hermes' wand oppressed, closed one by one to everlasting rest, thus at her felt approach and secret might, art after art goes out, and all is night. See skulking truth to her old cavern fled, mountains of casuistry heaped on her head philosophy, that reached the heavens before shrinks to her hidden cause and is no more. Physic of metaphysic begs defense, and metaphysic calls for aid to sense see mystery to mathematics fly. In vain, they gaze, turn giddy, rave, and die. Dunched B. Roman 4. 185, Introduction. We have now to consider more especially a long and barren period, which intervened between the scientific activity of ancient Greece and that of modern Europe, and which we may, therefore, call the stationary period of science. It would be to no purpose to enumerate the various forms in which, during these times, men reproduced the discoveries of the inventive ages, or to trace in them the small successes of art, void of any principle of genuine philosophy. Our object requires rather that we should point out the general and distinguishing features of the intellect and habits of those times. We must endeavor to delineate the character of the stationary period, and, as far as possible, to analyze its defects and errors, and thus obtain some knowledge of the causes of its barrenness and darkness. We have already stated that real scientific progress requires distinct general ideas applied to many special and certain facts. In the period of which we now have to speak, men's ideas were obscured, their disposition to bring their general views into accordance with facts was enfeebled. They were thus led to employ themselves unprofitably among indistinct and unreal notions. And the evil of these tendencies was further inflamed by moral peculiarities in the character of those times, by an abjectness of thought on the one hand, which could not help looking towards some intellectual superior, and by an impatience of dissent on the other. To this must be added an enthusiastic temper, which, when introduced into speculation, tends to subject the mind's operations to ideas altogether distorted and delusive. These characteristics of the stationary period, its obscurity of thought, its servility, its intolerant disposition, and its enthusiastic temper, will be treated of in the 4 following chapters, on the indistinctness of ideas, the commentatorial spirit, the dogmatism, and the mysticism of the Middle Ages. 186. Chapter 1. On the indistinctness of ideas of the Middle Ages. That firm and entire possession of certain clear and distinct general ideas, which is necessary to sound science, was the character of the minds of those among the ancients who created the several sciences which arose among them. It was indispensable that such inventors should have a luminous and steadfast apprehension of certain general relations, such as those of space and number, order and cause, and should be able to apply these notions with perfect readiness and precision to special facts and cases. It is necessary that such scientific notions should be more definite and precise than those which common language conveys, and in this state of unusual clearness, they must be so familiar to the philosopher that they are the language in which he thinks. The discoverer is thus led to doctrines which other men adopt and follow out, in proportion as they seize the fundamental ideas and become acquainted with the leading facts. Thus Hipparchus, conceiving clearly the motions and combinations of motion which enter into his theory, saw that the relative lengths of the seasons were sufficient data for determining the form of the sun's orbit. Thus Archimedes, possessing a steady notion of mechanical pressure, was able not only to deduce the properties of the lever and of the center of gravity, but also to see the truth of those principles respecting the distribution of pressure in fluids, on which the science of hydrostatics depends. With the progress of such distinct ideas, the inductive sciences rise and flourish. With the decay and loss of such distinct ideas, these sciences become stationary, languid, and retrograde. When men merely repeat the terms of science, without attaching to them any clear conceptions, when their apprehensions become vague and dim, when they assent to scientific doctrines as a matter of tradition, rather than of conviction, on trust rather than on sight, when science is considered as a collection of opinions, rather than a record of laws by which the universe is really governed, it must inevitably happen that men will lose their hold on the knowledge which the great discoverers who preceded them have brought to light. They are not able to push forwards the truths on which they lay so 187, feeble and irresolute a hand. Probably they cannot even prevent their sliding back towards the obscurity from which they had been drawn, or from being lost altogether. Such indistinctness and vacillation of thought appear to have prevailed in the stationary period, and to be, in fact, intimately connected with its stationary character. I shall point out some indications of the intellectual peculiarity of which I speak. 1. Collections of opinions. The fact that mere collections of the opinions of physical philosophers came to hold a prominent place in literature already indicated a tendency to an indistinct and wandering apprehension of such opinions. I speak of such works as Plutarch's 5 books on the opinions of philosophers, or the physical opinions which Diogenes Laertius gives in his Lives of the Philosophers. At an earlier period still, books of this kind appear, as for instance, a large portion of Pliny's Natural History, a work which has very appropriately been called the Encyclopedia of Antiquity. Even Aristotle himself is much in the habit of enumerating the opinions of those who had preceded him. To present such statements as an important part of physical philosophy shows an erroneous and loose apprehension of its nature. For the only proof of which its doctrines admit is the possibility of applying the general theory to each particular case. The authority of great men, which in moral and practical matters may or must have its weight, is here of no force, and the technical precision of ideas, which the terms of a sound physical theory usually demand, renders a mere statement of the doctrines very imperfectly intelligible to readers familiar with common notions only. To dwell upon such collections of opinions, therefore, both implies and produces in writers and readers an obscure and inadequate apprehension of the full meaning of the doctrines thus collected. Supposing there be among them any which really possess such a clearness, solidity, and reality as to make them important in the history of science. Such diversities of opinion convey no truth. Such a multiplicity of statements of what has been said in no degree teaches us what is. Such accumulations of indistinct notions, however vast and varied, do not make up one distinct idea. On the contrary, the habit of dwelling upon the verbal expressions of the views of other persons, and of being content with such an apprehension of doctrines as a transient notice can give us, is fatal to firm and clear thought. It indicates wavering and feeble conceptions, which are inconsistent with speculation. 188. We may, therefore, consider the prevalence of collections of the kind just referred to as indicating a deficiency of philosophical talent in the ages now under review. As evidence of the same character, we may add the long train of publishers of abstracts, epitomes, bibliographical notices, and similar writers. All such writers are worthless for all purposes of science, and their labors may be considered as dead works. They have in them no principle of philosophical vitality. They draw their origin and nutriment from the death of true physical knowledge, and resemble the swarms of insects that are born from the perishing carcass of some noble animal. 2. Indistinctness of ideas in mechanics. But the indistinctness of thought, which is so fatal a feature in the intellect of the stationary period, may be traced more directly in the works, even of the best authors of those times. We find that they did not retain steadily the ideas on which the scientific success of the previous period had depended. For instance, it is a remarkable circumstance in the history of the science of mechanics that it did not make any advance from the time of Archimedes to that of Stevinus and Galileo. Archimedes had established the doctrine of the lever. Several persons tried, in the intermediate time, to prove the property of the inclined plane, and none of them succeeded. But let us look to the attempts. For example, that of Pappus, in the 8th book of his mathematical collections, and we may see the reason of the failure. His problem shows, in the very terms in which it is propounded, the want of a clear apprehension of the subject. Having given the power which will draw a given weight along the horizontal plane, to find the additional power which will draw the same weight along a given inclined plane. This is proposed without previously defining how powers, producing such effects, are to be measured, and as if the speed with which the body were drawn and the nature of the surface of the plane were of no consequence. The proper elementary problem is to find the force which will support a body on a smooth inclined plane, and no doubt the solution of Pappus has more reference to this problem than to his own. His reasoning is, however, totally at variance with mechanical ideas on any view of the problem. He supposes the weight to be formed into a sphere, and this sphere being placed in contact with the inclined plane, he assumes that the effect will be the same as if the weight were supported on a horizontal lever, the fulcrum being the point of contact of the sphere with the plane, and the power acting at the circumference of the sphere. Such an assumption implies an entire 189 absence of those distinct ideas of force and mechanical pressure, on which our perception of the identity or difference of different modes of action must depend of those ideas by the help of which Archimedes had been able to demonstrate the properties of the lever. And Stevinus afterwards discovered the true solution of the problem of the inclined plane. The motive to Pappus's assumption was probably no more than this. He perceived that the additional power, which he thus obtained, vanished when the plane became horizontal and increased as the inclination became greater. Thus his views were vague. He had no clear conception of mechanical action, and he tried a geometrical conjecture. This is not the way to real knowledge. Pappus, who lived about AD 400, was one of the best mathematicians of the Alexandrian school. And, on subjects where his ideas were so indistinct, it is not likely that any much clearer were to be found in the minds of his contemporaries. Accordingly, on all subjects of speculative mechanics, there appears to have been an entire confusion and obscurity of thought till modern times. Men's minds were busy in endeavoring to systematize the distinctions and subtleties of the Aristotelian school concerning motion and power, and, being thus employed among doctrines in which there was involved no definite meaning capable of real exemplification, they, of course, could not acquire sound physical knowledge. We have already seen that the physical opinions of Aristotle, even as they came from him, had no proper scientific precision. His followers, in their endeavors to perfect and develop his statements, never attempted to introduce clearer ideas than those of their master. And as they never referred, in any steady manner, to facts, the vagueness of their notions was not corrected by any collision with observation. The physical doctrines which they extracted from Aristotle were, in the course of time, built up into a regular system. And though these doctrines could not be followed into a practical application without introducing distinctions and changes, such as deprive the terms of all steady signification, the dogmas continued to be repeated till the world was persuaded that they were self-evident. And when, at a later period, experimental philosophers, such as Galileo and Boyle, ventured to contradict these current maxims, their new principles sounded in men's ears as strange as they now sound familiar. Thus, Boyle promulgated his opinions on the mechanics of fluids as hydrostatical paradoxes proved and illustrated by experiments. And the opinions which he there opposes are those which the Aristotelian philosophers habitually propounded as certain, 190, and indisputable. Such, for instance, as that in fluids the upper parts do not gravitate on the lower, that a lighter fluid will not gravitate on a heavier, that levity is a positive quality of bodies as well as gravity. So long as these assertions were left uncontested and untried, men heard and repeated them, without perceiving the incongruities which they involved. And thus they long evaded refutation, amid the vague notions and undoubting habits of the stationary period. But when the controversies of Galileo's time had made men think with more acuteness and steadiness, it was discovered that many of these doctrines were inconsistent with themselves, as well as with experiment. We have an example of the confusion of thought to which the Aristotelians were liable in their doctrine concerning falling bodies. Heavy bodies, said they, must fall quicker than light ones, for weight is the cause of their fall, and the weight of the greater bodies is greater. They did not perceive that, if they considered the weight of the body as a power acting to produce motion, they must consider the body itself as offering a resistance to motion, and that the effect must depend on the proportion of the power to the resistance. In short, they had no clear idea of accelerating force. This defect runs through all their mechanical speculations and renders them entirely valueless. We may exemplify the same confusion of thought on mechanical subjects in writers of a less technical character. Thus, if men had any distinct idea of mechanical action, they could not have accepted for a moment the fable of the echinus, or remora, a little fish which was said to be able to stop a large ship merely by sticking to it. Lucan refers to this legend in a poetical manner and notices this creature only in bringing together a collection of monstrosities, but Pliny relates the tale gravely and moralizes upon it after his manner. "What," he cries, "is more violent than the sea and the winds? What a greater work of art than a ship? Yet one little fish, the echinus, can hold back all these when they all strain the same way. The winds may 191 blow, the waves may rage, but this small creature controls their fury and stops a vessel when chains and anchors would not hold it. And this it does not by hard labor but merely by adhering to it. Alas for human vanity! When the turreted ships which man has built, that he may fight from castle walls, at sea as well as at land, are held captive and motionless by a fish a foot and a half long. Such a fish is said to have stopped the admiral's ship at the Battle of Actium and compelled Antony to go into another. And in our own memory, one of these animals held fast the ship of Caius, the emperor, when he was sailing from Astera to Antium. The stopping of this ship, when all the rest of the fleet went on, caused surprise, but this did not last long, for some of the men jumped into the water to look for the fish and found it sticking to the rudder. They showed it to Caius, who was indignant that this animal should interpose its prohibition to his progress when impelled by 400 rowers. It was like a slug and had no power after it was taken into the ship. Note 1/4. Lucan is describing one of the poetical compounds produced in incantations. Huc quicquid fidu genuit natura sinistro misseter. Non spuma canum quibus unda timori est, viscera non linsis, non duri nodus hyeni diffuit, et servi pasti serpent medali, in mediis echinais aquas, oculique draconum, et cetera Pharsalia, Roman 6. 670. A very little advance in the power of thinking clearly on the force which it exerted in pulling would have enabled the Romans to see that the ship and its rowers must pull the adhering fish by the hold the oars had upon the water, and that, except the fish had a hold equally strong on some external body, it could not resist this force. 3. Indistinctness of ideas shown in architecture. Perhaps it may serve to illustrate still further the extent to which, under the Roman Empire, men's notions of mechanical relations became faint, wavered, and disappeared, if we observe the change which took place in architecture. All architecture, to possess genuine beauty, must be mechanically consistent. The decorative members must represent a structure which has in it a principle of support and stability. Thus, the Grecian colonnade was a straight horizontal beam resting on vertical props, and the pediment imitated a frame like a roof, where oppositely inclined beams support each other. These forms of building were, therefore, proper models of art because they implied supporting forces. But to be content with colonnades and pediments, which, though they imitated the forms of the Grecian ones, were destitute of their mechanical truth, belonged to the decline of art, and showed that men had lost the idea of force and retained only that of shape. Yet this was what the architects of the Roman Empire did. Under their hands, the pediment was severed at its vertex and divided into separate halves so that it was no longer a mechanical possibility. The entablature no longer lay straight from pillar to pillar, but, projecting over each 192 column, turned back to the wall and adhered to it in the intervening space. The splendid remains of Palmyra, Baalbek, Petra exhibit endless examples of this kind of perverse inventiveness, and show us, very instructively, how the decay of art and of science alike accompany this indistinctness of ideas which we are now endeavoring to illustrate. For indistinctness of ideas in astronomy returning to the sciences, it may be supposed, at first sight, that with regard to astronomy, we have not the same ground for charging the stationary period with indistinctness of ideas on that subject, since they were able to acquire and verify, and, in some measure, to apply, the doctrines previously established. And undoubtedly, it must be confessed that men's notions of the relations of space and number are never very indistinct. It appears to be impossible for these chains of elementary perception ever to be much entangled. The later Greeks, the Arabians, and the earliest modern astronomers must have conceived the hypotheses of the Ptolemaic system with tolerable completeness. And yet, we may assert that during the stationary period, men did not possess the notions, even of space and number, in that vivid and vigorous manner which enables them to discover new truths. If they had perceived distinctly that the astronomical theorist had merely to do with relative motions, they must have been led to see the possibility, at least, of the Copernican system, as the Greeks, at an earlier period, had already perceived it. We find no trace of this. Indeed, the mode in which the Arabian mathematicians present the solutions of their problems does not indicate that clear apprehension of the relations of space, and that delight in the contemplation of them, which the Greek geometrical speculations imply. The Arabs are in the habit of giving conclusions without demonstrations, precepts without the investigations by which they are obtained, as if their main object were practical rather than speculative, the calculation of results rather than the exposition of theory. D'Alembert has been obliged to exercise great ingenuity in order to discover the method by which Ibn Ionis proved his solution of certain difficult problems. Indistinctness of ideas shown by skeptics, the same unsteadiness of ideas which prevents men from obtaining clear views, and steady and just convictions on special subjects may lead them to despair of or deny the possibility of acquiring certainty at all, and may thus make them skeptics with regard to all knowledge. Such skeptics, 193, are themselves men of indistinct views, for they could not otherwise avoid assenting to the demonstrated truths of science. And, so far as they may be taken as specimens of their contemporaries, they prove that indistinct ideas prevail in the age in which they appear. In the stationary period, moreover, the indefinite speculations and unprofitable subtleties of the schools might further impel a man of bold and acute mind to this universal skepticism, because they offered nothing which could fix or satisfy him. And thus the skeptical spirit may deserve our notice as indicative of the defects of a system of doctrine too feeble in demonstration to control such resistance. The most remarkable of these philosophical skeptics is Sextus Empiricus, so called from his belonging to that medical sect which was termed the empirical, in contradistinction to the rational and methodical sects. His works contain a series of treatises directed against all the divisions of the science of his time. He has chapters against the geometers, against the arithmeticians, against the astrologers, against the musicians, as well as against grammarians, rhetoricians, and logicians, and, in short, As a modern writer has said, his skepticism is employed as a sort of framework which embraces an encyclopedical view of human knowledge. It must be stated, however, that his objections are rather to the metaphysical grounds than to the details of the sciences. He rather denies the possibility of speculative truth in general than the experimental truths which had been then obtained. Thus his objections to geometry and arithmetic are founded on abstract cavils concerning the nature of points, letters, unities, and and when he comes to speak against astrology, he says, "I am not going to consider that perfect science which rests upon geometry and arithmetic, for I have already shown the weakness of those sciences, nor that faculty of prediction of the motions of the heavens, which belongs to the pupils of Eudoxus and Hipparchus, and the rest, which some call astronomy. For that is an observation of phenomena, like agriculture or navigation, but against the art of prediction from the time of birth, which the Chaldeans exercise." Sextus, therefore, though a skeptic by profession, was not insensible to the difference between experimental knowledge and mystical dogmas, though even the former had nothing which excited his admiration. The skepticism which denies the evidence of the truths of which the best established physical sciences consist must necessarily involve a very indistinct apprehension of those truths. For such truths, properly exhibited, contain their own evidence and are the best antidote, 194, to this skepticism. But an incredulity or contempt towards the asserted truths of physical science may arise also from the attention being mainly directed to the certainty and importance of religious truths. A veneration for revealed religion may thus assume the aspect of a skepticism with regard to natural knowledge. Such appears to be the case with Algazel or Al-Ghazali, who is adduced by de Gerando as an example of an Arabian skeptic. He was a celebrated teacher at Baghdad in the 11th century, and he declared himself the enemy, not only of the mixed peripatetic and Platonic philosophy of the time, but of Aristotle himself. His work, entitled The Destructions of the Philosophers, is known to us by the refutation of it which Averroes published, under the title of Destruction of Algazel's Destructions of the Philosophers. It appears that he contested the fundamental principles both of the Platonic and of the Aristotelian schools, and denied the possibility of a known connection between cause and effect, thus making a prelude, says de Gerando, to the celebrated argumentation of Hume. Since the publication of my first edition, an account of Al-Ghazel or Al-Ghazali and his works has been published under the title of Essai sur les écoles philosophiques chez les Arabes, et notamment sur la doctrine d'Al-Ghazali, par Auguste Schmolders, Paris, 1842. From this book it appears that de Gerando's account of Al-Ghazali is correct, when he says that his skepticism seems to have essentially for its object to destroy all systems of merely rational theology, in order to open an indefinite career, not only to faith guided by revelation, but also to the free exaltation of a mystical enthusiasm. It is remarked by Dr. Schmolders, following M. de Hammerpergstall, that the title of the work referred to in the text ought rather to be Mutual Refutation of the Philosophers, and that its object is to show that philosophy consists of a mass of systems, each of which overturns the others. The work of Al-Ghazali which Dr. Schmolders has published, On the Errors of Sex, and contains a kind of autobiographical account of the way in which the author was led to his views. He does not reject the truths of science, but he condemns the mental habits which are caused by laying too much stress upon science. Religious men, he says, are, by such a course, led to reject all science, even what relates to eclipses of the moon and sun, and men of science are led to hate religion. 195. Neglect of physical reasoning in Christendom. If the Arabians, who, during the ages of which we are speaking, were the most eminent cultivators of science, entertained only such comparatively feeble and servile notions of its doctrines, it will easily be supposed that in the Christendom of that period, where physical knowledge was comparatively neglected, there was still less distinctness and vividness in the prevalent ideas on such subjects. Indeed, during a considerable period of the history of the Christian Church, and by many of its principal authorities, the study of natural philosophy was not only disregarded but discommended. The great practical doctrines which were presented to men's minds, and the serious tasks of the regulation of the will and affections, which religion impressed upon them, made inquiries of mere curiosity seem to be a reprehensible misapplication of human powers. And many of the fathers of the Church revived, in a still more peremptory form, the opinion of Socrates that the only valuable philosophy is that which teaches us our moral duties and religious hopes. Thus Eusebius says, "It is not through ignorance of the things admired by them, but through contempt of their useless labor, that we think little of these matters, turning our souls to the exercise of better things." When the thoughts were thus intentionally averted from those ideas which natural philosophy involves, the ideas inevitably became very indistinct in their minds, and they could not conceive that any other persons could find, on such subjects, grounds of clear conviction and certainty. They held the whole of their philosophy to be, as Lactantius asserts it to be, empty and false. To search, says he, for the causes of natural things, to inquire whether the sun be as large as he seems, whether the moon is convex or concave, whether the stars are fixed in the sky or float freely in the air. Of what size and of what material are the heavens, whether they be at rest or in motion? What is the magnitude of the earth? On what foundations it is suspended and balanced? To dispute and conjecture on such matters is just as if we chose to discuss what we think of a city in a remote country, of which we never heard but the name. It is impossible to express more forcibly that absence of any definite notions on physical subjects which led to this tone of thought. Question of antipodes with such habits of thought, we are not to be surprised if the relations resulting from the best established theories were apprehended in an imperfect and incongruous manner. 196. We have some remarkable examples of this, and a very notable one is the celebrated question of the existence of antipodes, or persons inhabiting the opposite side of the globe of the earth, and consequently having the soles of their feet directly opposed to ours. The doctrine of the globular form of the earth results, as we have seen, by a geometrical necessity, from a clear conception of the various points of knowledge which we obtain, bearing upon that subject. This doctrine was held distinctly by the Greeks. It was adopted by all astronomers, Arabian and European, who followed them, and was, in fact, an inevitable part of every system of astronomy which gave a consistent and intelligible representation of phenomena. But those who did not call before their minds any distinct representation at all, and who referred the whole question to other relations than those of space, might still deny this doctrine, and they did so. The existence of inhabitants on the opposite side of the terraqueous globe was a fact of which experience alone could teach the truth or falsehood. But the religious relations, which extend alike to all mankind, were supposed to give the Christian philosopher grounds for deciding against the possibility of such a race of men. Lactantius, in the 4th century, argues this matter in a way very illustrative of that impatience of such speculations, and consequent confusion of thought, which we have mentioned. Is it possible, he says, that men can be so absurd as to believe that the crops and trees on the other side of the earth hang downwards, and that men there have their feet higher than their heads? If you ask of them how they defend these monstrosities, how things do not fall away from the earth on that side, they reply, that the nature of things is such that heavy bodies tend towards the center, like the spokes of a wheel, while light bodies, as clouds, smoke, fire, tend from the center towards the heavens on all sides. Now I am really at a loss what to say of those who, when they have once gone wrong, steadily persevere in their folly, and defend one absurd opinion by another. It is obvious that so long as the writer refused to admit into his thoughts the fundamental conception of their theory, he must needs be at a loss what to say to their arguments, without being on that account in any degree convinced of their doctrines. In the 6th century, indeed, in the reign of Justinian, we find a writer, Cosmas Indicoplousts, who does not rest in this obscurity of 197 representation. But in this case, the distinctness of the pictures only serves to show his want of any clear conception as to what suppositions would explain the phenomena. He describes the earth as an oblong floor, surrounded by upright walls and covered by a vault, below which the heavenly bodies perform their revolutions, going round a certain high mountain, which occupies the northern parts of the earth and makes night by intercepting the light of the sun. In Augustine, who flourished AD 400, the opinion is treated on other grounds, and without denying the globular form of the earth, it is asserted that there are no inhabitants on the opposite side, because no such race is recorded by Scripture among the descendants of Adam. Considerations of the same kind operated in the well-known instance of Virgil, Bishop of Salzburg, in the 8th century. When he was reported to Boniface, Archbishop of Mentz, as holding the existence of antipodes, the prelate was shocked at the assumption, as it seemed to him, of a world of human beings, out of the reach of the conditions of salvation. An application was made to Pope Zachary for a censure of the holder of this dangerous doctrine. It does not, however, appear that this led to any severity, and the story of the deposition of Virgil from his bishopric, which is circulated by Kepler and by more modern writers, is undoubtedly altogether false. The same scruples continued to prevail among Christian writers to a later period. Antostatus notes the opinion of the rotundity of the earth as an unsafe doctrine only a few years before Columbus visited the other hemisphere. Note 11:4, Montfaucon, Collectio Nova Patrum, T. Roman II, p. 113, Cosmas Indicoplusts. Christianorum Opinions de Mundo, Sive Topographia Christiana. Note 13:4. It appears, however, that scriptural arguments were found on the other side. St. Jerome says, in Ezech, I6, speaking of the two cherubims with 4 faces, seen by the prophet, and the interpretation of the vision, Alii viro qui philosophorum stultum sequenter sapientium, duo hemispheria in duobus templi cherubim, nos et antipodes, quasi supinos et cadens homines suspicenter. Intellectual condition of the religious orders. It must be recollected, however, that though these were the views and tenets of many religious writers, and though they may be taken as indications of the prevalent and characteristic temper of the times of which we speak, they never were universal. Such a confusion of thought affects the minds of many persons, even in the most enlightened times, and in what we call the Dark Ages, though clear views on such subjects might be more rare, those who gave their minds to science entertained the true opinion of the figure of the earth. Thus Boethius, in the 6th century, urges the smallness of the globe of the earth, 198, compared with the heavens, as a reason to repress our love of glory. This work, it will be recollected, was translated into the Anglo-Saxon by our own Alfred. It was also commented on by Bede, who, in what he says on this passage, assents to the doctrine and shows an acquaintance with Ptolemy and his commentators, both Arabian and Greek. Gerbert, in the 10th century, went from France to Spain to study astronomy with the Arabians and soon surpassed his masters. He is reported to have fabricated clocks and an astrolabe of peculiar construction. Gerbert afterwards, in the last year of the first 1000 from the birth of Christ, became pope by the name of Sylvester Roman II. Among other cultivators of the sciences, some of whom from their proficiency must have possessed with considerable clearness and steadiness the elementary ideas on which it depends, we may here mention, after Montucla, Adelbold, whose work on the sphere was addressed to Pope Sylvester, and whose geometrical reasonings are, according to Montucla, vague and chimerical. Hermann Contractus, a monk of St. Gall, who, in 1050, published astronomical works. William of Herzogen, who followed his example in 1080. Robert of Lorraine, who was made Bishop of Hereford by William the Conqueror in consequence of his astronomical knowledge. In the next century, Adelhard Goth, an Englishman, traveled among the Arabs for purposes of study, as Gerbert had done in the preceding age, and on his return translated the elements of Euclid, which he had brought from Spain or Egypt. Robert Grosstert, Bishop of Lincoln, was the author of an epitome on the sphere. Roger Bacon, in his youth the contemporary of Robert, and of his brother Adam Marsh, praises very highly their knowledge in mathematics. And here, says the French historian of mathematics, whom I have followed in the preceding relation, it is impossible not to reflect that all those men who, if they did not augment the treasure of the sciences, at least served to transmit it, were monks, or had been such originally. Convents were, during these stormy ages, the asylum of sciences and letters. Without these religious men, who, in the silence of their monasteries, occupied themselves in transcribing, in studying, and in imitating the works of the ancients, well or ill, those works would have perished. Perhaps not one of them would have come down to us. The thread which connects us with the Greeks and Romans would have been snapped asunder. The precious productions of 199 ancient literature would no more exist for us than the works, if any there were, published before the catastrophe that annihilated that highly scientific nation, which, according to Bailey, existed in remote ages in the center of Tartary or at the roots of Caucasus. In the sciences, we should have had all to create, and at the moment when the human mind should have emerged from its stupor and shaken off its slumbers, we should have been no more advanced than the Greeks were after the taking of Troy. He adds that this consideration inspires feelings towards the religious orders very different from those which, when he wrote, were prevalent among his countrymen. Except so far as their religious opinions interfered, it was natural that men who lived a life of quiet and study, and were necessarily in a great measure removed from the absorbing and blinding interests with which practical life occupies the thoughts, should cultivate science more successfully than others, precisely because their ideas on speculative subjects had time and opportunity to become clear and steady. The studies which were cultivated under the name of the 7 liberal arts necessarily tended to favor this effect. The trivium, indeed, which consisted of grammar, logic, and rhetoric, had no direct bearing upon those ideas with which physical science is concerned. But the quadrivium, music, arithmetic, geometry, astronomy, could not be pursued with any attention, without a corresponding improvement of the mind for the purposes of sound knowledge. Note 19/4. Roger Bacon, in his Specula Mathematica, cap. I, says, Harum scientiarum porta et clavis est mathematica, quam sancti a principio mundi invenerunt, et cetera cujus negligentia, jam per trigenta vel quadragenta annos destruxit totum studium Latinorum. I do not know on what occasion this neglect took place. 9 popular opinions that, even in the best intellects, something was wanting to fit them for scientific progress and discovery, is obvious from the fact that science was so long absolutely stationary. And I have endeavored to show that one part of this deficiency was the want of the requisite clearness and vigor of the fundamental scientific ideas. If these were wanting, even in the most powerful and most cultivated minds, we may easily conceive that still greater confusion and obscurity prevailed in the common class of mankind. They actually adopted the belief, however crude and inconsistent, that the form of the earth and heavens really is what at any place it appears to be, that the earth is flat, and the waters of the sky sustained above a material floor, through which in showers they descend. Yet the true doctrines of 200 astronomy appear to have had some popular circulation. For instance, a French poem of the time of Edward II, called Image du Monde, contains a metrical account of the earth and heavens, according to the Ptolemaic views. And in a manuscript of this poem, preserved in the library of the University of Cambridge, there are representations, in accordance with the text, of a spherical earth, with men standing upright upon it on every side. And by way of illustrating the tendency of all things to the center, perforations of the earth, entirely through its mass, are described and depicted, and figures are exhibited dropping balls down each of these holes, so as to meet in the interior. And, as bearing upon the perplexity which attends the motions of up and down, when applied to the globular earth, and the change of the direction of gravity which would occur in passing the center, the readers of Dante will recollect the extraordinary manner in which the poet and his guide emerge from the bottom of the abyss, and the explanation which Virgil imparts to him of what he there sees. After they have crept through the aperture in which Lucifer is placed, the poet says, Io levi glai acai e credeti vedir Lucifero com io el aviolasiato, e vida legamb in su tenor. Questi cum e grav fido si sopra. Quando mi valsi, tu passest, il punto al qual si traggendi ogni part I pesi. Inferno, Roman 34. I raised mine eyes, believing that I Lucifer should see where he was lately left, but saw him now with legs held upward. How standeth he in posture thus reversed? Thou wast on the other side so long as I descended. When I turned, thou didst o'erpass that point to which from every part is dragged all heavy substance. Carry. This is more philosophical than Milton's representation, in a more scientific age, of Uriel sliding to the earth on a sunbeam, and sliding back again when the sun had sunk below the horizon. Uriel to his charge returned on that bright beam whose point now raised, bore him slope downward to the sun, now fallen beneath the Azores. Par. Lost, B. Roman 4. 201. The philosophical notions of up and down are too much at variance with the obvious suggestions of our senses, to be held steadily and justly by minds undisciplined in science. Perhaps it was some misunderstood statement of the curved surface of the ocean, which gave rise to the tradition of there being a part of the sea directly over the earth, from which at times an object has been known to fall or an anchor to be let down. Even such whimsical fancies are not without instruction, and may serve to show the reader what that vagueness and obscurity of ideas is, of which I have been endeavoring to trace the prevalence in the Dark Ages. We now proceed to another of the features which appears to me to mark, in a very prominent manner, the character of the stationary period. Chapter 2. The Commentatorial Spirit of the Middle Ages. We have already noticed that, after the first great achievements of the founders of sound speculation, in the different departments of human knowledge, had attracted the interest and admiration which those who became acquainted with them could not but give to them, there appeared a disposition among men to lean on the authority of some of these teachers, to study the opinions of others as the only mode of forming their own, to read nature through books, to attend to what had been already thought and said, rather than to what really is and happens. This tendency of men's minds requires our particular consideration. Its manifestations were very important and highly characteristic of the stationary period. It gave, in a great degree, a peculiar bias and direction to the intellectual activity of many centuries, and the kind of labor with which speculative men were occupied in consequence of this bias took the place of that examination of realities which must be their employment, in order that real knowledge may make any decided progress. In some subjects, indeed, as, for instance, in the domains of morals, poetry, and the arts, whose aim is the production of beauty, this opposition between the study of former opinion and present reality may not be so distinct, inasmuch as it may be said by some that in these subjects opinions are realities, that the thoughts and feelings which 202 prevail in men's minds are the material upon which we must work, the particulars from which we are to generalize, the instruments which we are to use, and that, therefore, to reject the study of antiquity, or even its authority, would be to show ourselves ignorant of the extent and mutual bearing of the elements with which we have to deal, would be to cut asunder that which we ought to unite into a vital whole. Yet even in the provinces of history and poetry, the poverty and servility of men's minds during the Middle Ages are shown by indications so strong as to be truly remarkable. For instance, in the efforts of the antiquarians of almost every European country to assimilate the early history of their own state to the poet's account of the foundation of Rome, by bringing from the sack of Troy, Brutus to England, Bavo to Flanders, and so on. But however this may be, our business at present is to trace the varying spirit of the physical philosophy of different ages, trusting that, hereafter, this prefatory study will enable us to throw some light upon the other parts of philosophy. And in physics the case undoubtedly was that the labor of observation, which is one of the two great elements of the progress of knowledge, was in a great measure superseded by the collection, the analysis, the explanation of previous authors and opinions. Experimenters were replaced by commentators. Criticism took the place of induction, and instead of great discoverers, we had learned men. One natural bias to authority it is very evident that, in such a bias of men's studies, there is something very natural. However strained and technical this erudition may have been, the propensities on which it depends are very general and are easily seen. Deference to the authority of thoughtful and sagacious men, a disposition which men in general neither reject nor think they ought to reject in practical matters, naturally clings to them, even in speculation. It is a satisfaction to us to suppose that there are, or have been, minds of transcendent powers, of wide and wise views, superior to the common errors and blindness of our nature. The pleasure of admiration and the repose of confidence are inducements to such a belief. There are also other reasons why we willingly believe that there are in philosophy great teachers, so profound and sagacious, that in order to arrive at truth, we have only to learn their thoughts, to understand their writings. There is a peculiar interest which men feel in dealing with the thoughts of their fellow men, rather than with brute matter. Matter feels and excites no sympathies. In seeking for mere laws of nature, there is nothing of mental intercourse with the great spirits of the past, as there is in 203 studying Aristotle or Plato. Moreover, a large portion of this employment is of a kind the most agreeable to most speculative minds. It consists in tracing the consequences of assumed principles. It is deductive like geometry. And the principles of the teachers being known and being undisputed, the deduction and application of their results is an obvious, self-satisfying, and inexhaustible exercise of ingenuity. These causes, and probably others, make criticism and commentation flourish, when invention begins to fail, oppressed and bewildered by the acquisitions it has already made, and when the vigor and hope of men's minds are enfeebled by civil and political changes. Accordingly, the Alexandrian school was eminently characterized by a spirit of erudition, of literary criticism, of interpretation, of imitation. These practices, which reigned first in their full vigor in the museum, are likely to be, at all times, the leading propensities of similar academical institutions. How natural it is to select a great writer as a paramount authority, and to ascribe to him extraordinary profundity and sagacity, we may see in the manner in which the Greeks looked upon Homer, and the fancy which detected in his poems traces of the origin of all arts and sciences has, as we know, found favor even in modern times. To pass over earlier instances of this feeling, we may observe that Strabo begins his geography by saying that he agrees with Hipparchus, who had declared Homer to be the first author of our geographical knowledge. And he does not confine the application of this assertion to the various and curious topographical information which the Iliad and Odyssey contain, concerning the countries surrounding the Mediterranean, but in phrases which, to most persons, might appear the mere play of a poetical fancy or a casual selection of circumstances, he finds unquestionable evidence of a correct knowledge of general geographical truths. Thus, when Homer speaks of the sun rising from the soft and deep-flowing ocean, of his splendid blaze plunging in the ocean, of the northern constellation alone unwashen by the ocean wave, and of Jupiter, who goes to the ocean to feast with the blameless Ethiopians, Strabo is satisfied from these passages that Homer knew the dry land to be surrounded with water, and he reasons in like manner with respect to other points of geography. 204. Character of commentators. The spirit of commentation, as has already been suggested, turns to questions of taste, of metaphysics, of morals, with far more avidity than to physics. Accordingly, critics and grammarians were peculiarly the growth of this school, and though the commentators sometimes chose works of mathematical or physical science for their subject, as Proclus, who commented on Euclid's geometry, and Simplicius on Aristotle's physics, these commentaries were, in fact, rather metaphysical than mathematical. It does not appear that the commentators have, in any instance, illustrated the author by bringing his assertions of facts to the test of experiment. Thus, when Simplicius comments on the passage concerning a vacuum, which we formerly adduced, he notices the argument which went upon the assertion that a vessel full of ashes would contain as much water as an empty vessel, and he mentions various opinions of different authors, but no trial of the fact. Eudemus had said that the ashes contain something hot, as quicklime does, and that by means of this, a part of the water was evaporated. Others supposed the water to be condensed, and so on. The commentator's professed object is to explain, to enforce, to illustrate doctrines assumed as true. He endeavors to adapt the work on which he employs himself to the state of information and of opinion in his own time, to elucidate obscurities and technicalities, to supply steps omitted in the reasoning, but he does not seek to obtain additional truths or new generalizations. He undertakes only to give what is virtually contained in his author, to develop, but not to create. He is a cultivator of the thoughts of others. His labor is not spent on a field of his own. He plows but to enrich the granary of another man. Thus he does not work as a freeman, but as one in a servile condition, or rather, his is a menial and not a productive service. His office is to adorn the appearance of his master, not to increase his wealth. Yet though the commentator's employment is thus subordinate and dependent, he is easily led to attribute to it the greatest importance and dignity. To elucidate good books is, indeed, a useful task, and when those who undertake this work execute it well, it would be most unreasonable to find fault with them for not doing more. But the critic, long and earnestly employed on one author, may easily underrate the relative value of other kinds of mental exertion. He may, 205, ascribe too large dimensions to that which occupies the whole of his own field of vision. Thus, he may come to consider such study as the highest aim and best evidence of human genius. To understand Aristotle or Plato may appear to him to comprise all that is possible of profundity and acuteness. And when he has traveled over a portion of their domain and satisfied himself that of this he too is master, he may look with complacency at the circuit he has made and speak of it as a labor of vast effort and difficulty. We may quote, as an expression of this temper, the language of Sir Henry Savile in concluding a course of lectures on Euclid delivered at Oxford. By the grace of God, gentlemen hearers, I have performed my promise. I have redeemed my pledge. I have explained, according to my ability, the definitions, postulates, axioms, and first 8 propositions of the elements of Euclid. Here, sinking under the weight of years, I lay down my art and my instruments. Note 23/4. Exalvi per de gratiam, domini auditors, promissum, liberavi FL meme, explicavi pro mio modulo, definitions, petitions, communes sententias, et octo priors propositions elementorum Euclides. Hic, annis fessus, cyclos artem repono. We here speak of the peculiar province of the commentator. For undoubtedly, in many instances, a commentary on a received author has been made the vehicle of conveying systems and doctrines entirely different from those of the author himself, as, for instance, when the new Platonists wrote, taking Plato for their text. The labors of learned men in the stationary period, which came under this description, belong to another class. 3 Greek commentators on Aristotle, the commentators, or disciples of the great philosophers, did not assume at once their servile character. At first their object was to supply and correct, as well as to explain their teacher. Thus, among the earlier commentators of Aristotle, Theophrastus invented 5 moods of syllogism in the first figure, in addition to the 4 invented by Aristotle, and stated with additional accuracy the rules of hypothetical syllogisms. He also not only collected much information concerning animals and natural events, which Aristotle had omitted, but often differed with his master. As, for instance, concerning the saltness of the sea. This, which the Stagirite attributed to the effect of the evaporation produced by the sun's rays, was ascribed by Theophrastus to beds of salt at the bottom. Porphyry, who flourished in the 3rd century, wrote a book on the predicables, which was found to be so suitable a complement, 206, to the predicaments or categories of Aristotle, that it was usually prefixed to that treatise. And the two have been used as an elementary work together, up to modern times. The predicables are the 5 steps which the gradations of generality and particularity introduce. Genus, species, difference, individual. Accident. The categories are the 10 heads under which assertions or predications may be arranged. Substance, quantity, relation, quality, place, time, position, habit, action, passion. At a later period, the Aristotelian commentators became more servile and followed the author step by step, explaining, according to their views, his expressions and doctrines. Often, indeed, with extreme prolixity, expanding his clauses into sentences and his sentences into paragraphs. Alexander Aphrodisiensis, who lived at the end of the 2nd century, is of this class. Sometimes useful, as one of the recent editors of Aristotle says, but by the prolixity of his interpretation, by his perverse itch for himself discussing the argument expounded by Aristotle, for defending his opinions, and for refuting or reconciling those of others, he rather obscures than enlightens. At various times, also, some of the commentators, and especially those of the Alexandrian school, endeavored to reconcile or combined without reconciling, opposing doctrines of the great philosophers of the earlier times. Simplicius, for instance, and indeed a great number of the Alexandrian philosophers, as Alexander, Ammonius, and others, employed themselves in the futile task of reconciling the doctrines of the Pythagoreans, of the Eleatics, of Plato, and of the Stoics with those of Aristotle. Boethius entertained the design of translating into Latin the whole of Aristotle's and Plato's works, and of showing their agreement, a gigantic plan which he never executed. Others employed themselves in disentangling the confusion which such attempts produced, as John the grammarian, surnamed Philoponus, the labor-loving, who, towards the end of the 7th century, maintained that Aristotle was entirely misunderstood by Porphyry and Proclus, who had pretended to incorporate his doctrines into those of the new Platonic school, or even to reconcile him with Plato himself on the subject of ideas. Others, again, wrote epitomes, compounds, abstracts, and endeavored to throw the works of the philosopher into some simpler and more obviously regular form, as John of Damascus, in 207, the middle of the 8th century, who made abstracts of some of Aristotle's works and introduced the study of the author into theological education. These two writers lived under the patronage of the Arabs. The former was favored by Amru, the conqueror of Egypt. The latter was at first secretary to the caliph, but afterwards withdrew to a monastery. At this period, the Arabians became the fosterers and patrons of philosophy, rather than the Greeks. Justinian had, by an edict, closed the school of Athens, the last of the schools of heathen philosophy. Leo, the Isaurian, who was a zealous iconoclast, abolished also the schools where general knowledge had been taught, in combination with Christianity, yet the line of the Aristotelian commentators was continued, though feebly, to the later ages of the Greek Empire. Anna Komnena mentions a Eustratus who employed himself upon the dialectic and moral treatises, and whom she does not hesitate to elevate above the Stoics and Platonists, for his talent in philosophical discussions. Nicephorus Blemmydes wrote logical and physical epitomes for the use of John Ducas. George Pachymerus composed an epitome of the philosophy of Aristotle and a compend of his logic. Theodore Metachites, who was famous in his time alike for his eloquence and his learning, has left a paraphrase of the books of Aristotle on physics, on the soul, the heavens, and C. Fabricius states that this writer has a chapter, the object of which is to prove that all philosophers, and Aristotle and Plato in particular, have disdained the authority of their predecessors. He could hardly help remarking in how different spirit philosophy had been pursued since their time. Greek commentators of Plato and others have spoken principally of the commentators of Aristotle, for he was the great subject of the commentators proper. And though the name of his rival, Plato, was graced by a list of attendants, hardly less numerous, these, the Neoplatonists, as they are called, had introduced new elements into the doctrines of their nominal master, to such an extent that they must be placed in a different class. We may observe here, however, how, in this school as in the Peripatetic, the race of commentators multiplied itself. Porphyry, who commented on Aristotle, was commented on by Ammonius. Plotinus's Enneads were commented on by Proclus and Dexippus. Cellus the Elder was a paraphrast of 208 Aristotle. Cellus the Younger, in the 11th century, attempted to restore the new Platonic school. The former of these two writers had for his pupils two men, the Emperor Leo, surnamed the Philosopher, and Photius the Patriarch, who exerted themselves to restore the study of literature at Constantinople. We still possess the collection of extracts of Photius, which, like that of Stobaeus and others, shows the tendency of the age to compilations, abstracts, and epitomes the extinction of philosophical vitality. Arabian commentators of Aristotle the reader might perhaps have expected that when the philosophy of the Greeks was carried among a new race of intellects, of a different national character and condition, the train of this servile tradition would have been broken, that some new thoughts would have started forth, that some new direction, some new impulse, would have been given to the search for truth. It might have been anticipated that we should have had schools among the Arabians which should rival the Peripatetic, academic, and Stoic among the Greeks, that they would preoccupy the ground on which Copernicus and Galileo, Lavoisier and Linnaeus won their fame, that they would make the next great steps in the progressive sciences. Nothing of this, however, happened. The Arabians cannot claim, in science or philosophy, any really great names. They produced no men and no discoveries which have materially influenced the course and destinies of human knowledge. They tamely adopted the intellectual servitude of the nation which they conquered by their arms. They joined themselves at once to the string of slaves who were dragging the car of Aristotle and Plotinus. Nor, perhaps, on a little further reflection, shall we be surprised at this want of vigor and productive power in this period of apparent national youth. The Arabians had not been duly prepared rightly to enjoy and use the treasures of which they became possessed. They had, like most uncivilized nations, been passionately fond of their indigenous poetry. Their imagination had been awakened, but their rational powers and speculative tendencies were still torpid. They received the Greek philosophy without having passed through those gradations of ardent curiosity and keen research, of obscurity brightening into clearness, of doubt succeeded by the joy of discovery, by which the Greek mind had been enlarged and exercised. Nor had the Arabians ever enjoyed, as the Greeks had, the individual consciousness, the independent volition, the intellectual freedom, arising from the freedom of political institutions. They had not felt the contagious mental activity of a small city, the elation arising from the general, 209, sympathy in speculative pursuits, diffused through an intelligent and acute audience. In short, they had not had a national education, such as fitted the Greeks to be disciples of Plato and Hipparchus. Hence, their new literary wealth rather encumbered and enslaved than enriched and strengthened them. In their want of taste for intellectual freedom, they were glad to give themselves up to the guidance of Aristotle and other dogmatists. Their military habits had accustomed them to look to a leader. Their reverence for the book of their law had prepared them to accept a philosophical Quran also. Thus the Arabians, though they never translated the Greek poetry, translated and merely translated, the Greek philosophy, they followed the Greek philosophers without deviation, or, at least, without any philosophical deviations. They became for the most part Aristotelians, studied not only Aristotle, but the commentators of Aristotle, and themselves swelled the vast and unprofitable herd. The philosophical works of Aristotle had in some measure made their way in the East before the growth of the Saracen power. In the 6th century, Assyrian Uranus, encouraged by the love of philosophy manifested by Khosroes, had translated some of the writings of the Stagirite. About the same time, Sergius had given some translations in Syriac. In the 7th century, Jacob of Edessa translated into this language the dialectics and added notes to the work. Such labors became numerous, and the first Arabic translations of Aristotle were formed upon these Persian or Syriac texts. In this succession of transfusions, some mistakes must inevitably have been introduced. The Arabian interpreters of Aristotle, like a large portion of the Alexandrian ones, gave to the philosopher a tinge of opinions borrowed from another source, of which I shall have to speak under the head of mysticism. But they are, for the most part, sufficiently strong examples of the peculiar spirit of commentation to make it fitting to notice them here. At the head of them stands Al-Kindi, who appears to have lived at the court of Almaman and who wrote commentaries on the Organon of Aristotle. But Al-Farabi was the glory of the school of Baghdad. His knowledge included mathematics, astronomy, medicine, and philosophy. Born in an elevated rank and possessed of a rich patrimony, he led an austere life and devoted himself altogether to study and meditation. He employed himself particularly in unfolding the import of Aristotle's treatise on the soul. Avicenna, Ibn Sina, 210, was at once the Hippocrates and the Aristotle of the Arabians, and certainly the most extraordinary man that the nation produced. In the course of an unfortunate and stormy life, occupied by politics and by pleasures, he produced works which were long revered as a sort of code of science. In particular, his writings on medicine, though they contain little besides a compilation of Hippocrates and Galen, took the place of both, even in the universities of Europe, and were studied as models at Paris and Montpellier, till the end of the 17th century, at which period they fell into an almost complete oblivion. Avicenna is conceived, by some modern writers, to have shown some power of original thinking in his representations of the Aristotelian logic and metaphysics. Averroes, Ibn Rushd of Cordova, was the most illustrious of the Spanish Aristotelians and became the guide of the schoolmen, being placed by them on a level with Aristotle himself or above him. He translated Aristotle from the first Syriac version, not being able to read the Greek text. He aspired to, and retained for centuries, the title of the commentator, and he deserves this title by the servility with which he maintains that Aristotle carried the sciences to the highest possible degree, measured their whole extent, and fixed their ultimate and permanent boundaries. Although his works are conceived to exhibit a trace of the New Platonism, some of his writings are directed against an Arabian skeptic of the name of Algazel, whom we have already noticed. When the schoolmen had adopted the supremacy of Aristotle to the extent in which Averroes maintained it, their philosophy went further than a system of mere commentation and became a system of dogmatism. We must, therefore, in another chapter, say a few words more of the Aristotelians in this point of view before we proceed to the revival of science, but we must previously consider some other features in the character of the stationary period. 211. Chapter 3. Of the mysticism of the Middle Ages. It has been already several times hinted that a new and peculiar element was introduced into the Greek philosophy which occupied the attention of the Alexandrian school, and that this element tinged a large portion of the speculations of succeeding ages. We may speak of this peculiar element as mysticism, for, from the notion usually conveyed by this term, the reader will easily apprehend the general character of the tendency now spoken of, and especially when he sees its effect pointed out in various subjects. Thus, instead of referring the events of the external world to space and time, to sensible connection and causation, men attempted to reduce such occurrences under spiritual and supersensual relations and dependencies. They referred them to superior intelligences, to theological conditions, to past and future events in the moral world, to states of mind and feelings, to the creatures of an imaginary mythology or demonology. And thus their physical science became magic, their astronomy became astrology, the study of the composition of bodies became alchemy, mathematics became the contemplation of the spiritual relations of number and figure, and philosophy became theosophy. The examination of this feature in the history of the human mind is important for us, in consequence of its influence upon the employments and the thoughts of the times now under our notice. This tendency materially affected both men's speculations and their labors in the pursuit of knowledge. By its direct operation, it gave rise to the newer Platonic philosophy among the Greeks and to corresponding doctrines among the Arabians, and by calling into a prominent place astrology, alchemy, and magic, it long occupied most of the real observers of the material world. In this manner, it delayed and impeded the progress of true science, for we shall see reason to believe that human knowledge lost more by the perversion of men's minds and the misdirection of their efforts than it gained by any increase of zeal arising from the peculiar hopes and objects of the mystics. It is not our purpose to attempt any general view of the progress and fortunes of the various forms of mystical philosophy, but only to exhibit some of its characters, in so far as they illustrate those 212 tendencies of thought which accompanied the retrogradation of inductive science. And of these, the leading feature which demands our notice is that already alluded to, namely, the practice of referring things and events not to clear and distinct relations, obviously applicable to such cases, not to general rules capable of direct verification, but to notions vague, distant, and vast, which we cannot bring into contact with facts, because they belong to a different region from the facts. As when we connect natural events with moral or historical causes, or seek spiritual meanings in the properties of number and figure. Thus the character of mysticism is that it refers particulars, not to generalizations homogeneous and immediate, but to such as are heterogeneous and remote, to which we must add that the process of this reference is not a calm act of the intellect, but is accompanied with a glow of enthusiastic feeling. One Neoplatonic theosophy, the newer Platonism, is the first example of this mystical philosophy, which I shall consider. The main points which here require our notice are the doctrine of an intellectual world resulting from the act of the divine mind as the only reality, and the aspiration after the union of the human soul with this divine mind as the object of human existence. The ideas of Plato were forms of our knowledge, but among the Neoplatonists they became really existing, indeed the only really existing objects. And the inaccessible scheme of the universe which these ideas constitute was offered as the great subject of philosophical contemplation. The desire of the human mind to approach towards its creator and preserver, and to obtain a spiritual access to him, leads to an employment of the thoughts which is well worth the notice of the religious philosopher. But such an effort, even when founded on revelation and well regulated, is not a means of advance in physics. And when it is the mere result of natural enthusiasm, it may easily obtain such a place in men's minds as to unfit them for the successful prosecution of natural philosophy. The temper, therefore, which introduces such supernatural communion into the general course of its speculations, may be properly treated as mystical, and as one of the causes of the decline of science in the stationary period. The Neoplatonic philosophy requires our notice as one of the most remarkable forms of this mysticism. Though Ammonius Saccas, who flourished at the end of the 2nd century, is looked upon as the beginner of the Neoplatonists, his disciple Plotinus is, in reality, the great founder of the school both by his 213 works, which still remain to us, and by the enthusiasm which his character and manners inspired among his followers. He lived a life of meditation, gentleness, and self-denial, and died in the 2nd year of the reign of Claudius, AD 270. His disciple, Porphyry, has given us a life of him, from which we may see how well his habitual manners were suited to make his doctrines impressive. Plotinus, the philosopher of our time, Porphyry thus begins his biography, appeared like a person ashamed that he was in the body. In consequence of this disposition, he could not bear to talk concerning his family, or his parents, or his country. He would not allow himself to be represented by a painter or statuary, and once, when Aurelius entreated him to permit a likeness of him to be taken, he said, "Is it not enough for us to carry this image in which nature has enclosed us, but we must also try to leave a more durable image of this image, as if it were so great a sight?" And he retained the same temper to the last. When he was dying, he said, "I am trying to bring the divinity which is in us to the divinity which is in the universe." He was looked upon by his successors with extraordinary admiration and reverence, and his disciple Porphyry collected from his lips, or from fragmental notes, the 6 Enneads of his doctrines, that is, parts each consisting of 9 books, which he arranged and annotated. We have no difficulty in finding in this remarkable work examples of mystical speculation. The intelligible world of realities or essences corresponds to the world of sense in the classes of things which it includes. To the intelligible world, man's mind ascends by a triple road which Plotinus figuratively calls that of the musician, the lover, the philosopher. The activity of the human soul is identified by analogy with the motion of the heavens. This activity is about a middle point, and thus it is circular, but a middle point is not the same in body and in the soul. In that, the middle point is local. In this, it is that on which the rest depends. There is, however, an analogy, for as in one case, so in the other, there must be a middle point, and as the sphere revolves about its center, the soul revolves about God through its affections. The conclusion of the work is, as might be supposed, upon the approach to, union with, and fruition of God. The author refers again to the analogy between the movements of the soul and those of the heavens. We move round him like a choral dance. Even when we, 214, look from him, we revolve about him. We do not always look at him, but when we do, we have satisfaction and rest, and the harmony which belongs to that divine movement. In this movement, the mind beholds the fountain of life, the fountain of mind, the origin of being, the cause of good, the root of the soul. There will be a time when this vision shall be continual, the mind being no more interrupted, nor suffering any perturbation from the body. Yet that which beholds is not that which is disturbed. And when this vision becomes dim, it does not obscure the knowledge which resides in demonstration and faith and reasoning. But the vision itself is not reason, but greater than reason, and before reason. The 5th book of the 3rd Ennead has for its subject the demon which belongs to each man. It is entitled Concerning Love, and the doctrine appears to be that the love or common source of the passions which is in each man's mind is the demon which they say accompanies each man. These demons were, however, at least by later writers, invested with a visible aspect and with a personal character, including a resemblance of human passions and motives. It is curious thus to see an untenable and visionary generalization falling back into the domain of the senses and the fancy, after a vain attempt to support itself in the region of the reason. This imagination soon produced pretensions to the power of making these demons or genii visible. And the treatise on the mysteries of the Egyptians, which is attributed to Iamblichus, gives an account of the secret ceremonies, the mysterious words, the sacrifices and expiations by which this was to be done. It is unnecessary for us to dwell on the progress of this school, to point out the growth of the theurgy which thus arose, or to describe the attempts to claim a high antiquity for this system, and to make Orpheus, the poet, the first promulgator of its doctrines. The system, like all mystical systems, assumed the character rather of religion than of a theory. The opinions of its disciples materially influenced their lives. It gave the world the spectacle of an austere morality, a devotional exaltation, combined with the grossest superstitions of paganism. The successors of Iamblichus appeared rather to hold a priesthood than the chair of a philosophical school. They were persecuted by Constantine and Constantius as opponents of Christianity. Sopater, a 215 Syrian philosopher of this school, was beheaded by the former emperor on a charge that he had bound the winds by the power of magic. But Julian, who shortly after succeeded to the purple, embraced with ardor the opinions of Iamblichus. Proclus, who died AD 487, was one of the greatest of the teachers of this school, and was, both in his life and doctrines, a worthy successor of Plotinus, Porphyry, and Iamblichus. We possess a biography, or rather a panegyric of him, by his disciple Marinus, in which he is exhibited as a representation of the ideal perfection of the philosophic character, according to the views of the Neoplatonists. His virtues are arranged as physical, moral, purificatory, theoretic, and theurgic. Even in his boyhood, Apollo and Minerva visited him in his dreams. He studied oratory at Alexandria, but it was at Athens that Plutarch and Lysianus initiated him in the mysteries of the New Platonists. He received a kind of consecration at the hands of the daughter of Plutarch, the celebrated Asclepigenia, who introduced him to the traditions of the Chaldeans and the practices of theurgy. He was also admitted to the mysteries of Eleusis. He became celebrated for his knowledge and eloquence, but especially for his skill in the supernatural arts which were connected with the doctrines of his sect. He appears before us rather as a hierophant than a philosopher. A large portion of his life was spent in evocations, purifications, fastings, prayers, hymns, intercourse with apparitions, and with the gods, and in the celebration of the festivals of paganism, especially those which were held in honor of the mother of the gods. His religious admiration extended to all forms of mythology. The philosopher, said he, is not the priest of a single religion, but of all the religions of the world. Accordingly, he composed hymns in honor of all the divinities of Greece, Rome, Egypt, Arabia. Christianity alone was excluded from his favor. The reader will find an interesting view of the school of Alexandria in M. Barthélemy Saint-Hilaire's rapport on the memoirs sent to the Academy of Moral and Political Sciences at Paris, in consequence of its having, in 1841, proposed this as the subject of a prize, which was awarded in 1844. M. Saint-Hilaire has prefixed to this rapport a dissertation on the mysticism of that school. He, however, uses the term mysticism in a wider sense than my purpose, which regarded mainly the bearing of the doctrines of this school upon the progress of the inductive sciences, has led me to do. Although he finds much to 216 admire in the Alexandrian philosophy, he declares that they were incapable of treating scientific questions. The extent to which this is true is well illustrated by the extract which he gives from Plotinus on the question, why objects appear smaller in proportion as they are more distant. Plotinus denies that the reason of this is that the angles of vision become smaller. His reason for this denial is curious enough. If it were so, he says, how could the heaven appear smaller than it is, since it occupies the whole of the visual angle? 2. Mystical arithmetic. It is unnecessary further to exemplify, from Proclus, the general mystical character of the school and time to which he belonged. But we may notice more specially one of the forms of this mysticism, which very frequently offers itself to our notice, especially in him, and which we may call mystical arithmetic. Like all the kinds of mysticism, this consists in the attempt to connect our conceptions of external objects by general and inappropriate notions of goodness, perfection, and relation to the divine essence and government. Instead of referring such conceptions to those appropriate ideas, which, by due attention, become perfectly distinct and capable of being positively applied and verified. The subject which is thus dealt with, in the doctrines of which we now speak, is number, a notion which tempts men into these visionary speculations more naturally than any other. For number is really applicable to moral notions, to emotions and feelings, and to their objects as well as to the things of the material world. Moreover, by the discovery of the principle of musical concords, it had been found, probably most unexpectedly, that numerical relations were closely connected with sounds which could hardly be distinguished from the expression of thought and feeling. And a suspicion might easily arise that the universe, both of matter and of thought, might contain many general and abstract truths of some analogous kind. The relations of number have so wide a bearing that the ramifications of such a suspicion could not easily be exhausted, supposing men willing to follow them into darkness and vagueness, which it is precisely the mystical tendency to do. Accordingly, this kind of speculation appeared very early, and showed itself first among the Pythagoreans, as we might have expected, from the attention which they gave to the theory of harmony. And this, as well as some other of the doctrines of the Pythagorean philosophy, was adopted by the later Platonists, and, indeed, by Plato himself, whose speculations concerning number have decidedly a mystical character. The mere mathematical relations of numbers, as odd and even, perfect and imperfect, 217, abundant and defective, were, by a willing submission to an enthusiastic bias, connected with the notions of good and beauty, which were suggested by the terms expressing their relations, and principles resulting from such a connection were woven into a wide and complex system. It is not necessary to dwell long on this subject. The mere titles of the works which treated of it show its nature. Archytas is said to have written a treatise on the number 10. Telegay, the daughter of Pythagoras, wrote on the number 4. This number, indeed, which was known by the name of the Tetractes, was very celebrated in the school of Pythagoras. It is mentioned in the golden verses, which are ascribed to him. The pupil is conjured to be virtuous. Mu alpha letter 1 F76, mu letter 1 F70, tau letter 1 F78, mu letter 1 F01, mu epsilon tau, epsilon rho letter 1 FB3, psi upsilon chi letter 1 FB7, pi alpha rho alpha delta omicron nu tau alpha, tau epsilon tau, rho alpha kappa tau letter 1 F7a, nu pi alpha gamma letter 1 F70, nu letter 1 F00 epsilon nu alpha omicron upsilon, phi upsilon sigma epsilon omega sigma. By him who stamped the 4 upon the mind, the 4, the fount of nature's endless stream. In Plato's works, we have evidence of a similar belief in religious relations of number, and in the New Platonists, this doctrine was established as a system. Proclus, of whom we have been speaking, founds his philosophy, in a great measure, on the relation of unity and multiple. From this, he is led to represent the causality of the divine mind by 3 triads of abstractions, and in the development of one part of this system, the number 7 is introduced. The intelligible and intellectual gods produce all things triadically, for the monads in these latter are divided according to number, and what the monad was in the former, the number is in these latter. And the intellectual gods produce all things hebdomically, for they evolve the intelligible, and at the same time intellectual triads into intellectual hebdomads, and expand their contracted powers into intellectual variety. 7 is what is called by arithmeticians a prime number, that is, it cannot be produced by the multiplication of other numbers. In the language of the New Platonists, the number 7 is said to be a virgin and without a mother, and it is therefore sacred to Minerva. The number 6 is a perfect number and is consecrated to Venus. The relations of space were dealt with in like manner, the geometrical properties being associated with such physical and metaphysical notions as vague thought and lively feeling could anyhow connect with them. We may consider, as an example of this, Plato's opinion 218 concerning the particles of the 4 elements. He gave to each kind of particle one of the 5 regular solids, about which the geometrical speculations of himself and his pupils had been employed. The particles of fire were pyramids because they are sharp and tend upwards. Those of earth are cubes because they are stable and fill space. The particles of air are octahedral, as most nearly resembling those of fire. Those of water are the icosahedron, as most nearly spherical. The dodecahedron is the figure of the element of the heavens and shows its influence in other things, as in the 12 signs of the zodiac. In such examples, we see how loosely space and number are combined or confounded by these mystical visionaries. These numerical dreams of ancient philosophers have been imitated by modern writers, for instance, by Peter Bungo and Kircher, who have written De Mysteries Numerorum. Bungo treats of the mystical properties of each of the numbers in order, at great length, and such speculations have influenced astronomical theories. In the first edition of the Alpensine Tables, The precession was represented by making the first point of Aries move, in a period of 7,000 years, through a circle of which the radius was 18 degrees, while the circle moved round the ecliptic in 49,000 years. And these numbers, 7,000 and 49,000, were chosen probably by Jewish calculators, or with reference to Jewish Sabbatarian notions. Astrology, of all the forms which mysticism assumed, none was cultivated more assiduously than astrology. Although this art prevailed most universally and powerfully during the stationary period, its existence, even as a detailed technical system, goes back to a very early age. It probably had its origin in the East. It is universally ascribed to the Babylonians and Chaldeans. The name Chaldean was, at Rome, synonymous with mathematicus or astrologer. And we read repeatedly that this class of persons were expelled from Italy by a decree of the Senate, both during the times of the Republic and of the Empire. The recurrence of this act of legislation shows that it was not effectual. It is a class of men, says Tacitus, which in our city will always be prohibited and will always exist. In Greece, it does not appear that the state showed any hostility to the professors of this art. They undertook, it would seem, then, as at a later period, to determine the course of a man's character and life from the configuration of the stars at the moment of his birth. We do not possess any of the 219 speculations of the early astrologers, and we cannot therefore be certain that the notions which operated in men's minds when the art had its birth agreed with the views on which it was afterwards defended when it became a matter of controversy. But it appears probable that, though it was at later periods supported by physical analogies, it was originally suggested by mythological belief. The Greeks spoke of the influences or effluxes, letter 1F00, pi omicron, letter 1Fe4, letter 1Fe5 omicron, iota alpha sigma, which proceeded from the stars. But the Chaldeans had probably thought rather of the powers which they exercised as deities. In whatever manner the sun, moon, and planets came to be identified with gods and goddesses, it is clear that the characters ascribed to these gods and goddesses regulate the virtues and powers of the stars which bear their names. This association, so manifestly visionary, was retained, amplified, and pursued in an enthusiastic spirit, instead of being rejected for more distinct and substantial connections, and a pretended science was thus formed, which bears the obvious stamp of mysticism. That common sense of mankind, which teaches them that theoretical opinions are to be calmly tried by their consequences and their accordance with facts, appears to have counteracted the prevalence of astrology in the better times of the human mind. Eudoxus, as we are informed by Cicero, rejected the pretensions of the Chaldeans, and Cicero himself reasons against them with arguments as sensible and intelligent as could be adduced by a writer of the present day, such as the different fortunes and characters of persons born at the same time, and the failure of the predictions in the case of Pompey, Crassus, Caesar, to whom the astrologers had foretold glorious old age and peaceful death. He also employs an argument which the reader would perhaps not expect from him, the very great remoteness of the planets as compared with the distance of the moon. What contagion can reach us, he asks, from a distance almost infinite? Pliny argues on the same side and with some of the same arguments. Homer, he says, tells us that Hector and Polydamas were born the same night, men of such different fortune, and every hour in every part of the world are born lords and slaves, kings and beggars. The impression made by these arguments is marked in an anecdote told concerning Publius Nigidius Figulus, a Roman of the time of Julius Caesar, whom Lucan mentions as a celebrated astrologer. It is 220 said that when an opponent of the art urged as an objection the different fates of persons born in two successive instants, Nigidius bade him make two contiguous marks on a potter's wheel, which was revolving rapidly near them. On stopping the wheel, the two marks were found to be really far removed from each other, and Nigidius is said to have received the name of Figulus, the potter. In remembrance of this story, his argument, says St. Augustine, who gives us the narrative, was as fragile as the ware which the wheel manufactured. As the darkening times of the Roman Empire advanced, even the stronger minds seem to have lost the clear energy which was requisite to throw off this delusion. Seneca appears to take the influence of the planets for granted, and even Tacitus seems to hesitate. For my own part, says he, I doubt, but certainly the majority of mankind cannot be weaned from the opinion that, at the birth of each man, his future destiny is fixed, though some things may fall out differently from the predictions by the ignorance of those who profess the art, and that thus the art is unjustly blamed, confirmed as it is by noted examples in all ages. The occasion which gives rise to these reflections of the historian is the mention of Thrasyllus, the favorite astrologer of the Emperor Tiberius, whose skill is exemplified in the following narrative. Those who were brought to Tiberius on any important matter were admitted to an interview in an apartment situated on a lofty cliff in the island of Capri. They reached this place by a narrow path, accompanied by a single freedman of great bodily strength. And on their return, if the emperor had conceived any doubts of their trustworthiness, a single blow buried the secret and its victim in the ocean below. After Thrasyllus had, in this retreat, stated the results of his art as they concerned the emperor, Tiberius asked him whether he had calculated how long he himself had to live. The astrologer examined the aspect of the stars, and while he did this, as the narrative states, showed hesitation, alarm, increasing terror, and at last declared that the present hour was for him critical, perhaps fatal. Tiberius embraced him and told him he was right in supposing he had been in danger, but that he should escape it, and made him thenceforth his confidential counselor. The belief in the power of astrological prediction, which thus obtained dominion over the minds of men of literary cultivation and practical energy, naturally had a more complete sway among the speculative, 221, but unstable minds of the later philosophical schools of Alexandria, Athens, and Rome. We have a treatise on astrology by Proclus, which will serve to exemplify the mystical principle in this form. It appears as a commentary on a work on the same subject called Tetrabiblos, ascribed to Ptolemy, though we may reasonably doubt whether the author of the Megalsyntaxis was also the writer of the astrological work. A few notices of the commentary of Proclus will suffice. The science is defended by urging how powerful we know the physical effects of the heavenly bodies to be. The sun regulates all things on earth, the birth of animals, the growth of fruits, the flowing of waters, the change of health according to the seasons. He produces heat, moisture, dryness, cold, according to his approach to our zenith. The moon, which is the nearest of all bodies to the earth, gives out much influence, and all things, animate and inanimate, sympathize with her. Rivers increase and diminish according to her light. The advance of the sea and its recess are regulated by her rising and setting, and along with her, fruits and animals wax and wane, either wholly or in part. It is easy to see that by pursuing this train of associations, some real and some imaginary, very vaguely and very enthusiastically, the connections which astrology supposes would receive a kind of countenance. Proclus then proceeds to state the doctrines of the science. The sun, he says, is productive of heat and dryness. This power is moderate in its nature, but is more perceived than that of the other luminaries from his magnitude and from the change of seasons. The nature of the moon is for the most part moist. For being the nearest to the earth, she receives the vapors which rise from moist bodies, and thus she causes bodies to soften and rot. But by the illumination she receives from the sun, she partakes in a moderate degree of heat. Saturn is cold and dry, being most distant both from the heating power of the sun and the moist vapors of the earth. His cold, however, is most prevalent, his dryness is more moderate. Both he and the rest receive additional powers from the configurations which they make with respect to the sun and moon. In the same manner, it is remarked that Mars is dry and caustic, from his fiery nature, which indeed his color shows. Jupiter is well compounded of warm and moist, as is Venus. Mercury is variable in his character. From these notions were derived others concerning the beneficial or hurtful effect of these stars. Heat and 222 moisture are generative and creative elements. Hence the ancients, says Proclus, deemed Jupiter and Venus and the moon to have a good power. Saturn and Mercury, on the other hand, had an evil nature. Other distinctions of the character of the stars are enumerated, equally visionary, and suggested by the most fanciful connections. Some are masculine and some feminine. The moon and Venus are of the latter kind. This appears to be merely a mythological or etymological association. Some are diurnal, some nocturnal. The moon and Venus are of the latter kind, the Sun and Jupiter of the former, Saturn and Mars are both. The fixed stars also, and especially those of the zodiac, had especial influences and subjects assigned to them. In particular, each sign was supposed to preside over a particular part of the body. Thus Aries had the head assigned to it, Taurus the neck, and so on. The most important part of the sky in the astrologer's consideration was that sign of the zodiac which rose at the moment of the child's birth. This was, properly speaking, the horoscope, the ascendant, or the first house, the whole circuit of the heavens being divided into 12 houses in which life and death, marriage and children, riches and honors, friends and enemies were distributed. We need not attempt to trace the progress of this science. It prevailed extensively among the Arabians, as we might expect from the character of that nation. Albumassar, of Balkh in Khorasan, who flourished in the 9th century, who was one of their greatest astronomers, was also a great astrologer, and his work on the latter subject, De Magnis Conjunctionibus, Anorum Revolutionibus AC Aerum Perfectionibus, was long celebrated in Europe. Abozen Halley, the writer of a treatise De Judices Astrorum, who lived in Spain in the 13th century, was one of the classical authors on this subject. It will easily be supposed that when this apotelesmatic or judicial astrology obtained firm possession of men's minds, it would be pursued into innumerable subtle distinctions and extravagant conceits, and the more so, as experience could offer little or no check to such exercises of fancy and subtlety. For the correction of rules of astrological divination by comparison with known events, though pretended to by many professors of the art, was far too vague and fallible a guidance to be of any real advantage. Even in what has been called natural astrology, the dependence of the weather on the heavenly bodies, it is easy to see what a vast accumulation of well-observed facts is requisite to establish 223 any true rule. And it is well known how long, in spite of facts, false and groundless rules, as the dependence of the weather on the moon, may keep their hold on men's minds. When the facts are such loose and many-sided things as human characters, passions, and happiness, it was hardly to be expected that even the most powerful minds should be able to find a footing sufficiently firm to enable them to resist the impression of a theory constructed of sweeping and bold assertions, and filled out into a complete system of details. Accordingly, the connection of the stars with human persons and actions was, for a long period, undisputed. The vague, obscure, and heterogeneous character of such a connection, and its unfitness for any really scientific reasoning, could, of course, never be got rid of, and the bewildering feeling of earnestness and solemnity, with which the connection of the heavens with man was contemplated, never died away. In other respects, however, the astrologers fell into a servile commentatorial spirit, and employed themselves in annotating and illustrating the works of their predecessors to a considerable extent before the revival of true science. It may be mentioned that astrology has long been, and probably is, an art held in great esteem and admiration among other Eastern nations besides the Mohammedans. For instance, the Jews, the Indians, the Siamese, and the Chinese. The prevalence of vague, visionary, and barren notions among these nations cannot surprise us, for with regard to them we have no evidence, as with regard to Europeans we have, that they are capable, on subjects of physical speculation, of originating sound and rational general principles. The arts may have had their birth in all parts of the globe, but it is only Europe, at particular favored periods of its history, which has ever produced sciences. We are, however, now speaking of a long period, during which this productive energy was interrupted and suspended. During this period, Europe descended, in intellectual character, to the level at which the other parts of the world have always stood. Her science was then a mixture of art and mysticism. We have considered several forms of this mysticism, but there are two others which must not pass unnoticed: alchemy and magic. We may observe before we proceed that the deep and settled influence which astrology had obtained among them appears perhaps most strongly in the circumstance that the most vigorous and clear-sighted minds which were concerned in the revival of science did not, for a long period, shake off the persuasion that there was, in this art, some element of truth. Roger Bacon, Cardan, Kepler, Tycho Brahe, 224 Francis Bacon are examples of this. These, or most of them, rejected all the more obvious and extravagant absurdities with which the subject had been loaded. but still conceived that some real and valuable truth remained when all these were removed. Thus Campanella, whom we shall have to speak of as one of the first opponents of Aristotle, wrote an astrology purified from all the superstitions of the Jews and Arabians and treated physiologically. Alchemy, like other kinds of mysticism, alchemy seems to have grown out of the notions of moral, personal, and mythological qualities, which men associated with terms, of which the primary application was to physical properties. This is the form in which the subject is presented to us in the earliest writings which we possess on the subject of chemistry, those of Geber of Seville, who is supposed to have lived in the 8th or 9th century. The very titles of Geber's works show the notions on which this pretended science proceeds. They are of the search of perfection, of the sum of perfection or of the perfect magistery, of the invention of verity or perfection. The basis of this phraseology is the distinction of metals into more or less perfect, gold being the most perfect, as being the most valuable, most beautiful, most pure, most durable, silver the next, and so on. The search of perfection was, therefore, the attempt to convert other metals into gold, and doctrines were adopted which represented the metals as all compounded of the same elements, so that this was theoretically possible. But the mystical trains of association were pursued much further than this. Gold and silver were held to be the most noble of metals. Gold was their king, and silver their queen. Mythological associations were called in aid of these fancies, as had been done in astrology. Gold was Sol, silver was Luna, the moon, copper, iron, tin, lead were assigned to Venus, Mars, Jupiter, Saturn. The processes of mixture and heat were spoken of as personal actions and relations, struggles and victories. Some elements were conquerors, some conquered. There existed preparations which possessed the power of changing the whole of a body into a substance of another kind. These were called magisteries. When gold and quicksilver are combined, the king and the queen are married to produce children of their own kind. It will easily be conceived that when chemical operations were described in phraseology of this sort, the enthusiasm of the 225 fancy would be added to that of the hopes, and observation would not be permitted to correct the delusion or to suggest sounder and more rational views. The exaggeration of the vague notion of perfection and power in the object of the alchemist's search was carried further still. The same preparation which possessed the faculty of turning baser metals into gold was imagined to be also a universal medicine, to have the gift of curing or preventing diseases, prolonging life, producing bodily strength and beauty. The philosopher's stone was finally invested with every desirable efficacy which the fancy of the philosophers could devise. It has been usual to say that alchemy was the mother of chemistry, and that men would never have made the experiments on which the real science is founded, if they had not been animated by the hopes and the energy which the delusive art inspired. To judge whether this is truly said, we must be able to estimate the degree of interest which men feel in purely speculative truth, and in the real and substantial improvement of art to which it leads. Since the fall of alchemy and the progress of real chemistry, these motives have been powerful enough to engage in the study of the science, a body far larger than the alchemists ever were, and no less zealous. There is no apparent reason why the result should not have been the same if the progress of true science had begun sooner. Astronomy was long cultivated without the bribe of astrology. But perhaps we may justly say this, that, in the stationary period, men's minds were so far enfeebled and degraded that pure speculative truth had not its full effect upon them. And the mystical pursuits in which some dim and disfigured images of truth were sought with avidity were among the provisions by which the human soul, even when sunk below its best condition, is perpetually directed to something above the mere objects of sense and appetite, a contrivance of compensation, as it were, in the intellectual and spiritual constitution of man. 5 magical arts, so far as they were believed in by those who profess to practice them, and so far as they have a bearing in science, stand on the same footing as astrology. And, indeed, a close alliance has generally been maintained between the two pursuits. Incapacity and indisposition to perceive natural and philosophical causation, an enthusiastic imagination, and such a faith as can devise and maintain supernatural and spiritual connections, are the elements of this, as of other forms of mysticism. And thus, that temper which led men to aim at the magician's supposed authority over the elements, 226 is an additional exemplification of those habits of thought which prevented the progress of real science, and the acquisition of that command over nature which is founded on science, during the interval now before us. But there is another aspect, under which the opinions connected with this pursuit may serve to illustrate the mental character of the stationary period. The tendency, during the Middle Ages, to attribute the character of magician to almost all persons eminent for great speculative or practical knowledge, is a feature of those times, which shows how extensive and complete was the inability to apprehend the nature of real science. In cultivated and enlightened periods, such as those of ancient Greece or modern Europe, knowledge is wished for and admired even by those who least possess it. But in dark and degraded periods, superior knowledge is a butt for hatred and fear. In the one case, men's eyes are open, their thoughts are clear, and however high the philosopher may be raised above the multitude, they can catch glimpses of the intervening path and see that it is free to all, and that elevation is the reward of energy and labor. In the other case, the crowd are not only ignorant, but spiritless. They have lost the pleasure in knowledge, the appetite for it, and the feeling of dignity which it gives. There is no sympathy which connects them with the learned man. They see him above them, but know not how he is raised or supported. He becomes an object of aversion and envy, of vague suspicion and terror. And these emotions are embodied and confirmed by association with the fancies and dogmas of superstition. To consider superior knowledge as magic, and magic as a detestable and criminal employment, was the form which these feelings of dislike assumed. And at one period in the history of Europe, almost everyone who had gained any eminent literary fame was spoken of as a magician. Nautius, a learned Frenchman in the 17th century, wrote an apology for all the wise men who have been unjustly reported magicians, from the creation to the present age. The list of persons whom he thus thinks it necessary to protect are of various classes and ages. Alkindi, Geber, Artephius, Thebet, Raymond Lully, Arnold de Villanova, Peter of Apono, and Paracelsus had incurred the black suspicion as physicians or alchemists. Thomas Aquinas, Roger Bacon, Michael Scott, Picus of Murrangula, and Trithemius had not escaped it, though ministers of religion. Even dignitaries, such as Robert Grosseteste, Bishop of Lincoln, Albertus Magnus, Bishop of Ratisbon, 227, Pope Sylvester II, and Gregory VII had been involved in the wide calumny. In the same way in which the vulgar confounded the eminent learning and knowledge which had appeared in recent times, with skill in dark and supernatural arts, they converted into wizards all the best-known names in the rolls of fame, as Aristotle, Solomon, Joseph, Pythagoras. And finally, the poet Virgil was a powerful and skillful necromancer, and this fancy was exemplified by many strange stories of his achievements and practices. The various results of the tendency of the human mind to mysticism, which we have here noticed, form prominent features in the intellectual character of the world for a long course of centuries. The theosophy and theurgy of the Neoplatonists, the mystical arithmetic of the Pythagoreans and their successors, the predictions of the astrologers, the pretenses of alchemy and magic, represent, not unfairly, the general character and disposition of men's thoughts with reference to philosophy and science. That there were stronger minds, which threw off in a greater or less degree this train of delusive and unsubstantial ideas, is true, as, on the other hand, mysticism, among the vulgar or the foolish, often went to an extent of extravagance and superstition, of which I have not attempted to convey any conception. The lesson which the preceding survey teaches us is that during the stationary period, mysticism, in its various forms, was a leading character, both of the common mind and of the speculations of the most intelligent and profound reasoners, and that this mysticism was the opposite of that habit of thought which we have stated science to require, namely, clear ideas distinctly employed to connect well-ascertained facts. Inasmuch as the ideas in which it dealt were vague and unstable, and the temper in which they were contemplated was an urgent and aspiring enthusiasm, which could not submit to a calm conference with experience upon even terms. The fervor of thought in some degree supplied the place of reason in producing belief, but opinions so obtained had no enduring value. They did not exhibit a permanent record of old truths, nor a firm foundation for new. Experience collected her stores in vain, or ceased to collect them, when she had only to pour them into the flimsy folds of the lap of mysticism. who was, in truth, so much absorbed in looking for the treasures which were to fall from the skies, that she heeded little how scantily she obtained, or how loosely she held, such riches as might be found near her. 228. Chapter 4. Of the dogmatism of the stationary period. In speaking of the character of the age of commentators, we noticed principally the ingenious servility which it displays, the acuteness with which it finds ground for speculation in the expression of other men's thoughts, the want of all vigor and fertility in acquiring any real and new truths. Such was the character of the reasoners of the stationary period from the first, but, at a later day, this character, from various causes, was modified by new features. The servility which had yielded itself to the yoke insisted upon forcing it on the necks of others. The subtlety which found all the truth it needed in certain accredited writings resolved that no one should find there, or in any other region, any other truths. Speculative men became tyrants without ceasing to be slaves. To their character of commentators, they added that of dogmatists. One origin of the scholastic philosophy. The causes of this change have been very happily analyzed and described by several modern writers. The general nature of the process may be briefly stated to have been the following. Note 62/4, Dr. Hampton in the Life of Thomas Aquinas in the Encyc. Metrop, Dejurando Hist, Compare Volume Roman 4, also Teneman Hist, of Phil, Volume Roman 8, Introduction. The tendencies of the later times of the Roman Empire to a commenting literature and a second-hand philosophy have already been noticed. The loss of the dignity of political freedom, the want of the cheerfulness of advancing prosperity, and the substitution of the less philosophical structure of the Latin language for the delicate intellectual mechanism of the Greek, fixed and augmented the prevalent feebleness and barrenness of intellect. Men forgot or feared to consult nature, to seek for new truths, to do what the great discoverers of other times had done. They were content to consult libraries, to study and defend old opinions, to talk of what great geniuses had said. They sought their philosophy in accredited treatises and dared not question such doctrines as they there found. The character of the philosophy to which they were thus led was determined by this want of courage and originality. There are various, 229 antagonist principles of opinion, which seem alike to have their root in the intellectual constitution of man, and which are maintained and developed by opposing sects when the intellect is in vigorous action. Such principles are, for instance, the claims of authority and of reason to our assent, the source of our knowledge in experience or in ideas, the superiority of a mystical or of a skeptical turn of thought. Such oppositions of doctrine were found in writers of the greatest fame, and two of those who most occupied the attention of students, Plato and Aristotle, were, on several points of this nature, very diverse from each other in their tendency. The attempt to reconcile these philosophers by Boethius and others we have already noticed, and the attempt was so far successful that it left on men's minds the belief in the possibility of a great philosophical system which should be based on both these writers, and have a claim to the assent of all sober speculators. But in the meantime, the Christian religion had become the leading subject of men's thoughts, and divines had put forward its claims to be, not merely the guide of men's lives, and the means of reconciling them to their heavenly master, but also to be a philosophy in the widest sense in which the term had been used, a consistent speculative view of man's condition and nature, and of the world in which he is placed. These claims had been acknowledged, and, unfortunately, from the intellectual condition of the times, with no due apprehension of the necessary ministry of observation, and reason dealing with observation, by which alone such a system can be embodied. It was held without any regulating principle that the philosophy which had been bequeathed to the world by the great geniuses of heathen antiquity, and the philosophy which was deduced from, and implied by, the revelations made by God to man, must be identical, and therefore that theology is the only true philosophy. Indeed, the Neoplatonists had already arrived, by other roads, at the same conviction. John Scott Erigena, in the reign of Alfred, and consequently before the existence of the scholastic philosophy, properly so called, had reasserted this doctrine. Anselm, in the 11th century, again brought it forward, and Bernard de Chartres in the 13th. This view was confirmed by the opinion which prevailed, Concerning the Nature of Philosophical Truth, a view supported by the theory 230 of Plato, the practice of Aristotle, and the general propensities of the human mind. I mean the opinion that all science may be obtained by the use of reasoning alone, that by analyzing and combining the notions which common language brings before us, we may learn all that we can know. Thus logic came to include the whole of science, and accordingly this Abelard expressly maintained. I have already explained, in some measure, the fallacy of this belief, which consists, as has been well said, in mistaking the universality of the theory of language for the generalization of facts. But on all accounts this opinion is readily accepted, and it led at once to the conclusion that the theological philosophy which we have described is complete as well as true. Thus, a universal science was established, with the authority of a religious creed. Its universality rested on erroneous views of the relation of words and truths. Its pretensions as a science were admitted by the servile temper of men's intellects, and its religious authority was assigned it by making all truth part of religion. And as religion claimed assent within her own jurisdiction under the most solemn and imperative sanctions, philosophy shared in her imperial power, and dissent from their doctrines was no longer blameless or allowable. Error became wicked, dissent became heresy. To reject the received human doctrines was nearly the same as to doubt the divine declarations. The scholastic philosophy claimed the assent of all believers. The external form, the details, and the text of this philosophy were taken, in a great measure, from Aristotle, though, in the spirit, the general notions, and the style of interpretation, Plato and the Platonists had no inconsiderable share. Various causes contributed to the elevation of Aristotle to this distinction. His logic had early been adopted as an instrument of theological disputation, and his spirit of systematization, of subtle distinction, and of analysis of words, as well as his disposition to argumentation, afforded the most natural and grateful employment to the commentating propensities. Those principles which we before noted as the leading points of his physical philosophy were selected and adopted, and these, presented in a most technical form, and applied in a systematic manner, constitute a large portion of the philosophy of which we now speak, so far as it pretends to deal with physics. Two scholastic dogmas but before the complete ascendancy of Aristotle was thus established, when something of an intellectual waking, 231, took place after the darkness and sleep of the 9th and 10th centuries, the Platonic doctrines seem to have had, at first, a strong attraction for men's minds, as better falling in with the mystical speculations and contemplative piety which belonged to the times. John Scott Erigena may be looked upon as the reviver of the new Platonism in the 10th century. Towards the end of the 11th, Peter Damian, in Italy, reproduced, involved in a theological discussion, some Neoplatonic ideas. Godfrey also, censor of Saint Victor, has left a treatise entitled Microcosmos. This is founded on a mystical analogy, often afterwards again brought forward, between man and the universe. Philosophers and theologians, says the writer, agree in considering man as a little world, and as the world is composed of 4 elements, man is endowed with 4 faculties: the senses, the imagination, reason, and understanding. Bernard of Chartres, in his Megascosmos and Microcosmos, took up the same notions. Hugo, abbot of St. Victor, made a contemplative life the main point and crown of his philosophy, and is said to have been the first of the scholastic writers who made psychology his special study. He says the faculties of the mind are the senses, the imagination, the reason, the memory, the understanding, and the intelligence. Physics does not originally and properly form any prominent part of the scholastic philosophy, which consists mainly of a series of questions and determinations upon the various points of a certain technical divinity. Of this kind is the Book of Sentences of Peter the Lombard, Bishop of Paris, who is, on that account, usually called Magister Sententiarum, a work which was published in the 12th century and was long the text and standard of such discussions. The questions are decided by the authority of Scripture and of the Fathers of the Church, and are divided into 4 books, of which the first contains questions concerning God and the doctrine of the Trinity in particular. The second is concerning the creation. The third, concerning Christ and the Christian religion, and the fourth treats of religious and moral duties. In the second book, As in many of the writers of this time, the nature of angels is considered in detail, and the orders of their hierarchy, of which there were held to be 9. The physical discussions enter only as bearing upon the scriptural history of the creation and cannot be taken as a specimen of the work. But I may observe that in speaking of the division of the waters above the 232 firmament, he gives one opinion, that of Bede, that the former waters are the solid crystalline heavens in which the stars are fixed. For crystal, which is so hard and transparent, is made of water. But he mentions also the opinion of St. Augustine, that the waters above the heavens are in a state of vapor, vaporyliter, and in minute drops. If, then, water can, as we see in clouds, be so minutely divided that it may be thus supported as vapor on air, which is naturally lighter than water, why may we not believe that it floats above that lighter celestial element in still minuter drops and still lighter vapors? But in whatever manner the waters are there, we do not doubt that they are there. The celebrated Summa Theologicae of Thomas Aquinas is a work of the same kind, and anything which has a physical bearing forms an equally small part of it. Thus, of the 512 questions of the Summa, there is only one Part 1 quest. 115, on corporeal action, or on any part of the material world, though there are several concerning the celestial hierarchies, as on the act of angels, on the speaking of angels, on the subordination of angels, on guardian angels, and the like. This, of course, would not be remarkable in a treatise on theology, except this theology were intended to constitute the whole of philosophy. We may observe that in this work, though Plato, Avicebron, and many other heathen as well as Christian philosophers are adduced as authority, Aristotle is referred to in a peculiar manner as the philosopher. This is noticed by John of Salisbury as attracting attention in his time. He died A.D. 1182. The various masters of dialectic, says he, shine each with his peculiar merit, but all are proud to worship the footsteps of Aristotle, so much so, indeed, that the name of philosopher, which belongs to them all, has been preeminently appropriated to him. He is called the philosopher autonomatus, that is, by excellence. The question concerning corporeal action in Aquinas is divided into 6 articles, and the conclusion delivered upon the first is that body being compounded of power and act is active as well as passive. Against this it is urged that quantity is an attribute of body, and that quantity prevents action, that this appears in fact, since a larger body is more difficult to move. The author replies that 233, quantity does not prevent corporeal form from action altogether, but prevents it from being a universal agent, inasmuch as the form is individualized, which, in matter subject to quantity, it is. Moreover, the illustration deduced from the ponderousness of bodies is not to the purpose. First, because the addition of quantity is not the cause of gravity, as is proved in the 4th book, De Cielo and De Mundo, we see that he quotes familiarly the physical treatises of Aristotle. Second, because it is false that ponderousness makes motion slower. On the contrary, in proportion as anything is heavier, the more does it move with its proper motion. Thirdly, because action does not take place by local motion, as Democritus asserted, but by this, that something is drawn from power into act. It does not belong to our purpose to consider either the theological or the metaphysical doctrines, which form so large a portion of the treatises of the schoolmen. Perhaps it may hereafter appear that some light is thrown on some of the questions which have occupied metaphysicians in all ages, by that examination of the history of the progressive sciences in which we are now engaged. But till we are able to analyze the leading controversies of this kind, it would be of little service to speak of them in detail. It may be noticed, however, that many of the most prominent of them refer to the great question: what is the relation between actual things and general terms? Perhaps in modern times, the actual things would be more commonly taken as the point to start from, and men would begin by considering how classes and universals are obtained from individuals. But the schoolmen, founding their speculations on the received modes of considering such subjects, to which both Aristotle and Plato had contributed, traveled in the opposite direction, and endeavored to discover how individuals were deduced from genera and species, what was the principle of individuation. This was variously stated by different reasoners. Thus, Bonaventura solves the difficulty by the aid of the Aristotelian distinction of matter and form. The individual derives from the form the property of being something, and from the matter the property of being that particular thing. Duns Scotus, the great adversary of Thomas Aquinas in theology, placed the principle of individuation in a certain determining positive entity, which his school called haecceity or thisness. Thus an individual man is Peter, because his humanity is combined with petrity. The force 234 of abstract terms is a curious question, and some remarkable experiments in their use had been made by the Latin Aristotelians before this time. In the same way in which we talk of the quantity and quality of a thing, they spoke of its quiddity. We may consider the reign of mere disputation as fully established at the time of which we are now speaking, and the only kind of philosophy henceforth studied was one in which no sound physical science had or could have a place. The wavering abstractions, indistinct generalizations, and loose classifications of common language, which we have already noted as the fountain of the physics of the Greek schools of philosophy, were also the only source from which the schoolmen of the Middle Ages drew their views, or rather their arguments. And though these notional and verbal relations were invested with a most complex and pedantic technicality, they did not, on that account, become at all more precise as notions, or more likely to lead to a single real truth. Instead of acquiring distinct ideas, they multiplied abstract terms. Instead of real generalizations, they had recourse to verbal distinctions. The whole course of their employments tended to make them, not only ignorant of physical truth, but incapable of conceiving its nature. Having thus taken upon themselves the task of raising and discussing questions by means of abstract terms, verbal distinctions, and logical rules alone, there was no tendency in their activity to come to an end, as there was no progress. The same questions, the same answers, the same difficulties, the same solutions, the same verbal subtleties sought for, admired, cavilled at, abandoned, reproduced, and again admired might recur without limit. John of Salisbury observes of the Parisian teachers that, after several years' absence, he found them not a step advanced, and still employed in urging and parrying the same arguments, and this, as Mr. Hallam remarks, was equally applicable to the period of centuries. The same knots were tied, and 235 untied, the same clouds were formed and dissipated. The poet's censure of the sons of Aristotle is just as happily expressed. They stand locked up together hand in hand, every one leads as he is led, the same bare path they tread, and dance like fairies a fantastic round, but neither change their motion nor their ground. Note 79/4. He studied logic at Paris, at St. Genevieve, and then left them. Duut senium mihi elapsum est diversis studiis occupatum. Jucundum idac visum est vetters quos reliquaram, et quos ad hoc dialectica detinebat in Monti, Sancti Genofi, revisor socios, confera cum eis super ambiguitatibus pristinis, ut nostrum invisum collation mudua commedhirmer proftum. Inventi sunt, qui furent, et ubi, nec enim ad pomum visi sunt processus ad questions pristinis dirimendas, nec propositionculam unum adjacurrent. Quibus urgibant stimulis aestum et ipsi urgibanter, and c. Metallogicus, lib Roman 2. Cap. 10. It will therefore be unnecessary to go into any detail respecting the history of the school philosophy of the 13th, 14th, and 15th centuries. We may suppose it to have been, during the intermediate time, such as it was at first and at last. An occasion to consider its later days will be brought before us by the course of our subject. But even during the most entire ascendancy of the scholastic doctrines, the elements of change were at work. While the doctors and the philosophers received all the ostensible homage of men, a doctrine and a philosophy of another kind were gradually forming. The practical instincts of man, their impatience of tyranny, the progress of the useful arts, the promises of alchemy, were all disposing men to reject the authority and deny the pretensions of the received philosophical creed. Two antagonist forms of opinion were in existence, which for some time went on detached and almost independent of each other. But finally, these came into conflict at the time of Galileo, and the war speedily extended to every part of civilized Europe. 3. Scholastic physics. It is difficult to give briefly any appropriate examples of the nature of the Aristotelian physics which are to be found in the works of this time. As the gravity of bodies was one of the first subjects of dispute when the struggle of the rival methods began, we may notice the mode in which it was treated. Zabarella maintains that the proximate cause of the motion of elements is the form, in the Aristotelian sense of the term. But to this sentence we, says Keckerman, cannot agree, for in all other things the form is the proximate cause, not of the act, but of the power or faculty from which the act flows. Thus, in man, the rational soul is not the cause of the act of laughing, but of the risible faculty or power. Keckerman's system was at one time a work of considerable authority. It was published in 1614. By comparing and systematizing what he finds in Aristotle, he is led to state his results in the form of definitions, 236, and theorems. Thus, gravity is a motive quality, arising from cold, density, and bulk, by which the elements are carried downwards. Water is the lower, intermediate element, cold and moist. The first theorem concerning water is, the moistness of the water is controlled by its coldness, so that it is less than the moistness of the air, though, according to the sense of the vulgar, water appears to moisten more than air. It is obvious that the two properties of fluids, to have their parts easily moved, and to wet other bodies, are here confounded. I may, as a concluding specimen of this kind, mention those propositions or maxims concerning fluids, which were so firmly established, that, when Boyle propounded the true mechanical principles of fluid action, he was obliged to state his opinions as hydrostatical paradoxes. These were that fluids do not gravitate in propria loco. That is, that water has no gravity in or on water, since it is in its own place. That air has no gravity on water, since it is above water, which is its proper place. That earth in water tends to descend, since its place is below water. That the water rises in a pump or siphon, because nature abhors a vacuum. That some bodies have a positive levity in others, as oil in water, and the like. Authority of Aristotle among the schoolmen, the authority of Aristotle, and the practice of making him the text and basis of the system, especially as it regarded physics, prevailed during the period of which we speak. This authority was not, however, without its fluctuations. Lon has traced one part of its history in a book on the various fortune of Aristotle in the University of Paris. The most material turns of this fortune depend on the bearing which the works of Aristotle were supposed to have upon theology. Several of Aristotle's works, and more especially his metaphysical writings, had been translated into Latin and were explained in the schools of the University of Paris as early as the beginning of the 13th century. At a council held at Paris in 1209, they were prohibited, as having given occasion to the heresy of Almeric or Amori, and because they might give occasion to other heresies not yet invented. The logic of Aristotle recovered its credit some years after this, and was publicly taught in the University of Paris in the year 1215. But the natural philosophy and metaphysics were prohibited by a decree of Gregory IX in 1231. The Emperor Frederick II employed a number of learned men to translate into Latin, from the Greek and 237 Arabic, certain books of Aristotle and of other ancient sages. And we have a letter of Peter de Vineis, in which they are recommended to the attention of the University of Bologna. Probably the same recommendation was addressed to other universities. Both Albertus Magnus and Thomas Aquinas wrote commentaries on Aristotle's works, and as this was done soon after the decree of Gregory IX, Lano is much perplexed to reconcile the fact with the orthodoxy of the two doctors. Campanella, who was one of the first to cast off the authority of Aristotle, says, "We are by no means to think that St. Thomas Aristotelized. He only expounded Aristotle, that he might correct his errors, and I should conceive he did this with the license of the Pope." This statement, however, by no means gives a just view of the nature of Albertus's and Aquinas's commentaries. Both have followed their author with profound deference. For instance, Aquinas attempts to defend Aristotle's assertion that if there were no resistance, a body would move through a space in no time, and the same defense is given by Scotus. We may imagine the extent of authority and admiration which Aristotle would attain when thus countenanced both by the powerful and the learned. In universities, no degree could be taken without a knowledge of the philosopher. In 1452, Cardinal Todorel established this rule in the University of Paris. When Ramus, in 1543, published an attack upon Aristotle, it was repelled by the power of the court and the severity of the law. Francis I published an edict in which he states that he had appointed certain judges, who had been of opinion, quelidit remus avoit ete temerare, arrogant et impudent, etque parsequin sun liver des animadversions, ill reprenate Aristotle, estate avidement, canu et manifest sun ignorance. The books are then declared to be suppressed. It was often a complaint of pious men that theology was corrupted by the influence of Aristotle and his commentators. Petrarch says that one of the Italian learned men conversing with him, after expressing much contempt for the apostles and fathers, exclaimed, Utinam tu averon patipasses, ut viters quanto aletuis his nugatoribus major sit. When the revival of letters began to take place, and a number of men of ardent and elegant minds, susceptible to the impressions of beauty of style and dignity of thought, were brought into contact with Greek literature, Plato had naturally greater charms for them. A 238, powerful school of Platonists, not Neoplatonists, was formed in Italy, including some of the principal scholars and men of genius of the time, as Picus of Murrangula in the middle, Marsilius Ficinus at the end, of the 15th century. At one time, it appeared as if the ascendancy of Aristotle was about to be overturned, but in physics at least, his authority passed unshaken through this trial. It was not by disputation that Aristotle could be overthrown, and the Platonists were not persons whose doctrines led them to use the only decisive method in such cases, the observation and unfettered interpretation of facts. The history of their controversies, therefore, does not belong to our design. For like reasons we do not here speak of other authors who opposed the scholastic philosophy on general theoretical grounds of various kinds. Such examples of insurrection against the dogmatism which we have been reviewing are extremely interesting events in the history of the philosophy of science. But in the present work, we are to confine ourselves to the history of science itself, in the hope that we may thus be able hereafter to throw a steadier light upon that philosophy by which the succession of stationary and progressive periods, which we are here tracing, may be in some measure explained. We are now to close our account of the stationary period, and to enter upon the great subject of the progress of physical science in modern times. 5 subjects omitted. Civil law, medicine. My object has been to make my way as rapidly as possible to this period of progress, and in doing this, I have had to pass over a long and barren track, where almost all traces of the right road disappear. In exploring this region, it is not without some difficulty that he who is traveling with objects such as mine continues a steady progress in the proper direction. For many curious and attractive subjects of research come in his way. He crosses the track of many a controversy, which in its time divided the world of speculators, and of which the results may be traced, even now, in the conduct of moral or political or metaphysical discussions, or in the common associations of thought and forms of language. The wars of the nominalists and realists, the disputes concerning the foundations of morals and the motives of human actions, the controversies concerning predestination, free will, grace, and the many other points of metaphysical divinity, the influence of theology and metaphysics upon each other and upon other subjects of human curiosity, the effects of opinion upon politics and of political condition upon opinion, the influence of literature and philosophy, 239, upon each other and upon society, and many other subjects, might be well worth examination if our hope of success did not reside in pursuing, steadily and directly, those inquiries in which we can look for a definite and certain reply. We must even neglect 2 of the leading studies of those times, which occupied much of men's time and thoughts, and had a very great influence on society, the one dealing with notions, the other with things, the one employed about moral rules, the other about material causes, but both for practical ends. I mean the study of the civil law and of medicine. The second of these studies will hereafter come before us, as one of the principal occasions which led to the cultivation of chemistry. But in itself, its progress is of too complex and indefinite a nature to be advantageously compared with that of the more exact sciences. The Roman law is held, by its admirers, to be a system of deductive science, as exact as the mathematical sciences themselves, and it may, therefore, be useful to consider it, if we should, in the sequel, have to examine how far there can exist an analogy between moral and physical science. But after a few more words on the Middle Ages, we must return to our task of tracing the progress of the latter. Chapter 5. Progress of the Arts in the Middle Ages. Art and science. I shall, before I resume the history of science, say a few words on the subject described in the title of this chapter, both because I might otherwise be accused of doing injustice to the period now treated of, and also because we shall by this means bring under our notice some circumstances which were important as being the harbingers of the revival of progressive knowledge. The accusation of injustice towards the state of science in the Middle Ages, if we were to terminate our survey of them with what has hitherto been said, might be urged from obvious topics. How do we recognize, it might be asked, in a picture of mere confusion and mysticism of thought, of servility and dogmatism of character, the powers and acquirements to which we owe so many of the most important inventions which we now enjoy? Parchment and paper, printing and engraving, improved glass and steel, gunpowder, clocks, telescopes, 240 the mariner's compass, the reformed calendar, the decimal notation, algebra, trigonometry, chemistry, counterpoint, an invention equivalent to a new creation of music. These are all possessions which we inherit from that which has been so disparagingly termed the stationary period. Above all, let us look at the monuments of architecture of this period, the admiration and the despair of modern architects, not only for their beauty, but for the skill disclosed in their construction. With all these evidences before us, how can we avoid allowing that the masters of the Middle Ages not only made some small progress in astronomy, which has, grudgingly as it would seem, been admitted in a former book, but also that they were no small proficients in other sciences, in optics, in harmonics, in physics, and, above all, in mechanics? If it may be added, we are allowed in the present day to refer to the perfection of our arts as evidence of the advanced state of our physical philosophy. If our steam engines, our gas illumination, our buildings, our navigation, our manufactures are cited as triumphs of science, shall not prior inventions, made under far heavier disadvantages, shall not greater works produced in an earlier state of knowledge also be admitted as witnesses that the Middle Ages had their share, and that not a small or doubtful one, of science? To these questions I answer by distinguishing between art and science in that sense of general inductive systematic truth which it bears in this work. To separate and compare with precision these two processes belongs to the philosophy of induction, and the attempt must be reserved for another place. But the leading differences are sufficiently obvious. Art is practical, science is speculative. The former is seen in doing, the latter rests in the contemplation of what is known. The art of the builder appears in his edifice, though he may never have meditated on the abstract propositions on which its stability and strength depends. The science of the mathematical mechanician consists in his seeing that, under certain conditions, bodies must sustain each other's pressure, though he may never have applied his knowledge in a single case. Now the remark which I have to make is this: in all cases the arts are prior to the related sciences. Art is the parent, not the progeny, of science. The realization of principles in practice forms part of the prelude, as well as of the sequel, of theoretical discovery. And thus the inventions of the Middle Ages, which have been above enumerated, though at the present day they may be portions of our sciences, are no evidence that the sciences then existed, but only that 241, those powers of practical observation and practical skill were at work, which prepare the way for theoretical views and scientific discoveries. It may be urged that the great works of art do virtually take for granted principles of science, and that, therefore, it is unreasonable to deny science to great artists. It may be said that the grand structures of Cologne, or Amiens, or Canterbury could not have been erected without a profound knowledge of mechanical principles. To this we reply that such knowledge is manifestly not of the nature of that which we call science. If the beautiful and skillful structures of the Middle Ages prove that mechanics then existed as a science, mechanics must have existed as a science also among the builders of the Cyclopean walls of Greece and Italy, or of our own Stonehenge. For the masses which are there piled on each other could not be raised without considerable mechanical skill. But we may go much further. The actions of every man who raises and balances weights or walks along a pole take for granted the laws of equilibrium, and even animals constantly avail themselves of such principles. Are these, then, acquainted with mechanics as a science? Again, if actions which are performed by taking advantage of mechanical properties prove a knowledge of the science of mechanics, they must also be allowed to prove a knowledge of the science of geometry when they proceed on geometrical properties. But the most familiar actions of men and animals proceed upon geometrical truths. The Epicureans held, as Proclus informs us, that even asses knew that two sides of a triangle are greater than the third. And animals may truly be said to have a practical knowledge of this truth, but they have not, therefore, a science of geometry. And in like manner among men, if we consider the matter strictly, a practical assumption of a principle does not imply a speculative knowledge of it. We may, in another way also, show how inadmissible are the works of the master artists of the Middle Ages into the series of events which mark the advance of science. The following maxim is applicable to a history, such as we are here endeavoring to write. We are employed in tracing the progress of such general principles as constitute each of the sciences which we are reviewing, and no facts or subordinate truths belong to our scheme, except so far as they tend to or are included in these higher principles. Nor are they important to us, any further than as they prove such principles. Now, with regard to processes of art like those which we have referred to, namely, the inventions of the Middle Ages, let us ask, what principle each of them, 242, illustrates? What chemical doctrine rests for its support on the phenomena of gunpowder, or glass, or steel? What new harmonical truth was illustrated in the Gregorian chant? What mechanical principle unknown to Archimedes was displayed in the printing press? The practical value and use, the ingenuity and skill of these inventions is not questioned, but what is their place in the history of speculative knowledge? Even in those cases in which they enter into such a history, how minute a figure do they make? How great is the contrast between their practical and theoretical importance? They may in their operation have changed the face of the world, but in the history of the principles of the sciences to which they belong, they may be omitted without being missed. As to that part of the objection which was stated by asking, why, if the arts of our age prove its scientific eminence, the arts of the Middle Ages should not be received as proof of theirs, we must reply to it by giving up some of the pretensions which are often put forwards on behalf of the science of our times. The perfection of the mechanical and other arts among us proves the advanced condition of our sciences, only in so far as these arts have been perfected by the application of some great scientific truth, with a clear insight into its nature. The greatest improvement of the steam engine was due to the steady apprehension of an atmological doctrine by Watt. But what distinct theoretical principle is illustrated by the beautiful manufactures of porcelain, or steel, or glass? A chemical view of these compounds, which would explain the conditions of success and failure in their manufacture, would be of great value in art, and it would also be a novelty in chemical theory. So little is the present condition of those processes a triumph of science, shedding intellectual glory on our age. And the same might be said of many, or of most, of the processes of the arts as now practiced. 2. Arabian science having, I trust, established the view I have stated, respecting the relation of art and science, we shall be able very rapidly to dispose of a number of subjects which otherwise might seem to require a detailed notice. Though this distinction has been recognized by others, it has hardly been rigorously adhered to in consequence of the indistinct notion of science which has commonly prevailed. Thus Gibbon, in speaking of the knowledge of the period now under our notice, says, "Much useful experience had been acquired in 243, the practice of arts and manufactures. But the science of chemistry owes its origin and improvement to the industry of the Saracens. They," he adds, "first invented and named the alembic for the purposes of distillation, analyzed the substances of the three kingdoms of nature, tried the distinction and affinities of alkalis and acids, and converted the poisonous minerals into soft and salutary medicines. The formation and realization of the notions of analysis and of affinity were important steps in chemical science, which, as I shall hereafter endeavor to show, it remained for the chemists of Europe to make at a much later period. If the Arabians had done this, they might with justice have been called the authors of the science of chemistry, but no doctrines can be adduced from their works which give them any title to this eminent distinction. Their claims are dissipated at once by the application of the maxim above stated. What analysis of theirs tended to establish any received principle of chemistry? What true doctrine concerning the differences and affinities of acids and alkalis did they teach? We need not wonder if Gibbon, whose views of the boundaries of scientific chemistry were probably very wide and indistinct, could include the arts of the Arabians within its domain. But they cannot pass the frontier of science if philosophically defined and steadily guarded. The judgment which we are thus led to form respecting the chemical knowledge of the Middle Ages, and of the Arabians in particular, may serve to measure the condition of science in other departments. For chemistry has justly been considered one of their strongest points. In botany, anatomy, zoology, optics, acoustics, we have still the same observations to make, that the steps in science which, in the order of progress, next followed what the Greeks had done, were left for the Europeans of the 16th and 17th centuries. The merits and advances of the Arabian philosophers in astronomy and pure mathematics we have already described. 3. Experimental philosophy of the Arabians. The estimate, to which we have thus been led, of the scientific merits of the learned men of the Middle Ages, is much less exalted than that which has been formed by many writers, and, among the rest, by some of our own time. But I am persuaded that any attempt to answer the questions just asked will expose the untenable nature of the higher claims which have been advanced in favor of the Arabians. We can deliver no just decision, except we will consent to use the terms of science in a strict and precise sense. And if we do this, we shall find little, either in the 244 particular discoveries or general processes of the Arabians, which is important in the history of the inductive sciences. Note 89/4. If I might take the liberty of criticizing an author who has given a very interesting view of the period in question, Mahomedanism Unveiled, by the Reverend Charles Forster, 1829, I would remark that in his work this caution is perhaps too little observed. Thus, he says, in speaking of Alhazen, volume Roman 2, p. 270, the theory of the telescope may be found in the work of this astronomer, and of another, the uses of magnifying glasses and telescopes, and the principle of their construction, are explained in the great work of Roger Bacon, with a truth and clearness which have commanded universal admiration. Such phrases would be much too strong, even if used respecting the optical doctrines of Kepler, which were yet incomparably more true and clear than those of Bacon. To employ such language, in such cases, is to deprive such terms as theory and principle of all meaning. The credit due to the Arabians for improvements in the general methods of philosophizing is a more difficult question, and cannot be discussed at length by us till we examine the history of such methods in the abstract, which, in the present work, it is not our intention to do. But we may observe that we cannot agree with those who rank their merits high in this respect. We have already seen that their minds were completely devoured by the worst habits of the stationary period mysticism and commentation. They followed their Greek leaders, for the most part, with abject servility, and with only that kind of acuteness and independent speculation which the commentator's vocation implies. And in their choice of the standard subjects of their studies, they fixed upon those works, the physical books of Aristotle, which have never promoted the progress of science, except in so far as they incited men to refute them, an effect which they never produced on the Arabians. That the Arabian astronomers made some advances beyond the Greeks, we have already stated. The two great instances are the discovery of the motion of the sun's apogee by Albaicneus, and the discovery, recently brought to light, of the existence of the moon's second inequality by Abul-Weffa. But we cannot but observe in how different a manner they treated these discoveries from that with which Hipparchus or Ptolemy would have done. The variation of the moon, in particular, instead of being incorporated into the system by means of an epicycle, as Ptolemy had done with the evection, was allowed, almost immediately, so far as we can judge, to fall into neglect and oblivion. So little were the learned Arabians prepared to take their lessons from observation as well as from books, that in many subjects they made experiments may easily be allowed. There never was a period of the earth's history, and least of all a period of commerce, 245, and manufactures, luxury, and art, medicine, and engineering, in which there were not going on innumerable processes, which may be termed experiments. And in addition to these, the Arabians adopted the pursuit of alchemy and the love of exotic plants and animals. But so far from their being, as has been maintained, a people whose experimental intellect fitted them to form sciences which the abstract intellect of the Greeks failed in producing, it rather appears that several of the sciences which the Greeks had founded were never even comprehended by the Arabians. I do not know any evidence that these pupils ever attained to understand the real principles of mechanics, hydrostatics, and harmonics, which their masters had established. At any rate, when these sciences again became progressive, Europe had to start where Europe had stopped. There is no Arabian name which anyone has thought of interposing between Archimedes the ancient and Stevinus and Galileo the moderns. Roger Bacon there is one writer of the Middle Ages on whom much stress has been laid, and who was certainly a most remarkable person. Roger Bacon's works are not only so far beyond his age in the knowledge which they contain, but so different from the temper of the times, in his assertion of the supremacy of experiment, and in his contemplation of the future progress of knowledge, that it is difficult to conceive how such a character could then exist. That he received much of his knowledge from Arabic writers, there can be no doubt, for they were in his time the repositories of all traditionary knowledge. But that he derived from them his disposition to shake off the authority of Aristotle, to maintain the importance of experiment, and to look upon knowledge as in its infancy, I cannot believe, because I have not myself hit upon, nor seen quoted by others, any passages in which Arabian writers express such a disposition. On the other hand, we do find in European writers, in the authors of Greece and Rome, the solid sense, the bold and hopeful spirit, which suggest such tendencies. We have already seen that Aristotle asserts, as distinctly as words can express, that all knowledge must depend on observation, and that science must be collected from facts by induction. We have seen, too, that the Roman writers, and Seneca in particular, speak with an enthusiastic confidence of the progress which science must make in the course of ages. When Roger Bacon holds similar language in the 13th century, the resemblance is probably rather a sympathy of character than a matter of direct derivation. But I know of nothing 246 which proves even so much as this sympathy in the case of Arabian philosophers. A good deal has been said of late of the coincidences between his views and those of his great namesake in later times, Francis Bacon. The resemblances consist mainly in such points as I have just noticed, and we cannot but acknowledge that many of the expressions of the Franciscan friar remind us of the large thoughts and lofty phrases of the philosophical chancellor. How far the one can be considered as having anticipated the method of the other, we shall examine more advantageously when we come to consider what the character and effect of Francis Bacon's works really are. Note 91/4, Hallam's Middle Ages, Roman 3, 549, Forster's Maham, U. Roman 2, 313. Note 92/4, in the philosophy of the Inductive Sciences, I have given an account at considerable length of Roger Bacon's mode of treating arts and sciences, and have also compared more fully his philosophy with that of Francis Bacon, and I have given a view of the bearing of this latter upon the progress of science in modern times. See Phil. Ind. Sc. Book 12, Chaps. 7 and 11. See also the appendix to this volume. 5. Architecture of the Middle Ages. But, though we are thus compelled to disallow several of the claims which have been put forwards in support of the scientific character of the Middle Ages, there are 2 points in which we may, I conceive, really trace the progress of scientific ideas among them, and which, therefore, may be considered as the prelude to the period of discovery. I mean their practical architecture and their architectural treatises. In a previous chapter of this book, we have endeavored to explain how the indistinctness of ideas, which attended the decline of the Roman Empire, appears in the forms of their architecture, in the disregard which the decorative construction exhibits of the necessary mechanical conditions of support. The original scheme of Greek ornamental architecture had been horizontal masses resting on vertical columns. When the arch was introduced by the Romans, it was concealed or kept in a state of subordination, and the lateral support which it required was supplied latently, marked by some artifice. But the struggle between the mechanical and the decorative construction ended in the complete disorganization of the classical style. The 247 inconsistencies and extravagances of which we have noticed the occurrence were results and indications of the fall of good architecture. The elements of the ancient system had lost all principle of connection and regard to rule. Building became not only a mere art, but an art exercised by masters without skill and without feeling for real beauty. Note 93/4. See Mr. Willis's admirable remarks on the architecture of the Middle Ages, chapter Roman 2. Since the publication of my first edition, Mr. Willis has shown that much of the mason craft of the Middle Ages consisted in the geometrical methods, by which the artists wrought out of the blocks the complex forms of their decorative system. To the general indistinctness of speculative notions on mechanical subjects prevalent in the Middle Ages, there may have been some exceptions, and especially so long as there were readers of Archimedes. Boethius had translated the mechanical works of Archimedes into Latin, as we learn from the enumeration of his works by his friend Cassiodorus, Verrier. Lib. I. Cap. 45, Mechanica Metium Archimedum Latialum Siculis Redidisti. But mechanicus was used in those times rather for one skilled in the art of constructing wonderful machines than in the speculative theory of them. The letter from which the quotation is taken is sent by King Theodoric to Boethius to urge him to send the king a water clock. When, after this deep decline, architecture rose again, as it did in the 12th and succeeding centuries, in the exquisitely beautiful and skillful forms of the Gothic style, what was the nature of the change which had taken place, so far as it bears upon the progress of science? It was this: the idea of true mechanical relations in an edifice had been revived in men's minds, as far as was requisite for the purposes of art and beauty. And this, though a very different thing from the possession of the idea as an element of speculative science, was the proper preparation for that acquisition. The notion of support and stability again became conspicuous in the decorative construction and universal in the forms of building. The eye which, looking for beauty in definite and significant relations of parts, is never satisfied except the weights appear to be duly supported, was again gratified. Architecture threw off its barbarous characters. A new decorative construction was matured, not thwarting and controlling, but assisting and harmonizing with the mechanical construction. All the ornamental parts were made to enter into the apparent construction. Every member, almost every molding, became a sustainer of weight, and by the multiplicity of props assisting each other and the consequent subdivision of weight, the eye was satisfied of the stability of the structure, notwithstanding the curiously slender forms of the separate parts. The arch and the vault, no longer trammeled by an incompatible system of decoration, but favored by more tractable forms, were only limited by the skill of the builders. Everything showed that, practically at least, men possessed and applied, with steadiness and pleasure, the idea of mechanical pressure and support. Note 94/4. Willis, pp. 1521. I have throughout this description of the formation of the Gothic style availed myself of Mr. Willis's well-chosen expressions. The possession of this idea, as a principle of art, led in the course of time to its speculative development as the foundation of a science. 248, and thus architecture prepared the way for mechanics. But this advance required several centuries. The interval between the admirable cathedrals of Salisbury, Amiens, Cologne, and the mechanical treatises of Stevinus is not less than 300 years. During this time, men were advancing towards science. But in the meantime, and perhaps from the very beginning of the time, art had begun to decline. The buildings of the 15th century, erected when the principles of mechanical support were just on the verge of being enunciated in general terms, exhibit those principles with a far less impressive simplicity and elegance than those of the 13th. We may hereafter inquire whether we find any other examples to countenance the belief that the formation of science is commonly accompanied by the decline of art. The leading principle of the style of the Gothic edifices was, not merely that the weights were supported, but that they were seen to be so, and that not only the mechanical relations of the larger masses, but of the smaller members also, were displayed. Hence we cannot admit, as an origin or anticipation of the Gothic, a style in which this principle is not manifested. I do not see, In any of the representations of the early Arabic buildings, that distribution of weights to supports and that mechanical consistency of parts, which would elevate them above the character of barbarous architecture. Their masses are broken into innumerable members, without subordination or meaning, in a manner suggested apparently by caprice and the love of the marvelous. In the construction of their mosques, it was a favorite artifice of the Arabs to sustain immense and ponderous masses of stone by the support of pillars so slender that the incumbent weight seemed, as it were, suspended in the air by an invisible hand. This pleasure in the contemplation of apparent impossibilities is a very general disposition among mankind, but it appears to belong to the infancy rather than the maturity of intellect. On the other hand, the pleasure in the contemplation of what is clear, the craving for a thorough insight into the reasons of things, which marks the European mind, is the temper which leads to science. Treatises on architecture know one who has attended to the architecture which prevailed in England, France, and Germany from the 12th to the 15th century, so far as to comprehend its beauty, harmony, consistency, and uniformity, even in the minutest parts and most obscure relations, can look upon it otherwise than as a 249 remarkably connected and definite artificial system. Nor can we doubt that it was exercised by a class of artists who formed themselves by laborious study and practice, and by communication with each other. There must have been bodies of masters and of scholars, discipline, traditions, precepts of art. How these associated artists diffused themselves over Europe, and whether history enables us to trace them in a distinct form, I shall not here discuss. But the existence of a course of instruction, and of a body of rules of practice, is proved beyond dispute by the great series of European cathedrals and churches, so nearly identical in their general arrangements and in their particular details. The question then occurs, have these rules and this system of instruction anywhere been committed to writing? Can we, by such evidence, trace the progress of the scientific idea of which we see the working in these buildings? We are not to be surprised if, during the most flourishing and vigorous period of the art of the Middle Ages, we find none of its precepts in books. Art has, in all ages and countries, been taught and transmitted by practice and verbal tradition, not by writing. It is only in our own times that the thought occurs as familiar, of committing to books all that we wish to preserve and convey. And even in our own times, most of the arts are learned far more by practice, and by intercourse with practitioners than by reading. Such is the case, not only with manufactures and handicrafts, but with the fine arts, with engineering, and even yet with that art, building, of which we are now speaking. We are not, therefore, to wonder if we have no treatises on architecture belonging to the great period of the Gothic masters, or if it appears to have required some other incitement and some other help, besides their own possession of their practical skill, to lead them to shape into a literary form the precepts of the art which they knew so well how to exercise, or if, when they did write on such subjects, they seem, instead of delivering their own sound practical principles, to satisfy themselves with pursuing some of the frivolous notions and speculations which were then current in the world of letters. Such appears to be the case. The earliest treatises on architecture come before us under the form which the commentatorial spirit of the Middle Ages inspired. They are translations of Vitruvius, with annotations. In some of these, particularly that of Cesare Cesariano, published at Como in 1521, we see, in a very curious manner, how the habit of assuming that, in every department of literature, the ancients, 250, must needs be their masters, led these writers to subordinate the members of their own architecture to the precepts of the Roman author. We have Gothic shafts, moldings, and arrangements given as parallelisms to others, which profess to represent the Roman style, but which are, in fact, examples of that mixed manner which is called the style of the Cinquecento by the Italians, of the Renaissance by the French, and which is commonly included in our Elizabethan. But in the early architectural works, besides the superstitions and mistaken erudition which thus choked the growth of real architectural doctrines, another of the peculiar elements of the Middle Ages comes into view, its mysticism. The dimensions and positions of the various parts of edifices and of their members are determined by drawing triangles, squares, circles, and other figures in such a manner as to bound them. and to these geometrical figures were assigned many abstruse significations. The plan and the front of the cathedral at Milan are thus represented in Cesariano's work, bounded and subdivided by various equilateral triangles. And it is easy to see, in the earnestness with which he points out these relations, the evidence of a fanciful and mystical turn of thought. Note 96/4. The plan which he has given, Fall 14, he has entitled Ichnographia Fundamenti Sacri Edis Beresfali, Germanico More, a trigono AC periquadrato perstructa, Udi etiam equi nunc Milani viter. The work of Cesariano was translated into German by Gualter Rivius and published at Nuremberg in 1548 under the title of Vitruvius Tuch, with copies of the Italian diagrams. A few years ago, in an article in the Wiener Jobbucher Acht, Dec. 1821, the reviewer maintained, on the authority of the diagrams in Rivius's book, that Gothic architecture had its origin in Germany and not in England. We thus find erudition and mysticism take the place of much of that development of the architectural principles of the Middle Ages, which would be so interesting to us. Still, however, these works are by no means without their value. Indeed, many of the arts appear to flourish not at all the worse, for being treated in a manner somewhat mystical, and it may easily be that the relations of geometrical figures, for which fantastical reasons are given, may really involve principles of beauty or stability. But independently of this, we find, in the best works of the architects of all ages, including engineers, evidence that the true idea of mechanical pressure exists among them more distinctly than among men in general, although it may not be developed in a scientific form. This is true up to our own time, and the arts which such persons cultivate could not be successfully, 251, exercised if it were not so. Hence the writings of architects and engineers during the Middle Ages do really form a prelude to the works on scientific mechanics. Vitruvius, in his Architecture, and Julius Frontinus, who, under Vespasian, wrote on aqueducts, of which he was superintendent, have transmitted to us the principal part of what we know respecting the practical mechanics and hydraulics of the Romans. In modern times, the series is resumed. The early writers on architecture are also writers on engineering, and often on hydrostatics. For example, Leonardo da Vinci wrote on the equilibrium of water. And thus we are led up to Stevinus of Bruges, who was engineer to Prince Maurice of Nassau and inspector of the dikes in Holland, and in whose work, on the processes of his art, is contained the first clear modern statement of the scientific principles of hydrostatics. Having thus explained both the obstacles and the prospects which the Middle Ages offered to the progress of science, I now proceed to the history of the progress, when that progress was once again resumed. 253, Book 5. History of Formal Astronomy after the Stationary Period. Cyclopum educta caminis monia conspicio, ac adverso fornis portas. His demum exactis perfecto munor divi, devenor locos lidos et ammona virta fortunatorum nemorum sedesc betas, larger hic campos etha et lumine vestit purpureo. Solemn suum sua sidera norant Virgil, Roman 6, 630. They leave at length the nether gloom, and stand before the portals of a better land. To happier plains they come, and fairer groves, the seats of those whom heaven, benignant, loves, a brighter day, a bluer ether, spreads its lucid depths above their favored heads, and, purged from mists that veil our earthly skies, shine suns and stars unseen by mortal eyes. 255, Introduction. Of Formal and Physical Astronomy. We have thus rapidly traced the causes of the almost complete blank which the history of physical science offers, from the decline of the Roman Empire, for 1,000 years. Along with the breaking up of the ancient forms of society were broken up the ancient energy of thinking, the clearness of idea, and steadiness of intellectual action. This mental declension produced a servile admiration for the genius of the better periods, and thus the spirit of commentation. Christianity established the claim of truth to govern the world. And this principle, misinterpreted and combined with the ignorance and servility of the times, gave rise to the dogmatic system. And the love of speculation, finding no secure and permitted path on solid ground, went off into the regions of mysticism. The causes which produced the inertness and blindness of the stationary period of human knowledge began at last to yield to the influence of the principles which tended to progression. The indistinctness of thought, which was the original feature in the decline of sound knowledge, was in a measure remedied by the steady cultivation of pure mathematics and astronomy, and by the progress of inventions in the arts, which call out and fix the distinctness of our conceptions of the relations of natural phenomena. As men's minds became clear, they became less servile. The perception of the nature of truth drew men away from controversies about mere opinion. When they saw distinctly the relations of things, they ceased to give their whole attention to what had been said concerning them. And thus, as science rose into view, the spirit of commentation lost its way. And when men came to feel what it was to think for themselves on subjects of science, they soon rebelled against the right of others to impose opinions upon them. When they threw off their blind admiration for the ancients, they were disposed to cast away also their passive obedience to the ancient system of doctrines. When they were no longer inspired by the spirit of commentation, they were no longer submissive to the dogmatism of the schools. When they began to feel that they could, 256, discover truths, they felt also a persuasion of a right and a growing will so to do. Thus the revived clearness of ideas, which made its appearance at the revival of letters, brought on a struggle with the authority, intellectual and civil, of the established schools of philosophy. This clearness of idea showed itself, in the first instance, in astronomy, and was embodied in the system of Copernicus. But the contest did not come to a crisis till a century later, in the time of Galileo and other disciples of the new doctrine. It is our present business to trace the principles of this series of events in the history of philosophy. I do not profess to write a history of astronomy, any further than is necessary in order to exhibit the principles on which the progression of science proceeds. And, therefore, I neglect subordinate persons and occurrences in order to bring into view the leading features of great changes. Now, in the introduction of the Copernican system into general acceptation, two leading views operated upon men's minds: the consideration of the system as exhibiting the apparent motions of the universe, and the consideration of this system with reference to its causes, the formal and the physical aspect of the theory, the relations of space and time, and the relations of force and matter. These two divisions of the subject were at first not clearly separated. The second was long mixed, in a manner very dim and obscure, with the first, without appearing as a distinct subject of attention. But at last it was extricated and treated in a manner suitable to its nature. The views of Copernicus rested mainly on the formal condition of the universe, the relations of space and time. But Kepler, Galileo, and others were led, by controversies and other causes, to give a gradually increasing attention to the physical relations of the heavenly bodies. An impulse was given to the study of mechanics, the doctrine of motion, which became very soon an important and extensive science. And in no long period, the discoveries of Kepler, suggested by a vague but intense belief in the physical connection of the parts of the universe, led to the decisive and sublime generalizations of Newton. The distinction of formal and physical astronomy thus becomes necessary, in order to treat clearly of the discussions which the propounding of the Copernican theory occasioned. But it may be observed that, besides this great change, astronomy made very great advances in the same path which we have already been tracing, namely, the determination of the quantities and laws of the celestial motions, in so far as they were exhibited by the ancient theories, or 257 might be represented by obvious modifications of those theories. I speak of new inequalities, new phenomena, such as Copernicus, Galileo, and Tycho Brahe discovered. As, however, these were very soon referred to the Copernican rather than the Ptolemaic hypothesis, they may be considered as developments rather of the new than of the old theory, and I shall, therefore, treat of them, agreeably to the plan of the former part, as the sequel of the Copernican induction. Chapter 1. Prelude to the Inductive Epoch of Copernicus. The doctrine of Copernicus, that the sun is the true center of the celestial motions, depends primarily upon the consideration that such a supposition explains very simply and completely all the obvious appearances of the heavens. In order to see that it does this, nothing more is requisite than a distinct conception of the nature of relative motion and a knowledge of the principal astronomical phenomena. There was, therefore, no reason why such a doctrine might not be discovered, that is, suggested as a theory plausible at first sight, long before the time of Copernicus. Or rather, it was impossible that this guess, among others, should not be propounded as a solution of the appearances of the heavens. We are not, therefore, to be surprised if we find, in the earliest times of astronomy, and at various succeeding periods, such a system spoken of by astronomers, and maintained by some as true, though rejected by the majority and by the principal writers. When we look back at such a difference of opinion, having in our minds, as we unavoidably have, the clear and irresistible considerations by which the Copernican doctrine is established for us, it is difficult for us not to attribute superior sagacity and candor to those who held that side of the question, and to imagine those who clung to the Ptolemaic hypothesis to have been blind and prejudiced, incapable of seeing the beauty of simplicity and symmetry, or indisposed to resign established errors and to accept novel and comprehensive truths. Yet in judging thus, we are probably ourselves influenced by prejudices arising from the knowledge and received opinions of our own times. For is it in reality clear that before the time of Copernicus, the 258 heliocentric theory, that which places the center of the celestial motions in the sun, had a claim to ascent so decidedly superior to the geocentric theory, which places the Earth in the center? What is the basis of the heliocentric theory? That the relative motions are the same on that and on the other supposition. So far, therefore, the two hypotheses are exactly on the same footing. But it is urged, on the heliocentric side we have the advantage of simplicity. True, but we have on the other side the testimony of our senses. That is, the geocentric doctrine, which asserts that the Earth rests and the heavenly bodies move, is the obvious and spontaneous interpretation of the appearances. Both these arguments, simplicity on the one side and obviousness on the other, are vague, and we may venture to say both indecisive. We cannot establish any strong preponderance of probability in favor of the former doctrine, without going much further into the arguments of the question. Nor, when we speak of the superior simplicity of the Copernican theory, must we forget that though this theory has undoubtedly, in this respect, a great advantage over the Ptolemaic, yet that the Copernican system itself is very complex, when it undertakes to account, as the Ptolemaic did, for the inequalities of the motions of the sun, moon, and planets. And that in the hands of Copernicus, it retained a large share of the eccentrics and epicycles of its predecessor, and, in some parts, with increased machinery. The heliocentric theory, without these appendages, would not approach the Ptolemaic, in the accurate explanation of facts. And as those who had placed the sun in the center had never, till the time of Copernicus, shown how the inequalities were to be explained on that supposition, we may assert that after the promulgation of the theory of eccentrics and epicycles on the geocentric hypothesis, there was no published heliocentric theory which could bear a comparison with that hypothesis. It is true that all the contrivances of epicycles, and the like, by which the geocentric hypothesis was made to represent the phenomena, were susceptible of an easy adaptation to a heliocentric method, when a good mathematician had once proposed to himself the problem. And this was precisely what Copernicus undertook and executed. But till the appearance of his work, the heliocentric system had never come before the world except as a hasty and imperfect hypothesis, which bore a favorable comparison with the phenomena, so long as their general features only were known, but which had been completely thrown into the shade by the labor and intelligence bestowed upon 259 the Hipparchian or Ptolemaic theories by a long series of great astronomers of all civilized countries. But though the astronomers who, before Copernicus, held the heliocentric opinion, cannot, on any good grounds, be considered as much more enlightened than their opponents, it is curious to trace the early and repeated manifestations of this view of the universe. The distinct assertion of the heliocentric theory among the Greeks is an evidence of the clearness of their thoughts and the vigor of their minds, and it is a proof of the feebleness and servility of intellect in the stationary period, that, till the period of Copernicus, no one was found to try the fortune of this hypothesis, modified according to the improved astronomical knowledge of the time. The most ancient of the Greek philosophers to whom the ancients ascribed the heliocentric doctrine is Pythagoras, but Diogenes Laertius makes Philolaus, one of the followers of Pythagoras, the first author of this doctrine. We learn from Archimedes that it was held by his contemporary Aristarchus. Aristarchus of Samos, says he, makes this supposition that the fixed stars and the sun remain at rest, and that the earth revolves round the sun in a circle. Plutarch asserts that this, which was only a hypothesis in the hands of Aristarchus, was proved by Seleucus, but we may venture to say that, at that time, no such proof was possible. Aristotle had recognized the existence of this doctrine by arguing against it. All things, says he, tend to the center of the earth and rest there, and therefore the whole mass of the earth cannot rest except there. Ptolemy had in like manner argued against the diurnal motion of the earth. Such a revolution would, he urged, disperse into surrounding space all the loose parts of the earth. Yet he allowed that such a supposition would facilitate the explanation of some phenomena. Cicero appears to make Mercury and Venus revolve about the sun, as does Martianus Capella at a later period. And Seneca says it is a worthy subject of contemplation, whether the earth be at rest or in motion. But at this period, as we may see from Seneca himself, that habit of intellect which was requisite for the solution of such a question had been succeeded by indistinct views and rhetorical forms of speech. If there were any good mathematicians and good observers at this period, they were employed in cultivating and verifying the Hipparchian theory. Next to the Greeks, the Indians appear to have possessed that 260 original vigor and clearness of thought from which true science springs. It is remarkable that the Indians also had their heliocentric theorists. Aryabhata, A.D. 1322, and other astronomers of that country are said to have advocated the doctrine of the Earth's revolution on its axis, which opinion, however, was rejected by subsequent philosophers among the Hindus. Some writers have thought that the heliocentric doctrine was derived by Pythagoras and other European philosophers from some of the Oriental nations. This opinion, however, will appear to have little weight if we consider that the heliocentric hypothesis, in the only shape in which the ancients knew it, was too obvious to require much teaching, that it did not and could not, so far as we know, receive any additional strength from anything which the Oriental nations could teach, and that each astronomer was induced to adopt or reject it, not by any information which a master could give him, but by his love of geometrical simplicity on the one hand, or the prejudices of sense on the other. Real science, depending on a clear view of the relation of phenomena to general theoretical ideas, cannot be communicated in the way of secret and exclusive traditions, like the mysteries of certain arts and crafts. If the philosopher do not see that the theory is true, he is little the better for having heard or read the words which assert its truth. It is impossible, therefore, for us to assent to those views which would discover in the heliocentric doctrines of the ancients traces of a more profound astronomy than any which they have transmitted to us. Those doctrines were merely the plausible conjectures of men with sound geometrical notions, but they were never extended so as to embrace the details of the existing astronomical knowledge. And perhaps we may say that the analysis of the phenomena into the arrangements of the Ptolemaic system was so much more obvious than any other, that it must necessarily come first, in order to form an introduction to the Copernican. The true foundation of the heliocentric theory for the ancients was, as we have intimated, its perfect geometrical consistency with the general features of the phenomena and its simplicity. But it was unlikely that the human mind would be content to consider the subject under this strict and limited aspect alone. In its eagerness for wide speculative views, it naturally looked out for other and vaguer principles of connection and relation. Thus, as it had been urged in 261 favor of the geocentric doctrine, that the heaviest body must be in the center, it was maintained, as a leading recommendation of the opposite opinion, that it placed the fire, the noblest element, in the center of the universe. The authority of mythological ideas was called in on both sides to support these views. Numa, as Plutarch informs us, built a circular temple over the ever-burning fire of Vesta, typifying not the earth, but the universe, which, according to the Pythagoreans, has the fire seated at its center. The same writer in another of his works makes one of his interlocutors say, "Only, my friend, do not bring me before a court of law on a charge of impiety." As Cleans said that Aristarchus the Samian ought to be tried for impiety because he removed the hearth of the universe. This, however, seems to have been intended as a pleasantry. The prevalent physical views and the opinions concerning the causes of the motions of the parts of the universe were scarcely more definite than the ancient opinions concerning the relations of the four elements, till Galileo had founded the true doctrine of motion. Though, therefore, arguments on this part of the subject were the most important part of the controversy after Copernicus, the force of such arguments was at his time almost balanced. Even if more had been known on such subjects, the arguments would not have been conclusive. For instance, the vast mass of the heavens, which is commonly urged as a reason why the heavens do not move round the earth, would not make such a motion impossible. And, on the other hand, the motions of bodies at the earth's surface, which were alleged as inconsistent with its motion, did not really disprove such an opinion. But according to the state of the science of motion before Copernicus, all reasonings from such principles were utterly vague and obscure. We must not omit to mention a modern who preceded Copernicus in the assertion at least of the heliocentric doctrine. This was Nicholas of Cusa, a village near Treves, a cardinal and bishop who, in the first half of the 15th century, was very eminent as a divine and mathematician, and who in a work, De Docta Ignorantia, propounded the doctrine of the motion of the earth, more, however, as a paradox than as a reality. We cannot consider this as any distinct anticipation of a profound and consistent view of the truth. We shall now examine further the promulgation of the heliocentric system by Copernicus and its consequences. 262. Chapter 2. Induction of Copernicus, the heliocentric theory asserted on formal grounds. It will be recollected that the formal are opposed to the physical grounds of a theory, the former term indicating that it gives a satisfactory account of the relations of the phenomena in space and time, that is, of the motions themselves, while the latter expression implies further that we include in our explanation the causes of the motions, the laws of force and matter. The strongest of the considerations by which Copernicus was led to invent and adopt his system of the universe were of the former kind. He was dissatisfied, he says, in his preface addressed to the Pope, with the want of symmetry in the eccentric theory as it prevailed in his days, and weary of the uncertainty of the mathematical traditions. He then sought through all the works of philosophers whether any had held opinions concerning the motions of the world, different from those received in the established mathematical schools. He found, in ancient authors, accounts of Philolaus and others who had asserted the motion of the earth. Then, he adds, I, too, began to meditate concerning the motion of the earth. And though it appeared an absurd opinion, yet since I knew that, in previous times, others had been allowed the privilege of feigning what circles they chose, in order to explain the phenomena, I conceived that I also might take the liberty of trying whether, on the supposition of the earth's motion, it was possible to find better explanations than the ancient ones of the revolutions of the celestial orbs. Having then assumed the motions of the earth, which are hereafter explained, by laborious and long observation I at length found that if the motions of the other planets be compared with the revolution of the earth, not only their phenomena follow from the suppositions, but also that the several orbs and the whole system are so connected in order and magnitude that no one part can be transposed without disturbing the rest and introducing confusion into the whole universe. Thus, the satisfactory explanation of the apparent motions of the planets and the simplicity and symmetry of the system were the 263 grounds on which Copernicus adopted his theory, as the craving for these qualities was the feeling which led him to seek for a new theory. It is manifest that in this, as in other cases of discovery, a clear and steady possession of abstract ideas and an aptitude in comprehending real facts under these general conceptions must have been leading characters in the discoverer's mind. He must have had a good geometrical head and great astronomical knowledge. He must have seen, with peculiar distinctness, the consequences which flowed from his suppositions as to the relations of space and time, the apparent motions which resulted from the assumed real ones, and he must also have known well all the irregularities of the apparent motions for which he had to account. We find indications of these qualities in his expressions. A steady and calm contemplation of the theory is what he asks for as the main requisite to its reception. If you suppose the earth to revolve and the heaven to be at rest, you will find, he says, si serio animadvertes, if you think steadily, that the apparent diurnal motion will follow. And after alleging his reasons for his system, he says, we are therefore not ashamed to confess that the whole of the space within the orbit of the Moon, along with the center of the Earth, moves round the Sun in a year among the other planets. The magnitude of the world being so great that the distance of the Earth from the Sun has no apparent magnitude when compared with the sphere of the fixed stars. All which things, though they be difficult and almost inconceivable, and against the opinion of the majority, yet, in the sequel, by God's favor, we will make clearer than the sun, at least to those who are not ignorant of mathematics. Note 7/5. Nicolae Copernicitorinensis de Revolutionibus Orbium Celestium Libri Roman 6. Norimbergi, M.D. Roman 43. p. 9. It will easily be understood that since the ancient geocentric hypothesis ascribed to the planets those motions which were apparent only, and which really arose from the motion of the Earth round the Sun in the new hypothesis, the latter scheme must much simplify the planetary theory. Kepler enumerates 11 motions of the Ptolemaic system, which are at once exterminated and rendered unnecessary by the new system. Still, as the real motions, both of the Earth and the planets, are unequable, it was requisite to have some mode of representing their inequalities, and accordingly, the ancient theory of eccentrics and epicycles was retained, so far as was requisite for this purpose. The planets revolved round the Sun by means of a deferent and a 264 great and small epicycle, or else by means of an eccentric and epicycle modified from Ptolemy's for reasons which we shall shortly mention. This mode of representing the motions of the planets continued in use until it was expelled by the discoveries of Kepler. Besides the daily rotation of the Earth on its axis and its annual circuit about the Sun, Copernicus attributed to the axis a motion of declination, by which, during the whole annual revolution, the pole was constantly directed towards the same part of the heavens. This constancy in the absolute direction of the axis, or its moving parallel to itself, may be more correctly viewed as not indicating any separate motion. The axis continues in the same direction because there is nothing to make it change its direction, just as a straw, lying on the surface of a cup of water, continues to point nearly in the same direction when the cup is carried round a room, and this was noticed by Copernicus's adherent Rothman a few years after the publication of the work De Revolutionibus. There is no occasion, he says in a letter to Tycho Brahe, for the triple motion of the Earth. The annual and diurnal motions suffice. This error of Copernicus, if it be looked upon as an error, arose from his referring the position of the axis to a limited space, which he conceived to be carried round the Sun along with the Earth, instead of referring it to fixed or absolute space. When, in a planetarium, a machine in which the motions of the planets are imitated, the Earth is carried round the Sun by being fastened to a material radius, it is requisite to give a motion to the axis by additional machinery, in order to enable it to preserve its parallelism. A similar confusion of geometrical conception, produced by a double reference to absolute space and to the center of revolution, often leads persons to dispute whether the Moon, which revolves about the Earth, always turning to it the same face, revolves about her axis or not. It is also to be noticed that the precession of the equinoxes made it necessary to suppose the axis of the Earth to be not exactly parallel to itself, but to deviate from that position by a slight annual difference. Copernicus erroneously supposes the precession to be unequable, and his method of explaining this change, which is simpler than that of the ancients, becomes more simple still, when applied to the true state of the facts. The tendencies of our speculative nature, which carry us onwards in 265, Pursuit of Symmetry and Rule, and which thus produce the theory of Copernicus, as they produce all theories, perpetually show their vigor by overshooting their mark. They obtain something by aiming at much more. They detect the order and connection which exist by imagining relations of order and connection which have no existence. Real discoveries are thus mixed with baseless assumptions. Profound sagacity is combined with fanciful conjecture, not rarely, or in peculiar instances, but commonly, and in most cases, probably in all, if we could read the thoughts of the discoverers as we read the books of Kepler. To try wrong guesses is apparently the only way to hit upon right ones. The character of the true philosopher is not that he never conjectures hazardously, but that his conjectures are clearly conceived and brought into rigid contact with facts. He sees and compares distinctly the ideas and the things the relations of his notions to each other and to phenomena. Under these conditions, it is not only excusable, but necessary for him to snatch at every semblance of general rule, to try all promising forms of simplicity and symmetry. Copernicus is not exempt from giving us, in his work, an example of this character of the inventive spirit. The axiom that the celestial motions must be circular and uniform appeared to him to have strong claims to acceptation, and his theory of the inequalities of the planetary motions is fashioned upon it. His great desire was to apply it more rigidly than Ptolemy had done. The time did not come for rejecting this axiom, till the observations of Tycho Brahe and the calculations of Kepler had been made. I shall not attempt to explain, in detail, Copernicus's system of the planetary inequalities. He retained epicycles and eccentrics, altering their centers of motion. That is, he retained what was true in the old system, translating it into his own. The peculiarities of his method consisted in making such a combination of epicycles as to supply the place of the equant, and to make all the motions equable about the centers of motion. This device was admired for a time, till Kepler's elliptic theory expelled it, with all other forms of the theory of epicycles. But we must observe that Copernicus was aware of some of the discrepancies which belonged to that theory as it had, up to that time, been propounded. In the case of Mercury's orbit, which is more eccentric than that of the other planets, he makes suppositions which are complex indeed, but which show his perception of the imperfection of 266, the common theory. And he proposes a new theory of the moon, for the very reason which did at last overturn the doctrine of epicycles, namely, that the ratio of their distances from the Earth at different times was inconsistent with the circular hypothesis. It is obvious that, along with his mathematical clearness of view and his astronomical knowledge, Copernicus must have had great intellectual boldness and vigor to conceive and fully develop a theory so different as his was from all received doctrines. His pupil and expositor, Rheticus, says to Schener, "I beg you to have this opinion concerning that learned man, my preceptor, that he was an ardent admirer and follower of Ptolemy. But when he was compelled by phenomena and demonstration, he thought he did well to aim at the same mark at which Ptolemy had aimed, though with a bow and shafts of a very different material from his." We must recollect what Ptolemy says, delta epsilon letter 1 f d6, letter 1 f10 lambda epsilon theta epsilon rho omicron nu, epsilon letter 1 f36, nu alpha gota tau, letter 1 fc7 gamma nu omega, mu letter 1 fc3 tau, letter 1 f78, nu mu epsilon lambda omicron nu tau alpha, phi gota lambda omicron sigma omicron, phi epsilon letter 1 fd6 nu. He who is to follow philosophy must be a freeman in mind. Rheticus then goes on to defend his master from the charge of disrespect to the ancients. That temper, he says, is alien from the disposition of every good man, and most especially from the spirit of philosophy, and from no one more utterly than from my preceptor. He was very far from rashly rejecting the opinions of ancient philosophers, except for weighty reasons and irresistible facts, through any love of novelty. His years, his gravity of character, his excellent learning, his magnanimity and nobleness of spirit, are very far from having any liability to such a temper, which belongs either to youth, or to ardent and light minds, or to those tau letter 1 ff6 nu mu epsilon gamma alpha, phi rho omicron nu omicron epsilon nu tau, mega nu letter 1 f10 pi letter 1 f76 theta epsilon, omega rho gota letter 1 fb3, mu gota kappa rho letter 1 fc2. Who think much of themselves and know little, as Aristotle says. Undoubtedly, this deference for the great men of the past, joined with the talent of seizing the spirit of their methods when the letter of their theories is no longer tenable, is the true mental constitution of discoverers. Besides the intellectual energy which was requisite in order to construct a system of doctrines so novel as those of Copernicus, some courage was necessary to the publication of such opinions, certain as they were to be met, to a great extent, by rejection and dispute, and perhaps by charges of heresy and mischievous tendency. This last danger, however, must not be judged so great as we might infer from the angry controversies and acts of authority which occurred in 267, Galileo's time. The dogmatism of the stationary period, which identified the cause of philosophical and religious truth, had not yet distinctly felt itself attacked by the advance of physical knowledge, and therefore had not begun to look with alarm on such movements. Still, the claims of scripture and of ecclesiastical authority were asserted as paramount on all subjects, and it was obvious that many persons would be disquieted or offended with the new interpretation of many scriptural expressions, which the true theory would make necessary. This evil Copernicus appears to have foreseen, and this and other causes long withheld him from publication. He was himself an ecclesiastic, and by the patronage of his maternal uncle, was prebendary of the Church of St. John at Thorn, and a canon of the Church of Frauenburg, in the Diocese of Ermeland. He had been a student at Bologna, and had taught mathematics at Rome in the year 1500, and he afterwards pursued his studies and observations at his residence near the mouth of the Vistula. His discovery of his system must have occurred before 1507, for in 1543 he informs Pope Paulus III, in his dedication, that he had kept his book by him for 4 times the 9 years recommended by Horace, and then only published it at the earnest entreaty of his friend Cardinal Scamarg, whose letter is prefixed to the work. "Though I know," he says, "that the thoughts of a philosopher do not depend on the judgment of the many, his study being to seek out truth in all things as far as that is permitted by God to human reason. Yet when I considered," he adds, "how absurd my doctrine would appear, I long hesitated whether I should publish my book, or whether it were not better to follow the example of the Pythagoreans and others, who delivered their doctrines only by tradition and to friends." It will be observed that he speaks here of the opposition of the established school of astronomers, not of divines. The latter, indeed, he appears to consider as a less formidable danger. "If perchance," he says at the end of his preface, "there be mu alpha tau alpha iota omicron lambda omicron gamma omicron iota, vain babblers, who knowing nothing of mathematics, yet assume the right of judging on account of some place of Scripture perversely wrested to their purpose, and who blame and attack my undertaking, I heed them not, and look upon their judgments as rash and contemptible." He then goes on to show that the globular figure of the Earth, which was, of course, at that time, an undisputed point among astronomers, had been opposed on similar grounds by Lactantius, who, 268, though a writer of credit in other respects, had spoken very childishly in that matter. In another epistle prefixed to the work, by Andreas Osiander, the reader is reminded that the hypotheses of astronomers are not necessarily asserted to be true by those who propose them, but only to be a way of representing facts. We may observe that, in the time of Copernicus, when the motion of the Earth had not been connected with the physical laws of matter and motion, it could not be considered so distinctly real as it necessarily was held to be in after times. The delay of the publication of Copernicus's work brought it to the end of his life. He died in the year 1543, in which it was published. It was entitled De Revolutionibus Orbium Celestium Libri Roman 6. He received the only copy he ever saw on the day of his death and never opened it. He had then, says Gassendi, his biographer, other cares. His system was, however, to a certain extent, promulgated, and his fame diffused before that time. Cardinal Scamarg, in his letter of 1536, which has been already mentioned, says, "Some years ago, when I heard tidings of your merit by the constant report of all persons, my affection for you was augmented, and I congratulated the men of our time, among whom you flourish in so much honor. For I had understood that you were not only acquainted with the discoveries of ancient mathematicians, but also had formed a new system of the world, in which you teach that the earth moves, the sun occupies the lowest, and consequently, the middle place, the sphere of the fixed stars, remains immovable and fixed, and the moon, along with the elements included in her sphere, placed between the orbits, coelom, of Mars and Venus, travels round the sun in a yearly revolution." The writer goes on to say that he has heard that Copernicus has written a book, Commentarios, in which this system is applied to the construction of tables of the planetary motions, Ariticarum Stellarum. He then proceeds to entreat him earnestly to publish his lucubrations. 269. Note 14/5. This passage has so important a place in the history that I will give it in the original. Intellixeram te non modo veterum mathematicorum inventa egregi caler, sed etiam novum mundi rationem constituis. Qua docias terram moveri. Solum imum mundi, ac medium locum obtiner. Coelum octavum imatum ac fixum perpetuum manner. lunam si unicum inclusis sui spheri elementis, inter martis et veneris coelum sidam, anniversario cursus circum solum converter. Ac de hac tot a astronomii, ration commentarios a t confectos esse, ac erticarum stellarum modus calculis subductos tabulis t conchalis, maxima omnium cum admiration. Quamabrum ver doctisime, nisi tibi molestisum, t etiam ac etiam oro vehementer, ut hoc tuum inventum studiosus communices, et tuas de mundi sphera lucubrations, unicum tabulis et si quid habes praeterea quad ad indem rem pertinit primo quoque tempor admi mitas. This letter is dated 1536 and implies that the work of Copernicus was then written and known to persons who studied astronomy. De Lambert says that Achilles Gassaris of Lindau, in a letter dated 1540, sends to his friend George Vaugelan of Constance the book Der Revolutionibus. But Mr. de Morgan has pointed out that the printed work which Gassaris sent to Vaugelan was the Narratio by Rheticus of Feldkirch, a eulogium of Copernicus and his system prefixed to the second edition of the De Revolutionibus, which appeared in 1566. In this narration, Rheticus speaks of the work of Copernicus as a palingenesia, or new birth of astronomy. Rheticus, it appears, had gone to Copernicus for the purpose of getting knowledge about triangles and trigonometrical tables, and had had his attention called to the heliocentric theory, of which he became an ardent admirer. He speaks of his preceptor with strong admiration, as we have seen. He appears to me, says he, more to resemble Ptolemy than any other astronomers. This, it must be recollected, was selecting the highest known subject of comparison. Note 15/5. Asked, Mod IP 138. I owe this and many other corrections to the personal kindness of Mr. de Morgan. Chapter 3. Sequel to Copernicus, the reception and development of the Copernican theory. Sect 1. First reception of the Copernican theory. The theories of Copernicus made their way among astronomers, in the manner in which true astronomical theories always obtain the assent of competent judges. They led to the construction of tables of the motion of the sun, moon, and planets, as the theories of Hipparchus and Ptolemy had done, and the verification of the doctrines was to be looked for from the agreement of these tables with observation through a sufficient course of time. The work De Revolutionibus contains such tables. In 1551, Reinhold improved and republished tables founded on the principles of Copernicus. We owe, he says in his preface, great obligations to Copernicus, both for his laborious 270 observations and for restoring the doctrine of the motions. But though his geometry is perfect, the good old man appears to have been, at times, careless in his numerical calculations. I have, therefore, recalculated the whole, from a comparison of his observations with those of Ptolemy and others, following nothing but the general plan of Copernicus's demonstrations. These Prutenic tables were republished in 1571 and 1585, and continued in repute for some time, till superseded by the Rudolphine tables of Kepler in 1627. The name Prutenic, or Prussian, was employed by the author as a mark of gratitude to his benefactor Albert, Markgrave of Brandenburg. The discoveries of Copernicus had inspired neighboring nations with the ambition of claiming a place in the literary community of Europe. In something of the same spirit, Rheticus wrote an encomium Borussii, which was published along with his Narratio. The tables founded upon the Copernican system were, at first, much more generally adopted than the heliocentric doctrine on which they were founded. Thus Magini published at Venice, in 1587, new theories of the celestial orbits, agreeing with the observations of Nicholas Copernicus. But in the preface, after praising Copernicus, he says, since, however, he, either for the sake of showing his talents or induced by his own reasons, has revived the opinion of Nystas, Aristarchus, and others concerning the motion of the earth, and has disturbed the established constitution of the world, which was a reason why many rejected or received with dislike his hypothesis, I have thought it worthwhile that, rejecting the suppositions of Copernicus, I should accommodate other causes to his observations, and to the Prutenic tables. This doctrine, however, was, as we have shown, received with favor by many persons, even before its general publication. The doctrine of the motion of the earth was first publicly maintained at Rome by Widmanstadt, who professed to have received it from Copernicus and explained the system before the Pope and the cardinals, but did not teach it to the public. Note 16/5. Si Venturi, Essai sur les ouvrages physico-mathématiques de Léonard da Vinci, avec des fragments tirés de ses manuscrits apportés d'Italie. Paris, 1797, and as they're quoted, Marini Archiatri Pontificii, Tom, Roman 2, p. 251. Leonardo da Vinci, who was an eminent mathematician, as well as painter, about 1510, explained how a body, by describing a kind of spiral, might descend towards a revolving globe, so that its apparent motion relative to a point in the surface of the globe might be in a 271 straight line leading to the center. He thus showed that he had entertained in his thoughts the hypothesis of the Earth's rotation, and was employed in removing the difficulties which accompanied this supposition, by means of the consideration of the composition of motions. In like manner, we find the question stirred by other eminent men. Thus John Muller of Königsberg, a celebrated astronomer who died in 1476, better known by the name of Regiomontanus, wrote a dissertation on the subject, whether the Earth be in motion or at rest, in which he decides ex professo against the motion. Yet such discussions must have made generally known the arguments for the heliocentric theory. We have already seen the enthusiasm with which Rheticus, who was Copernicus's pupil in the latter years of his life, speaks of him. Thus, says he, God has given to my excellent preceptor a reign without end, which may he vouchsafe to guide, govern, and increase to the restoration of astronomical truth. Amen. Of the immediate converts of the Copernican system, who adopted it before the controversy on the subject had attracted attention, I shall only add Maestlin and his pupil, Kepler. Maestlin published in 1588 an Epitome Astronomiae, in which the immobility of the Earth is asserted. But in 1596, he edited Kepler's Mysterium Cosmographicum and the Narratio of Rheticus. And in an epistle of his own, which he inserts, he defends the Copernican system by those physical reasonings which we shall shortly have to mention, as the usual arguments in this dispute. Kepler himself, in the outset of the work just named, says, "When I was at Tübingen, attending to Michael Maestlin, being disturbed by the manifold inconveniences of the usual opinion concerning the world, I was so delighted with Copernicus, of whom he made great mention in his lectures, that I not only defended his opinions in our disputations of the candidates, but wrote a thesis concerning the first motion which is produced by the revolution of the Earth." This must have been in 1590. The differences of opinion respecting the Copernican system, of which we thus see traces, led to a controversy of some length and extent. This controversy turned principally upon physical considerations, which were much more distinctly dealt with by Kepler, and others of the followers of Copernicus, than they had been by the 272 discoverer himself. I shall, therefore, give a separate consideration to this part of the subject. It may be proper, however, in the first place, to make a few observations on the progress of the doctrine, independently of these physical speculations. Sect 2. Diffusion of the Copernican theory. The diffusion of the Copernican opinions in the world did not take place rapidly at first. Indeed, it was necessarily some time before the progress of observation and of theoretical mechanics gave the heliocentric doctrine that superiority in argument, which now makes us wonder that men should have hesitated when it was presented to them. Yet there were some speculators of this kind, who were attracted at once by the enlarged views of the universe which it opened to them. Among these was the unfortunate Giordano Bruno of Nola, who was burnt as a heretic at Rome in 1600. The heresies which led to his unhappy fate were, however, not his astronomical opinions, but a work which he published in England and dedicated to Sir Philip Sidney, under the title of Spazio della Bestia Triunfante, and which is understood to contain a bitter satire of religion and the papal government. Montucla conceives that, by his rashness in visiting Italy after putting forth such a work, he compelled the government to act against him. Bruno embraced the Copernican opinions at an early period, and connected with them the belief in innumerable worlds besides that which we inhabit, as also certain metaphysical or theological doctrines which he called the Gnolan philosophy. In 1591, he published De Innumerabilibus, Immenso, et Infigurabili, Seu de Universo et Mundis, in which he maintains that each star is a sun, about which revolve planets like our Earth. But this opinion is mixed up with a large mass of baseless verbal speculations. Giordano Bruno is a disciple of Copernicus on whom we may look with peculiar interest, since he probably had a considerable share in introducing the new opinions into England, although other persons, as Ricord, Field, D., had adopted it nearly 30 years earlier, and Thomas Digges 10 years before, much more expressly. Bruno visited this country in the reign of Queen Elizabeth, and speaks of her and of her counselors in terms of praise, which appear to show that 273, his book was intended for English readers, though he describes the mob which was usually to be met with in the streets of London with expressions of great disgust. Una plebe la qual in esser irrespettivole, in civil, rasa, rustica, selvatica, et malelevata, non sed ad altrici passer passa la terra nel suicino. The work to which I refer is La Cena de la Senner, and narrates what took place at a supper held on the evening of Ash Wednesday, about 1583, CP 145 of the book, at the house of Sir Fulk Greville, in order to give Il Nolano an opportunity of defending his peculiar opinions. His principal antagonists are two Dittori di Oxonia, whom Bruno calls Nundinio and Torquato. The subject is not treated in any very masterly manner on either side, but the author makes himself have greatly the advantage not only in argument, but in temper and courtesy. And in support of his representations of pedantesca, ostinatissima ignoranza et praesenziani, mistacon una rustica incivilita, chi fareb prevaricar la pasians et job. In his opponents, he refers to a public disputation which he had held at Oxford with these doctors of theology, in presence of Prince Alasco and many of the English nobility. Note 18/5, see Burton's Annat, Mel, Pref. Some prodigious tenet or paradox of the Earth's motion, and see Bruno and c. Among the evidences of the difficulties which still lay in the way of the reception of the Copernican system, we may notice Bacon, who, as is well known, never gave a full assent to it. It is to be observed, however, that he does not reject the opinion of the Earth's motion in so peremptory and dogmatical a manner as he is sometimes accused of doing. Thus in the Thema Caeli he says, "The Earth, then, being supposed to be at rest, for that now appears to us the more true opinion." And in his tract on the cause of the tides, he says, "If the tide of the sea be the extreme and diminished limit of the diurnal motion of the heavens, it will follow that the earth is immovable, or at least that it moves with a much slower motion than the water." In the Descriptio Globi Intellectualis, he gives his reasons for not accepting the heliocentric theory. In the system of Copernicus, there are many and grave difficulties, for the threefold motion with which he encumbers the earth is a serious inconvenience, and the separation of the sun from the planets, with which he has so many affections in common, is likewise a harsh step, and the introduction of so many immovable bodies into nature, as when he makes the sun and the stars immovable, the bodies which are peculiarly lucid and radiant, and his making the moon adhere to the earth in a sort of epicycle. And some 274 other things which he assumes are proceedings which mark a man who thinks nothing of introducing fictions of any kind into nature, provided his calculations turn out well. We have already explained that, in attributing three motions to the earth, Copernicus had presented his system encumbered with a complexity not really belonging to it. But it will be seen shortly that Bacon's fundamental objection to this system was his wish for a system which could be supported by sound physical considerations. And it must be allowed that at the period of which we are speaking, this had not yet been done in favor of the Copernican hypothesis. We may add, however, that it is not quite clear that Bacon was in full possession of the details of the astronomical systems which that of Copernicus was intended to supersede, and that thus he, perhaps, did not see how much less harsh were these fictions, as he called them, than those which were the inevitable alternatives. Perhaps he might even be liable to a little of that indistinctness, with respect to strictly geometrical conceptions, which we have remarked in Aristotle. We can hardly otherwise account for his not seeing any use in resolving the apparently irregular motion of a planet into separate regular motions. Yet he speaks slightingly of this important step. The motion of planets, which is constantly talked of as the motion of regression or renitency from west to east, and which is ascribed to the planets as a proper motion, is not true, but only arises from appearance, from the greater advance of the starry heavens towards the west, by which the planets are left behind to the east. Undoubtedly, those who spoke of such a motion of regression were aware of this, but they saw how the motion was simplified by this way of conceiving it, which Bacon seems not to have seen. Though, therefore, we may admire Bacon for the steadfastness with which he looked forward to physical astronomy as the great and proper object of philosophical interest, we cannot give him credit for seeing the full value and meaning of what had been done, up to his time, in formal astronomy. Bacon's contemporary, Gilbert, whom he frequently praises as a philosopher, was much more disposed to adopt the Copernican opinions, though even he does not appear to have made up his mind to assent to the whole of the system. In his work, De Magnete, printed 1600, he gives the principal arguments in favor of the Copernican system and decides that the Earth revolves on its axis. He connects 275 this opinion with his magnetic doctrines, and especially endeavors by that means to account for the precession of the equinoxes. But he does not seem to have been equally confident of its annual motion. In a posthumous work, published in 1661, De Mundo Nostra Sublunari Philosophia Nova, he appears to hesitate between the systems of Tycho and Copernicus. Indeed, it is probable that at this period many persons were in a state of doubt on such subjects. Milton, at a period somewhat later, appears to have been still undecided. In the opening of the 8th book of the Paradise Lost, he makes Adam state the difficulties of the Ptolemaic hypothesis, to which the archangel Raphael opposes the usual answers, but afterwards suggests to his pupil the newer system. What if seventh to these the planet Earth, so steadfast though she seem, insensibly 3 different motions move, par. Lost, be Roman 8. Milton's leaning, however, seems to have been for the new system. We can hardly believe that he would otherwise have conceived so distinctly, and described with such obvious pleasure, the motion of the earth, or she from west her silent course advance with inoffensive pace, that spinning sleeps on her soft axle, while she paces even, and bears thee soft with the smooth air along, par. Lost, be Roman 8. Perhaps the works of the celebrated Bishop Wilkins tended more than any others to the diffusion of the Copernican system in England, since even their extravagances drew a stronger attention to them. In 1638, when he was only 24 years old, he published a book entitled The Discovery of a New World, or a discourse tending to prove that it is probable there may be another habitable world in the moon, with a discourse concerning the possibility of a passage thither. The latter part of his subject was, of course, an obvious mark for the sneers and witticisms of critics. 2 years afterwards, in 1640, appeared his discourse concerning a new planet, tending to prove that it is probable our Earth is one of the planets, in which he urged the reasons in favor of the heliocentric system, and explained away the opposite arguments, especially those drawn from the 276 supposed declarations of Scripture. Probably a good deal was done for the establishment of those opinions by Thomas Salisbury, who was a warm admirer of Galileo, and published in 1661 a translation of several of his works bearing upon this subject. The mathematicians of this country in the 17th century, as Napier and Briggs, Horrocks and Crabtree, Ovid and Sethward, Wallis and Wren, were probably all decided Copernicans. Kepler dedicates one of his works to Napier, and Ward invented an approximate method of solving Kepler's problem, still known as the simple elliptical hypothesis. Horrocks wrote, and wrote well, in defense of the Copernican opinion, in his Keplerian Astronomy Defended and Promoted, composed in Latin probably about 1635, but not published till 1673, the author having died at the age of 22 and his papers having been lost. But Salisbury's work was calculated for another circle of readers. The book, he says in the introductory address, being, for subject and design, intended chiefly for gentlemen, I have been as careless of using a studied pedantry in my style, as careful in contriving a pleasant and beautiful impression. In order, however, to judge of the advantage under which the Copernican system now came forward, we must consider the additional evidence for it which was brought to light by Galileo's astronomical discoveries. Sect 3. The heliocentric theory confirmed by facts, Galileo's astronomical discoveries. The long interval which elapsed between the last great discoveries made by the ancients and the first made by the moderns had afforded ample time for the development of all the important consequences of the ancient doctrines. But when the human mind had been thoroughly roused again into activity, this was no longer the course of events. Discoveries crowded on each other. One wide field of speculation was only just opened, when a richer promise tempted the laborers away into another quarter. Hence, the history of this period contains the beginnings of many sciences, but exhibits none fully worked out into a complete or final form. Thus, the science of statics, soon after its revival, was eclipsed and overlaid by that of dynamics, and the Copernican system, considered merely with reference to the views of its author, was absorbed in the commanding interest of physical astronomy. Still, advances were made which had an important bearing on the 277 heliocentric theory, in other ways than by throwing light upon its physical principles. I speak of the new views of the heavens which the telescope gave, the visible inequalities of the moon's surface, the moon-like phases of the planet Venus, the discovery of the satellites of Jupiter and of the ring of Saturn. These discoveries excited at the time the strongest interest, both from the novelty and beauty of the objects they presented to the sense, from the way in which they seemed to gratify man's curiosity with regard to the remote parts of the universe, and also from that of which we have here to speak, their bearing upon the conflict of the old and the new philosophy, the heliocentric and geocentric theories. It may be true, as Lagrange and Montucla say, that the laws which Galileo discovered in mechanics implied a profounder genius than the novelties he detected in the sky. But the latter naturally attracted the greater share of the attention of the world, and were matter of keener discussion. It is not to our purpose to speak here of the details and of the occasion of the invention of the telescope. It is well known that Galileo constructed his about 1609 and proceeded immediately to apply it to the heavens. The discovery of the satellites of Jupiter was almost immediately the reward of his activity, and these were announced in his Nuncius Sidereus, published at Venice in 1610. The title of this work will best convey an idea of the claim it made to public notice. The sidereal messenger, announcing great and very wonderful spectacles, and offering them to the consideration of everyone, but especially of philosophers and astronomers, which have been observed by Galileo Galilei, and C by the assistance of a perspective glass lately invented by him. Namely, in the face of the moon, in innumerable fixed stars in the Milky Way, in nebulous stars, but especially in 4 planets which revolve round Jupiter at different intervals and periods with a wonderful celerity, which hitherto not known to anyone, the author has recently been the first to detect, and has decreed to call the Medicean stars. The interest this discovery excited was intense, and men were at this period so little habituated to accommodate their convictions on matters of science to newly observed facts, that several of the paper philosophers, as Galileo termed them, appear to have thought they could get rid of these new objects by writing books against them. The effect which the discovery had upon the reception of the Copernican system was immediately very considerable. It showed that the real universe was very different from that which ancient philosophers had imagined, 278, and suggested at once the thought that it contained mechanism more various and more vast than had yet been conjectured. And when the system of the planet Jupiter thus offered to the bodily eye a model or image of the solar system according to the views of Copernicus, it supported the belief of such an arrangement of the planets, by an analogy all but irresistible. It thus, as a writer of our own times has said, gave the holding turn to the opinions of mankind respecting the Copernican system. We may trace this effect in Bacon, even though he does not assent to the motion of the earth. We affirm, he says, the sun-following arrangement, Solaisquium, of Venus and Mercury, since it has been found by Galileo that Jupiter also has attendants. The Nuncius Sidereus contained other discoveries which had the same tendency in other ways. The examination of the moon showed, or at least seemed to show, that she was a solid body, with a surface extremely rugged and irregular. This, though perhaps not bearing directly upon the question of the heliocentric theory, was yet a blow to the Aristotelians, who had, in their philosophy, made the moon a body of a kind altogether different from this, and had given an abundant quantity of reasons for the visible marks on her surface, all proceeding on these preconceived views. Others of his discoveries produced the same effect. For instance, the new stars invisible to the naked eye, and those extraordinary appearances called nebulae. But before the end of the year, Galileo had new information to communicate, bearing more decidedly on the Copernican controversy. This intelligence was indeed decisive with regard to the motion of Venus about the Sun, for he found that that planet, in the course of her revolution, assumes the same succession of phases which the Moon exhibits in the course of a month. This he expressed by a Latin verse, Cynthiae figuras emulator mater amorum. The Queen of Love, like Cynthia, shapes her forms, transposing the letters of this line in the published account, according to the practice of the age, which thus showed the ancient love for combining verbal puzzles with scientific discoveries, while it betrayed the newer feeling of jealousy respecting the priority of discovery of physical facts. It had always been a formidable objection to the Copernican theory that this appearance of the planets had not been observed. The author, 279 of that theory, had endeavored to account for this by supposing that the rays of the sun passed freely through the body of the planet. And Galileo takes occasion to praise him for not being deterred from adopting the system which, on the whole, appeared to agree best with the phenomena, by meeting with some appearances which it did not enable him to explain. Yet while the fate of the theory was yet undecided, this could not but be looked upon as a weak point in its defenses. The objection, in another form also, was embarrassing alike to the Ptolemaic and Copernican systems. Why, it was asked, did not Venus appear 4 times as large when nearest to the Earth as when furthest from it? The author of the epistle prefixed to Copernicus's work had taken refuge in this argument from the danger of being supposed to believe in the reality of the system. And Bruno had attempted to answer it by saying that luminous bodies were not governed by the same laws of perspective as opic ones. But a more satisfactory answer now readily offered itself. Venus does not appear 4 times as large when she is 4 times as near, because her bright part is not 4 times as large, though her visible diameter is. And as she is too small for us to see her shape with the naked eye, we judge of her size only by the quantity of light. The other great discoveries made in the heavens by means of telescopes, as that of Saturn's ring and his satellites, the spots in the sun, and others, belong to the further progress of astronomy. But we may here observe that this doctrine of the motion of Mercury and Venus about the sun was further confirmed by Kepler's observation of the transit of the former planet over the sun in 1631. Our countryman Horrocks was the first person who, in 1639, had the satisfaction of seeing a transit of Venus. These events are a remarkable instance of the way in which a discovery in art, for at this period, the making of telescopes must be mainly so considered, may influence the progress of science. We shall soon have to notice a still more remarkable example of the way in which 2 sciences, astronomy and mechanics, may influence and promote the progress of each other. 280. Sect 4. The Copernican system, opposed on theological grounds. The doctrine of the Earth's motion round the sun, when it was asserted and promulgated by Copernicus, soon after 1500, excited no visible alarm among the theologians of his own time. Indeed, it was received with favor by the most intelligent ecclesiastics, and lectures in support of the heliocentric doctrine were delivered in the ecclesiastical colleges. But the assertion and confirmation of this doctrine by Galileo, about a century later, excited a storm of controversy and was visited with severe condemnation. Galileo's own behavior appears to have provoked the interference of the ecclesiastical authorities, but there must have been a great change in the temper of the times to make it possible for his adversaries to bring down the sentence of the Inquisition upon opinions which had been so long current without giving any serious offense. It appears to me that the different degree of toleration accorded to the heliocentric theory in the time of Copernicus and of Galileo must be ascribed in a great measure to the controversies and alarms which had in the meantime arisen out of the Reformation in religion, and which had rendered the Romish Church more jealous of innovations in received opinions than it had previously been. It appears, too, that the discussion of such novel doctrines was, at that time at least, less freely tolerated in Italy than in other countries. In 1597, Kepler writes to Galileo thus: "Confide Galilei et progredir. Si bene conjecto, posse de praecipuis Europae mathematicis a nobis cessidir volunt, tanta vis est veritatis." Si tibi Italia minus est idonia ad publicationem et si aliqua habitures eis impedimenta, forsan Germania nobis hanc libertatem concedit. Venturi, Mem. Di Galileo, Volume IP 19. I would not, however, be understood to assert the condemnation of new doctrines in science to be either a general or a characteristic practice of the Romish Church. Certainly, the intelligent and cultivated minds of Italy, and many of the most eminent of her ecclesiastics among them, have always been the foremost in promoting and welcoming the progress of science. And, as I have stated, there were found among the Italian ecclesiastics of Galileo's time many of the earliest and most enlightened adherents of the Copernican system. The condemnation of the doctrine of the Earth's motion is, so far as I am aware, the only instance in which the papal authority has pronounced a decree upon a point of science. And the most candid of the 281 adherents of the Romish Church condemn the assumption of authority in such matters, which in this one instance, at least, was made by the ecclesiastical tribunals. The author of the Ages of Faith, Book 8, p. 248, says, "A congregation, it is to be lamented, declared the new system to be opposed to Scripture, and therefore heretical." In more recent times, as I have elsewhere remarked, the Church of authority and the Church of private judgment have each its peculiar temptations and dangers, when there appears to be a discrepance between Scripture and philosophy. But though we may acquit the popes and cardinals in Galileo's time of stupidity and perverseness in rejecting manifest scientific truths, I do not see how we can acquit them of dissimulation and duplicity. Those persons appear to me to defend in a very strange manner the conduct of the ecclesiastical authorities of that period, who boast of the liberality with which Copernican professors were placed by them in important offices, at the very time when the motion of the earth had been declared by the same authorities contrary to Scripture. Such merits cannot make us approve of their conduct in demanding from Galileo a public recantation of the system which they thus favored in other ways, and which they had repeatedly told Galileo he might hold as much as he pleased. Nor can anyone, reading the plain language of the sentence passed upon Galileo, and of the abjuration forced from him, find any value in the plea which has been urged, that the opinion was denominated a heresy only in a wide, improper, and technical sense. But if we are thus unable to excuse the conduct of Galileo's judges, I do not see how we can give our unconditional admiration to the philosopher himself. Perhaps the conventional decorum which, as we have seen, was required in treating of the Copernican system, may excuse or explain the furtive mode of insinuating his doctrines which he often employs, and which some of his historians admire as subtle irony, while others blame it as insincerity. But I do not see with what propriety Galileo can be looked upon as a martyr of science. Undoubtedly, he was very desirous of promoting what he conceived to be the cause of philosophical truth, but it would seem that, while he was restless and eager in urging his opinions, he was always ready to make such submissions as the spiritual tribunals required. He would really have acted as a martyr if he had uttered 282 his e per se muove in the place of his abjuration, not after it. But even in this case, he would have been a martyr to a cause of which the merit was of a mingled scientific character. For his own special and favorite share in the reasonings by which the Copernican system was supported was the argument drawn from the flux and reflux of the sea, which argument is altogether false. He considered this as supplying a mechanical ground of belief, without which the mere astronomical reasons were quite insufficient. But in this case, he was deserted by the mechanical sagacity which appeared in his other speculations. The heliocentric doctrine had for a century been making its way into the minds of thoughtful men, on the general ground of its simplicity and symmetry. Galileo appears to have thought that now, when these original recommendations of the system had been reinforced by his own discoveries and reasonings, it ought to be universally acknowledged as a truth and a reality. And when arguments against the fixity of the sun and the motion of the earth were adduced from the expressions of Scripture, he could not be satisfied without maintaining his favorite opinion to be conformable to Scripture as well as to philosophy, and he was very eager in his attempts to obtain from authority a declaration to this effect. The ecclesiastical authorities were naturally averse to express themselves in favor of a novel opinion, startling to the common mind and contrary to the most obvious meaning of the words of the Bible. And when they were compelled to pronounce, they decided against Galileo and his doctrines. He was accused before the Inquisition in 1615, but at that period the result was that he was merely recommended to confine himself to the mathematical reasonings upon the system, and to abstain from meddling with the scripture. Galileo's zeal for his opinions soon led him again to bring the question under the notice of the Pope, and the result was a declaration of the Inquisition that the doctrine of the Earth's motion appeared to be contrary to the sacred scripture. Galileo was prohibited from defending and teaching this doctrine in any manner, and promised obedience to this injunction. But in 1632, he published his asterisk, Dialogo degli due massimi sistemi del mondo, Tolmeco e Copernicano. And in this, he defended the heliocentric system by all the strongest arguments which its admirers used. Not only so, but he introduced into this dialogue a character under the name of Simplicius, in whose mouth was put the defense of all the ancient dogmas, and who was represented as defeated at all points in the discussion. 283, and he prefixed to the dialogue a notice, to the discreet reader, in which, in a vein of transparent irony, he assigned his reasons for the publication. Some years ago, he says, a wholesome edict was promulgated at Rome, which, in order to check the perilous scandals of the present age, imposed silence upon the Pythagorean opinion of the motion of the earth. There were not wanting, he adds, persons who rashly asserted that this decree was the result, not of a judicious inquiry, but of a passion ill-informed. And complaints were heard that counselors, utterly unacquainted with astronomical observations, ought not to be allowed, with their undue prohibitions, to clip the wings of speculative intellects. At the hearing of rash lamentations like these, my zeal could not keep silence. And he then goes on to say that he wishes, by the publication of his dialogue, to show that the subject had been fully examined at Rome. The result of this was that Galileo was condemned for his infraction of the injunction laid upon him in 1616. His dialogue was prohibited. He himself was commanded to abjure on his knees the doctrine which he had taught, and this abjuration he performed. This celebrated event must be looked upon rather as a question of decorum than a struggle in which the interests of truth and free inquiry were deeply concerned. The general acceptance of the Copernican system was no longer a matter of doubt. Several persons in the highest positions, including the Pope himself, looked upon the doctrine with favorable eyes, and had shown their interest in Galileo and his discoveries. They had tried to prevent his involving himself in trouble by discussing the question on scriptural grounds. It is probable that his knowledge of those favorable dispositions towards himself and his opinions led him to suppose that the slightest color of professed submission to the Church in his belief would enable his arguments in favor of the system to pass unvisited. The notice which I have quoted, in which the irony is quite transparent and the sarcasm glaringly obvious, was deemed too flimsy a veil for the purpose of decency, and indeed must have aggravated the offense. But it is not to be supposed that the inquisitors believed Galileo's abjuration to be sincere, or even that they wished it to be so. It is stated that when Galileo had made his renunciation of the earth's motion, he rose from his knees, and stamping on the earth with his foot, said, "E per si muove," and yet it does move. This is sometimes represented as the heroic soliloquy of a mind, cherishing its conviction of the truth in spite of persecution. I think we may more naturally conceive it uttered as a playful, 284, epigram in the ear of a cardinal's secretary, with a full knowledge that it would be immediately repeated to his master. Throughout the course of the proceedings against him, Galileo was treated with great courtesy and indulgence. He was condemned to a formal imprisonment and a very light discipline. T damnamus ad formulum carcerum, hugis es officii ad tempus, arbitrio nostro limitandum. Et titulo ponitentii salutaris praecipimus ut tribus annis futuris recites ** semel in hebdomada septem samos penitentials. But this confinement was reduced to his being placed under some slight restrictions, first at the house of Nicolani, the ambassador of his own sovereign, and afterwards at the country seat of Archbishop Piccolomini, one of his own warmest friends. It has sometimes been asserted or insinuated that Galileo was subjected to bodily torture. An argument has been drawn from the expressions used in his sentence, cum viro nobis vidretur, non sat integram veritatem pronunciatum circa tuum intentionem, judicavimus nessus esse venire ad rigorosum examen tui, in quo respondisti Catholis. It has been argued by M. Libri, Hist. Des Sciences Mathematiques and Italy, Volume Roman 4. p. 259, and M. Quinet, L. Ultramontanismi, Roman 4. Lecken, p. 104, that the rigorosum examen necessarily implies bodily torture, notwithstanding that no such thing is mentioned by Galileo and his contemporaries, and notwithstanding the consideration with which he was treated in all other respects. But M. Biot more justly remarks Biager. Univ. Art. Galileo, that such a procedure is incredible. To the opinion of M. Biot, we may add that of Delambre, who rejects the notion of Galileo's having been put to the torture, as inconsistent with the general conduct of the authorities towards him, and as irreconcilable with the accounts of the trial given by Galileo himself, and by a servant of his, who never quitted him for an instant. He adds also that it is inconsistent with the words of his sentence, Ni tus ist gravis et perniciosus error, ac transgressio remanet omnino impunitus. For the error would have been already very far from impunity if Galileo had been previously subjected to the rack. He adds, very reasonably, Il ni faut noircir person sans preuve, pas même l'inquisition. We must not calumniate even the Inquisition. The ecclesiastical authorities, having once declared the doctrine of the earth's motion to be contrary to Scripture and heretical, long adhered in form to this declaration, and did not allow the Copernican system to be taught in any other way than as an hypothesis. The 285 Padua edition of Galileo's works, published in 1744, contains the dialogue which now, the editors say, S finalmente publico libero uso call debite license, is now at last freely published with the requisite license. But they add, Quanto alla question principale del modo della terra, anche noi ci conformiamo alla retresione et protesta dell'autori, dichiarando nella più solenne forma, ci non più, ni di amitersi si non cum pura ipotesi mathematis, ci serve a spiegare più agevolamento certi fenomeni. Neither can nor ought to be admitted except as a convenient hypothesis. And in the edition of Newton's Principia, published in 1760 by Lesueur and Jacquier, of the Order of Minims, the editors prefix to the third book their declaratio, that though Newton assumes the hypothesis of the motion of the earth, and therefore they had used similar language, they were, in doing this, assuming a character which did not belong to them. Hinc alienam cocti summus gerer personam. They add, Ceterum latis a summis pontificibus contra telluris modum decretis, nos obsequi profemer. By thus making decrees against a doctrine which in the course of time was established as an indisputable scientific truth, the See of Rome was guilty of an unwise and unfortunate stretch of ecclesiastical authority. But though we do not hesitate to pronounce such a judgment on this case, we may add that there is a question of no small real difficulty, which the progress of science often brings into notice, as it did then. The revelation on which our religion is founded seems to declare, or to take for granted, opinions on points on which science also gives her decision. And we then come to this dilemma that doctrines, established by a scientific use of reason, may seem to contradict the declarations of revelation, according to our view of its meaning. And yet, that we cannot, in consistency with our religious views, make reason a judge of the truth of revealed doctrines. In the case of astronomy, on which Galileo was called in question, the general sense of cultivated and sober-minded men has long ago drawn that distinction between religious and physical tenets, which is necessary to resolve this dilemma. On this point, it is reasonably held that the phrases which are employed in Scripture respecting astronomical facts are not to be made use of to guide our scientific opinions. They may be supposed to answer their end if they fall in with common notions, and are thus effectually subservient to the moral and religion's import of revelation. But the establishment of this distinction was not accomplished without long and distressing controversies. Nor, if we wish to 286, include all cases in which the same dilemma may again come into play, is it easy to lay down an adequate canon for the purpose. For we can hardly foresee beforehand what part of the past history of the universe may eventually be found to come within the domain of science, or what bearing the tenets, which science establishes, may have upon our view of the providential and revealed government of the world. But without attempting here to generalize on this subject, there are two reflections which may be worth our notice. They are supported by what took place in reference to astronomy on the occasion of which we are speaking, and may, at other periods, be applicable to other sciences. In the first place, the meaning which any generation puts upon the phrases of Scripture depends, more than is at first sight supposed, upon the received philosophy of the time. Hence, while men imagine that they are contending for revelation, they are, in fact, contending for their own interpretation of revelation, unconsciously adapted to what they believe to be rationally probable. And the new interpretation, which the new philosophy requires, and which appears to the older school to be a fatal violence done to the authority of religion, is accepted by their successors without the dangerous results which were apprehended. When the language of Scripture, invested with its new meaning, has become familiar to men, it is found that the ideas which it calls up are quite as reconcilable as the former ones were with the soundest religious views. And the world then looks back with surprise at the error of those who thought that the essence of revelation was involved in their own arbitrary version of some collateral circumstance. At the present day, we can hardly conceive how reasonable men should have imagined that religious reflections on the stability of the earth, and the beauty and use of the luminaries which revolve round it, would be interfered with by its being acknowledged that this rest and motion are apparent only. In the next place, we may observe that those who thus adhere tenaciously to the traditionary or arbitrary mode of understanding scriptural expressions of physical events are always strongly condemned by succeeding generations. They are looked upon with contempt by the world at large, who cannot enter into the obsolete difficulties with which they encumbered themselves, and with pity by the more considerate and serious, who know how much sagacity and right-mindedness are requisite for the conduct of philosophers and religious men on such occasions, but who know also how weak and vain is the attempt, 287, to get rid of the difficulty by merely denouncing the new tenets as inconsistent with religious belief, and by visiting the promulgators of them with severity such as the state of opinions and institutions may allow. The prosecutors of Galileo are still up to the scorn and aversion of mankind, although, as we have seen, they did not act till it seemed that their position compelled them to do so, and then proceeded with all the gentleness and moderation which were compatible with judicial forms. Sect 5. The heliocentric theory confirmed on physical considerations. Prelude to Kepler's astronomical discoveries. By physical views, I mean, as I have already said, those which depend on the causes of the motions of matter, as, for instance, the consideration of the nature and laws of the force by which bodies fall downwards. Such considerations were necessarily and immediately brought under notice by the examination of the Copernican theory, but the loose and inaccurate notions which prevailed respecting the nature and laws of force prevented, for some time, all distinct reasoning on this subject, and gave truth little advantage over error. The formation of a new science, the science of motion and its causes, was requisite before the heliocentric system could have justice done it with regard to this part of the subject. This discussion was at first carried on, as was to be expected in terms of the received, that is, the Aristotelian doctrines. Thus, Copernicus says that terrestrial things appear to be at rest when they have a motion according to